GNU utilities. Besides having a kernel to control hardware devices, a computer operating system needs utilities to perform standard functions such as controlling files and programs. Although Linus created the Linux system kernel, he had no system utilities to run on it. Fortunately for him, at the same time, he was working a group of people working together on the internet trying to develop a standard set of computer system utilities that mimic the popular Unix operating system. The GNU organization developed a complete set of Unix utilities but had no kernel system to run them on. These utilities were developed under a software philosophy called open source software. The concept of OSS allows programmers to develop software and then release it to the world with no licensing fees attached. Anyone can use, modify, or incorporate the software into their own system without having to pay a license fee. Uniting Linux kernel with the GNU operating system, utilities created a complete, functional, free operating system. Although the bundling of the Linux kernel and GNU utilities is often just called Linux, you will see some Linux purists on the internet refer to it as the GNU or Linux system to give credit to the GNU organization for its contribution to the cause. The core GNU utilities. The GNU project was mainly designed for Unix system administrators to have a Unix-like environment. The core GNU utilities. The GNU project was mainly designed for Unix system administrators to have a Unix-like environment available. This focus resulted in the project porting many common Unix system command line utilities. The core bundle of utilities supplied for Linux systems is called Core Utils package. The GNU Core Utils package consists of three parts: properties for handling files, utilities for manipulating text, utilities for managing processes. Each of these three main groups of utilities contain several utility programs that are invaluable to the Linux system administrator and programmer. This book covers each of the utilities contained in the GNU Core Utils package in detail. The shell. The GNU or Linux shell is a special interactive utility. It provides a way for users to start programs, manage files on the file system, and manage processes running on the Linux system. The core of the shell is the command prompt. The command prompt is the interactive part of the shell. It allows you to enter text commands, and then it interprets the commands and executes them in the kernel. The shell contains a set of internal commands that you use to control tasks such as copying files, moving files, renaming files, displaying the programs currently running on the system, and stopping programs running on the system. Besides the internal commands, the shell allows you to enter the name of the program at the command prompt. The shell passes the program name off to the kernel to start it. You can also group shell commands into files to execute as a program. Those files are called shell scripts. Any command that you can execute from the command line can be placed in a shell script and run as a group of commands. This provides great flexibility in creating utilities for commonly run commands or processes that require several commands grouped together. Quite a few Linux shells are available to use on a Linux system. Different shells have different characteristics. some being more useful for creating scripts and some being more useful for managing processes. The default shell used in all Linux distributions is the Bash shell. The Bash shell was developed by the GNU project as a replacement for the standard Unix shell called the Bourne shell after its creator. The Bash shell name is a play on its wording, referred to as the Born Again shell. In addition to the Bash shell, we will cover several other shells in this book. Table 1.3 lists the different shells we will examine. Bash, a simple, lightweight shell that runs in low memory environments but has full compatibility with the Bash shell. ZSH, an advanced shell that incorporates features from Bash, PCSH, and Korn, providing advanced programming features, shared history files, and team prompts. TCSH, a shell that incorporates elements from the C programming language into shell scripts. Korn, a programming shell compatible with the Bourne shell but supporting advanced programming features like associative arrays and floating point arithmetic. Most Linux distributions include more than one shell, although usually they pick one of them to be the default. If your Linux distribution includes multiple shells, feel free to experiment with different shells and see which one fits your needs. The Linux desktop environment. In the early days of Linux, all that was available was a simple text interface to the Linux operating system. This text interface allowed administrators to start programs, control program operations, and move files around on the system. With the popularity of Microsoft Windows, a computer users expected more than the old text interface to work with. This spurred more development in the OSS community, and the Linux graphical desktops emerged. Linux is famous for being able to do things in more than one way, and no place is this more relevant than in graphical desktops. In Linux, you can choose from a plethora of graphical desktops. The following sections describe a few popular ones. The X Windows software. Two basic elements control your video environment: the video card in your PC and your monitor. To display fancy graphics on your computer, the Linux software needs to know how to talk to both of them. The X Windows software is the core element in presenting graphics. The X Windows software is a low-level program that works directly with the video card and monitor in the PC and controls how Linux applications can present fancy windows and graphics on your computer. Thus, isn't only the only operating system that uses X Window. Versions have been written for many different operating systems. In the Linux world, a few software packages can implement it. Two X Window packages are most commonly used in Linux: X.org, Wayland. The X.org package is the older of the two, based on the original X Window System version 11, often called X11. More Linux distributions are migrating to the newer Wayland software, which is more secure and easier to maintain. When you first install a Linux distribution, it attempts to detect your video card and monitor, and it then creates an X window configuration file that contains the required information. During installation, you may notice a time when the installation program scans your monitor for supported video modes. Sometimes this causes your monitor to go blank for a few days. Because lots of different types of video cards and monitors are out there, this process can take a little while to complete. The core X Windows software produces a graphical display environment but nothing else. Although this is fine for running individual applications, it is not useful for day-to-day computer use. There is no desktop environment allowing users to manipulate files or launch programs. To do that, you need a desktop environment on top of the X Windows system software. Introducing the KDE Plasma Desktop. The KDesktop environment was first released in 1966 as an open source project to produce a graphical desktop similar to the Microsoft Windows environment. The KDE Desktop incorporates all the features you are probably familiar with if you are a Windows user. Figure 1.3 shows the current version called KDE Plasma running in the OpenSUSE Linux distribution. The KDE Plasma Desktop allows you to place both application and file icons in a special area on the desktop. If you single-click an application icon, the Linux system starts the application. If you single-click a file icon, the KDE Desktop attempts to determine what application to start to handle the file. System Memory Management. Next, Software Program Management. The Linux operating system calls a running program a process. A process can run in the foreground, displaying output on a display. If it can run in the background, behind the scenes. The kernel controls how the Linux system manages all the processes running on the system. The kernel creates the first process called the init process to start all other processes on the system. When the kernel starts, it loads the init process into virtual memory. As the kernel starts much additional process, it gives the process a unique area in virtual memory to store the data and code that process uses. Allow different types of init process implementations are available in Linux, but these days, the two most popular are sysv init, the sysv init initialization method. The original method used by Linux was based on the Unix System V initialization method. Though it's not used by many Linux distributions these days, you still may find it around in older Linux distributions. Systemd. The Systemd initialization method created in 2010 has become the most popular initialization and process management system used by Linux. The sysv initialization method used a concept called run levels to determine what processes to start. The run level defines the state of the running Linux system and what process should run in each state. Table 1.1 shows the different run levels associated with the sysv initialization method. The structure of the kernel is virtual memory on the left side, the kernel on the middle, physical memory on the right. The kernel is primarily responsible for four main functions: system memory management, software program management, hardware management, file system management. Note, Chapter 4, more bash shell commands. You'll see how to use the ps command to view the processes currently running on the Linux system. Hardware management. Still another responsibility for the kernel is hardware management. Any device that Linux system must communicate with needs driver code inserted inside the kernel code. The driver code allows the kernel to pass data back and forth to the device, acting as an intermediary between applications and the hardware. Two methods are used for inserting device driver code in Linux kernel: drivers compiled in the kernel, driver modules added to the kernel. Previously, The only way to insert device driver code was to recompile the kernel. Each time you added a new device to the system, you had to recompile the kernel code. This process became even more inefficient as Linux kernel supported more hardware. Fortunately, Linux developers devised a better method to insert driver code into the running kernel. Programmers developed the concept of kernel modules to allow you to insert driver code into a running kernel without having to compile the kernel. Also, a kernel module could be removed from the kernel when the device was finished being used. This shortly simplified and expanded using hardware with Linux. The Linux system identifies hardware devices as special files called device files. There are three classifications of device files: character, block, network. Character device files are for devices that can handle data only one character at a time. Most types of modems and terminals are created as character files. Block files are for devices that can handle data in large blocks at a time, such as disk drives. The network file types are used for devices that use packets to send and receive data. This includes network cards and a special loopback device that allows the Linux system to communicate with itself using common network programming protocols. Linux creates special files called nodes for each device on the system. All communication with the device is performed through the device node. Each node has a unique number pair that identifies it to the Linux kernel. The number pair includes a major and a minor device number. Similar devices are grouped into the same major device number. The minor device number is used to identify a specific device within the major device group. File system management. Unlike some other operating systems, the Linux kernel can support different types of file systems to read and write data to and from hard drives. Besides having over a dozen file systems of its own, Linux can read and write to and from file systems used by other operating systems, such as Microsoft Windows. The kernel must be compiled with support for all types of file systems that the system will use. Table 1.2 lists the standard file system that a Linux system can use to read and write data: ext, ex2, ex3, ex4, exFAT, ncp, nfs, ntfs, vfat, xfs. Any hard drive that Linux server access must be formatted using one of the file system types listed in Table 1.2. The Linux kernel interfaces with each file system using the Virtual File System, VFS. This provides a standard interface for the kernel to communicate with any type of file system. VFS cache information in memory as each file system is mounted and used. The kmenu in KDE Plasma desktop environment. Much like the Windows Start menu, the kmenu contains links to start installed applications. Program shortcuts. These are quick links to start applications directly from the panel. The taskbar. The taskbar shows icons for applications currently running on the desktop. Applets. These are small applications that have an icon in the panel that can often change depending on information from the application. All of the panel features are similar to what you find in Windows. In addition to desktop features, the KDE project has produced a wide assortment of applications that run in KDE environment. Other desktops. One of the main features of Linux is choice, and nowhere is that more evident than in the graphical desktop world. There are a plethora of different types of graphical desktop available in the Linux world. Examining Linux distributions. Now that you have seen the four main components required for a complete Linux system, you may be wondering how you are doing to get them all together to make a Linux system. Fortunately, there are people who have already done that for you. A complete Linux system package is called a distribution. Numerous Linux distributions are available to meet just about any computing requirement you could have. Most distributions are currently are customized for a specific user group, such as business users, multimedia enthusiasts, software developers, or average home users. Each customized distribution includes the software packages required to support specialized functions such as audio and video editing software for multimedia enthusiasts or compilers in integrated development environments for software developers. Console terminals. One way to get to a CLI is to access the Linux system via text mode. This provides nothing more than a simple shell CLI on the monitor, just like the days before graphical desktops. This mode is called the Linux console because it emulates the old days of hardware console terminal and is a direct interface to the Linux system. When the Linux system starts, it automatically creates several virtual consoles. A virtual console is a terminal session that runs in Linux system memory. Instead of having several dumb terminals connected to the computer, most Linux distributions start 5 or 6 or sometimes even more virtual consoles that you can access from a single computer keyboard and monitor. Graphical terminals. The alternative to using a virtual console terminal is to use terminal emulation package from within the Linux graphical desktop environment. A terminal emulation package simulates working a console terminal but within a desktop graphical window. Figure 2.1 shows an example of a terminal emulator running a Linux graphical desktop environment. Graphical terminal emulation is responsible only for a portion of the Linux graphical experience. As a whole, the experience is accomplished through several components, including graphical terminal emulation software called a client. Table 2.1 shows the different components in the Linux graphical desktop environment. Graphical interface elements, client, graphical terminal emulator, desktop environment, GNOME, Shell, KDE Plasma, network browser, an application that requests graphical services, display server, Wayland, X window system, element that manages the display or screen and the input device such as keyboard, mouse, and touchscreen. Window Manager, Matter, MetaCity, Queen, element that add borders to windows and provides features to move and manage windows. Widgets Library, Plasmoids, Cinnamon, Spices, element that add menus and appearance items for desktop environment clients. For dealing with the command line for the desktop, the focus is in the graphical terminal emulator. You can think of graphical terminal emulators as CLI terminals in the graphical user interface or GUI, and virtual console terminals as CLI terminals outside the GUI. Understanding the various terminals and their features can enhance your command line experience. Accessing CLI via a Linux console terminal. In the early days of Linux, when you booted up your system, you would see a login prompt on your monitor, and that's all. As mentioned earlier, this is called the Linux console. It was the only place you could enter commands for the system. Even though several virtual consoles are created at boot time, many Linux desktop distributions switch to a graphical environment after the boot sequence completes. This provides the user with a graphical login and desktop experience. For these systems, accessing a virtual console is done manually. On most Linux distributions, you can access one of the Linux virtual consoles using a simple keystroke combination. Usually, you must hold down the CTRL plus Alt key combination and then press a function key such as F1 through F7 for virtual console you want to use. Function key F2 produces Virtual Console 2, key F3 produces Virtual Console 3, key F4 produces Virtual Console 4, and so on. Linux distributions typically use the CTRL Alt key combination with F1, F7, or F8 to reach the graphical interface. Ubuntu and CentOS both use F1. However, it is best to test and see where your distribution puts the graphical interface, especially on older distribution versions. Getting to the shell. In the old days of Linux, system administrators, programmers, and system users all sat at something called a Linux console terminal, entering shell commands and viewing text output. These days, with graphical desktop environments, it's getting harder to get to a shell prompt on the system in order to enter shell commands. This chapter discusses what is required to reach a command line environment, and it walks you through a few terminal emulation packages you may run into in the various Linux distributions. Reaching the command line. Before the days of graphical desktops, the only way to interact with the Unix system was through a text command line interface, CLI, provided by the shell. The CLI allowed text input only and would display only text and rudimentary graphics output. Because of these restrictions, output devices were not very fancy. Often, you needed only a simple dumb terminal to interact with the Unix system. A dumb terminal was usually nothing more than a monitor and a keyboard connected to the Unix system via a communication cable, usually a multi-wire serial cable. This simple combination provided an easy way to enter text data into the Unix system and view text results. As you well know, things are significantly different in today's Linux environment. Just about every Linux desktop distribution uses some type of graphical desktop environment. However, to enter shell commands, you still need a text display to access the shell CLI. The problem now is getting to one. Sometimes finding a way to get a CLI in a Linux distribution is not an easy task. Console terminals. One way to get to a CLI is to access the Linux system via text mode. This provides nothing more than a simple shell CLI on the monitor, just like the days before graphical desktops. This mode is called the Linux console because it emulates the old days of hardwired console terminal and is a direct interface to the Linux system. When the Linux system starts, it automatically creates several virtual consoles. A virtual console is a terminal session that runs in Linux system memory. Instead of having several dumb terminal connected to the computer, most Linux distributions start 5 or 6 or sometimes even more virtual consoles that you can access from a single computer keyboard and monitor. Graphical terminals. The alternative to using a virtual console terminal is to use a terminal emulation package from within the Linux graphical desktop environment. A terminal emulation package simulates working a console terminal but within a desktop graphical window. Figure 2.1 shows an example of a terminal emulator running in a Linux graphical desktop environment. Accessing CLI via a Linux console terminal. In the early days of Linux, when you booted up your system, you would see login prompt on your monitor, and that's all. As mentioned earlier, this is called the Linux console. It was the only place you could enter commands for the system. Even though several virtual consoles are created at boot time, many Linux desktop distributions switch to a graphical environment after the boot sequence completes. This provides the user with a graphical login and desktop experience. For these systems, accessing a virtual console is done manually. On most Linux distributions, you can access one of the Linux dual consoles using a simple keystroke combination. Usually, you must hold down the Ctrl plus Alt key combination and then press function key F1 through 7 for virtual console you want to use. Function key F2 produces Virtual Console 2, key F3 produces Virtual Console 3, key F4 produces Virtual Console 4, and so on. In the previous chapter, you saw how to manipulate the flow of a shell script program by checking the output of commands and the values of variables. In this chapter, we continue to look at structured commands that control the flow of your shell scripts. You'll see how you can perform repeating processes, commands that can loop through a set of commands until an indicated condition has been met. This chapter discusses and demonstrates the for, while, and until bash shell looping commands. Looking at the for command, iterating through a series of commands is a common programming practice. Often, you need to repeat a set of commands until specific condition has been met, such as processing all the files in a directory, all the users on a system, or all the lines in a text. The bash shell provides the for command to allow you to create loop that iterates through a series of values. Each iteration performs a defined set of commands using one of the values in the series. Here's the basic format of the bash shell for command. For var in list, do commands done. You supply the series of values used in the iterations in the list parameter. You can specify the values in the list in several ways. In each iteration, the variable var contains the current value in the list. The first iteration uses the first item in the list, the second iteration the second item, and so on, until all the items in the list have been used. The commands entered between do and done statements can be one or more standard bash shell commands. Within the commands, the var variable contains the current list item value for the iteration. Note, if you prefer, you can include the do statement on the same line as the for statement, but you must separate it from the list items using a semicolon. For var in list semicolon do. We mentioned that there are several ways to specify the value in the list. The following sections show the various ways. Reading values in a list. The most basic use of the for command is to iterate through the list of values defined within the for command itself. Cat s1 bin /bash basic for command. For test in Alabama, Alaska, Arizona, Arkansas, California, Colorado, do echo. The next state is test. Done. And then on ./test1, the next state is Alabama, the next state is Alaska, the next state is Arizona, the next state is Arkansas, the next state is California, the next state is Colorado. Each time the for command iterates through the list of values provided, it assigns the test variable the next value in the list. The test variable can be used just like any other script variable within the for command statements. After the last iteration, the test variable remains valid throughout the remainder of the shell script. It retains the last iteration value unless you change its value. The test variable retained its value and allows us to change the value and use it outside of the for command loop as any other variable would. Reading complex values in a list. Things aren't always as easy as they seem with the for loop. There are times when you run into data that causes problem. Here's a classic example of what can cause problems for shell script programmers. Ouch, that hurts. The shell saw the single quotation marks within the list values and attempted to use them to define a single data value, and it really messed things up in the process. You have two ways to solve this problem. The escape character, the backlash, to escape the single quotation mark. Use double quotation marks to define the values that use single quotation marks. Now that we've covered the basics of Linux system and the command line, it's time to start coding. This chapter discusses the basics of writing shell scripts. You'll need to know these basic concepts before you can start writing your own shell script masterpieces. Using multiple commands. So far, you've seen how to use the command line interface prompt of the shell to enter commands and view the command results. The key to shell scripts is the ability to enter multiple commands and process the results from each command, even possibly passing the results of one command to another. The shell allows you to chain commands together into a single steps. If you want to run two commands together, you can enter them on the same prompt line, separated with a semicolon. Congratulations, you just wrote a shell script. This simple script uses just two bash shell commands. The date command runs first, displaying the current date and time, followed by the output of the who command, showing who is currently logged onto the system. Using this technique, you can string together as many commands as you wish, up to the maximum command line character count of 255 characters. Although using this technique is fine for small scripts, it has a major drawback in that you have to enter the entire command at the command prompt every time you want to run it. Instead of having to manually enter the commands on a command line, you can combine them into a simple text file. When you need to run the commands, just simply run the text file. Creating a script file. To place shell commands in a text file, first you'll need to use a text editor to create a file and then enter the commands into the file. When creating a shell script file, you should specify the shell you are using in the first line of the file. The format for this is #!! /bin/bin/bash. In a normal shell script line, the $sign is used as a comment line. A comment line in a shell script isn't processed by the shell. However, the first line of a shell script file is a special case, and the $sign followed by the exclamation point tells the shell what shell to run the script under. Yes, you can be using a bash shell and run your script using another shell. After indicating the shell, commands are entered onto each line of the file, followed by a carriage return. As mentioned, comments can be added by using the $sign. An example looks like this: #!bin/bin/bash Hashtag this script displays the date and who's logon date. Woo. And that's all there is to it. You can use the semicolon and put both commands on the same line if you want to, but in a shell script, you can list commands on separate lines. The shell will process commands in the order in which they appear in the file. Also notice that another line was included that starts with the pound symbol and adds a comment. Lines that start with the pound symbol, other than the first hashtag exclamation line, aren't interpreted by the shell. This is a great way to leave comments for yourself about what's happening in the script, so that when you come back to it 2 years later, you can easily remember what you did. Save this script in a file called test1 and you are almost ready. There are still a couple of things to do before you can run your new shell script file. If you try running the file now, you'll be somewhat disappointed to see this. The first hurdle is getting the bash shell to find your script file. If you remember from using Linux environment variables, the shell uses an environment variable called path to find commands. A quick look at the path environment variable demonstrates our problem. The path environment variable is set to look for commands only in a handful of directories. To get the shell to find the test1 script, we need to do one of two things. Add a directory where our shell script file is located to the path environment variable. Use an absolute or relative file path to reference our shell script file in the prompt. Tip: exploring the while command. The while command is somewhat of a cross between the if-then statement and the for loop. The while command allows you to define a command to test and then loop through a set of commands for as long as the defined test command returns a 0 exit status. It tests the test command at the start of each iteration. When the test command returns a non-zero exit status, the while command stops executing the set of commands. Basic while format. Here's the format of the while command. While test command, do, other commands, done. The test command defined in the while command is the exact same format as in if-then statements. As in the if-then statement, you can use any normal bash shell command or you can use the test command to test for conditions such as variable values. The key to while command is that the exit status of the test commands specified must change based on the commands run during the loop. If the exit status never changes, the while loop will get stuck in an infinite loop. The most common use of the test command is to use brackets to check a value of a shell variable that's used in the loop commands. The while command defines the test condition to check for each iteration. As long as the test condition is true, the while command continues to loop through the commands defined. Within the commands, the variable used in the test condition must be modified or you'll have an infinite loop. In this example, we use shell arithmetic to decrease the variable value by 1. var1 equals to $var1 minus 1. The while loop stops when the test condition is no longer true. Using multiple test commands, the while command allows you to define multiple test commands on while statement line. Only the exit status of the last test command is used to determine when the loop stops. This can cause interesting results if you're not careful. Here's an example of what we mean. Pay close attention to what happened in this example. Two test commands were defined in the while statement. The first test simply displays the current value of the var1 variable. The second test uses brackets to determine the value of the var1 variable. Inside the loop, an echo statement displays a simple message indicating that loop was processed. Notice then you run the example How the output ends. The while loop executed the echo statement when the var1 variable was equal to 0. Linux Bible Introduction. Linux seems complicated, but it can be divided into 4 parts: application software, window management software, GNU system utilities, and the kernel. Looking into the kernel can be divided into system memory management, software program management, hardware management, file system management. Memory management. The kernel divides the memory into physical and virtual. It does this by using space on the hard disk called swap space. The kernel swaps the contents of virtual memory locations back and forth from the swap space to the actual physical memory. System memory locations are grouped into blocks called pages. The kernel locates each page of memory in either the physical memory or swap space. It maintains a table of the memory pages that indicates which are in physical and virtual memory. So for program management, every program in Linux is called a process, which can be run in the foreground or background. The kernel controls how the Linux system manages all the processes in the system. Linux makes it easy for software to communicate through its initialization method. There are many initialization methods in the market, but the most useful are sysv and systemd. Systemd allows for the startup of multiple processes at the same time, while sysv follows orders. Sysv init method was based on Unix system v init but is not used by many Linux distributions these days. Systemd, created in 2010, has become the most popular initialization and process management system. It has become popular because of its ability to start processes on different events. First, when the system boots. Second, when a particular hardware device is connected. Third, when a service is started. 4. When a network connection is established. 5. When a timer has expired. It determines which events to run by linking events to unit files. The systemctl program allows you to start, stop, and list the unit files currently running on the system. It groups unit files together into targets. Hardware management. Another responsibility of the kernel is hardware management. Any device that the Linux system must communicate with needs driver code inserted inside the kernel code. This allows the kernel to pass data back and forth to the device, acting as an intermediary between applications and hardware. The methods used for inserting drivers now are: 1. Drivers compiled in the kernel. 2. Driver modules added to the kernel. Previously, the only way to insert device driver code was to compile the kernel each time you added a new device to the system. You had to recompile the kernel code. This system became inefficient as the kernel supported more hardware. Linux developers devised better methods, allowing you to insert driver code into a running kernel without having to compile the kernel, and allowing you to remove the driver when the device was finished being used. It does this through the identification of devices via special files called device files. There are 3 classifications of device files: character, block, and network. Character devices read characters at a time. Terminals are examples of character devices. Block devices read and write blocks at a time. Examples include hard drives. NIC and loopback devices are for network data. File system management. The Linux kernel supports different types of file systems to read and write data to and from hard drives. Besides having over a dozen file systems of its own, Linux can read and write to file systems used by other operating systems such as Windows. Any hard drive that Linux accesses must be formatted into one of the supported file systems. The Linux kernel interface and uses VFS to standardize the support for other file systems such as NTFS. Configuring and maintaining server functions and features. Once you have installed your servers, you must take additional steps to enable them to perform the roles you choose for them in the network. You also need to monitor and maintain the servers so that they continue to perform well. In addition, you want to avoid security-related issues such as malware infections and data breaches by instituting and following best practices with regards to patches, updates, and data security. Server role requirements. Server exists to serve the network and its users in some form. Each server has a certain role to play, although in small networks, a server performs multiple roles. Each of those roles places different types of demand on the hardware and software of the server. Some roles demand lots of memory, whereas others place a heavier load on CPU. Warning: the size of your network, the number of servers you have performing a role, and in some cases, the exact way you deploy the server will have a big impact on the requirements. For example, if the server will be either a domain controller or a DNS server, you will almost certainly want to have multiple servers for these roles in case one should fail. Print, memory. Print servers need lots of memory to hold the print jobs waiting in the print queue. The exact amount will be the number of users assigned to the printers being managed by this printer server. CPU. The number and type of CPUs are impacted by the amount of processing power available on the print devices the server is managing. Disk. As is the case with processing power, if there's plenty of disk space on the print device, you will need less on the print server. NIC. As always, use 1 GB NICs, and if the server will be managing many printers and thus many users, you may want to have multiple NICs for fault tolerance and load balancing. Database. A database server is one that runs database software such as SQL Server or Oracle. It contains information stored in the database, and users can search the database either directly by issuing commands or by using an application that does this through a GUI. Here are some of the components that should be maximized to ensure good performance in a database server. CPU. Your CPU, yes, multiple, should be as fast as you can afford with multiple cores and plenty of cache. The specific number should be driven by the database software, recommendations, and the number of users. Memory. With respect to memory, you should fill all available slots with the cheapest memory you can get. That means smaller DIMMs, dual inline memory modules, but more of them. For example, rather than filling 12 slots with 64 GB of memory, save some money for very little cost and speed by installing 32 gigs DIMMs. Disk. You should use multiple disks in RAID 5 configuration so that you get performance and fault tolerance. Network. File. File servers are used to store files that can be accessed by the network users. Typically, users are encouraged or even required to store any important data on the servers rather than on their local hard drives, because these servers are typically backed up on a regular basis, whereas the user machine typically are not. Here, the disk file servers should have significant amounts of storage space and may even have a multiple hard drives configured in a RAID array to provide quicker recovery from a drive crash that could be provided by recovering with a backup. CPU. As the number of users increases, at a certain point, it becomes better to use more and slower processors rather than fewer and faster ones. GNU utilities. Besides controlling hardware and application programs, the operating system needs utilities. The Linux desktop environment. In 1990, administrators who managed and automated Fortune 500 company systems started programs, controlled program operations, and moved files around on the system through a simple text interface. Due to the popularity of Windows environment that provides a graphical interface to CLI, there was an exponential increase in development in the OSS community, leading to the development of the Linux graphical desktop environment. The X Windows software. MIT played a key role in leading the development of graphical interfaces, though Windows invested a lot in their research for this, just as they do with artificial intelligence. Two basic elements control your video environment: the video card in your PC and your monitor. To display fancy graphics on your computer, the Linux software needs to know how to talk to both of them. The X Windows software is the core element in presenting graphics. It is a low-level program that works directly with the video card and monitor the PC and controls how Linux applications can present fancy windows and graphics on your computer. Linux isn't the only OS that uses X Window. Versions have been written for many different OS. In the Linux world, a few software packages can implement it. Two X Window packages are most commonly used in Linux. 1. X.org. 2. Wayland. Wayland persists among the two because of better security and easier maintenance. The first is known for the difficulty of configuration because it was based on the original Linux X Window system version 11 or X11. When you first install the distribution, it attempts to detect your video card and monitor, and it then creates an X Window configuration file that contains the required information to function properly. It's a complex theory applied in the real world. You may notice a time when the installation program scans your monitor for supported video modes, sometimes causing your monitor to go blank for a few seconds, because there are many different types of video cards and monitors. The initialization process of computers takes a while to complete. The X Windows software produces a graphical display environment where you can put icons, but it has none. Although this is fine for running individual applications, it is not useful for day-to-day computer use. Therefore, standards of useful commands available on screen need to be established for administrators and subsequently users. To manipulate files or launch programs, you need a desktop on top of the display environment. The KDE Plasma Desktop. Just like shells, different distributions have different characteristics that can be useful for different goals and user requirements. The KDesktop environment was first released 30 years ago as an open source project to produce a graphical desktop similar to the Microsoft Windows environment. It was designed to incorporate all the features of Windows to add things you are familiar with based on human computer interaction concepts. KDE can run on the Open SUSE distribution. It allows you to place both application and file icons in a special area on the desktop. We forget the powerful ability to configure our applications in our display today because we don't want to work. It's easier to let others configure things for us instead of doing it ourselves. If you single click an application icon, the Linux system starts the application. If you single click a file icon, the KDE desktop attempts to determine what application to start to handle the file. The bar at the bottom of the desktop is called the panel. The panel consists of 4 parts, which are similar to what you would see in Windows. The basic 4 are 1. The K menu. Much like the Windows Start menu, the K menu contains links to start installed applications. 2. Program shortcuts. These are quick links to start applications directly from the panel. 3. The taskbar. The taskbar shows icons from applications currently running on the desktop. 4. Applets. These are small applications that have an icon in the panel that can often change depending on information in the KDE environment. A lot of applications were designed to run in the KDE environment, which produced a wide assortment of applications that run on it. The GNOME Desktop. The GNU Network Object Model environment is another popular Linux desktop environment. GNOME was released 27 years ago and has become the default desktop environment for many Linux distributions, the most popular being Red Hat Linux. Note: GNOME underwent a radical change 15 years ago. It departed from standard menus and taskbars to make the interface more user-friendly across multiple platforms, such as tablets and mobile phones, by reducing a lot of menus. People slowly accepted the new and improved look. It cleans the desktop environment by reducing available menus to just 3. 1. Activities. Displays favorites as well as any running applications. 2. Calendar. Shows the current date or time along with any system notification messages. 3. System. Shows network connections, system settings, and options to restart the system. To launch applications, you must search for them using Activities. Overview, which is a search feature on the Activities menu. Remember, the search feature is just one of many features of the Activities menus, just like how commands are just part of a program or script. To not be outdone by KDE, GNOME also produces useful graphical applications integrated with it. Some people dislike version 3 and like version 2 of GNOME, which leads them to create Cinnamon, which is available in Ubuntu, Fedora, OpenSUSE, and Mint. The downside to these fancy graphical desktop environments is they require a fair amount of system resources to operate properly. In 1990, the selling point of Linux was its ability to perform on older PCs that the newer Microsoft couldn't operate. With KDE and GNOME, the economics changed for Linux. However, Linux developers took it back to its roots through the creation of low memory-oriented graphical desktop applications that provide basic features to run perfectly fine on old PCs. They only support the basics such as word processing, spreadsheets, databases, drawing, and, of course, multimedia support just like in the early days of Mac and Windows. The Windows OS won, but Linux is still cheaper today but less secure. Examining Linux distributions. It seems complex to build everything from the start. Fortunately, there are people who have combined all of these to make it usable for you and the administrator of the company. The combination of the kernel, GNU utilities, window management utilities, and software programs created by GNU utilities are called Linux, distributions. Numerous distributions are available to meet just about any computing requirement you could have. Most distributions are customized for a specific user group, such as business users and multimedia enthusiasts, developers, software developers, or average home users. Each customized distribution includes the software packages required to support specialized functions such as audio and video editing software for multimedia enthusiasts, or compilers and integrated development environments for software developers. Different Linux distributions are often divided into full core and specialized Linux distributions. The following sections describe them. Core Linux distributions. Core contains a kernel, one or more graphical desktop environments, and just about every Linux application that is available pre-compiled for the kernel. It provides one-stop shopping for a complete Linux installation. 1. Red Hat Enterprise, a commercial business distribution used mainly for internet servers. 2. Debian, popular with Linux experts and commercial Linux products. 3. Slackware, one of the originals popular with Linux geeks. 29 years ago, distribution was released as a set of floppy disks. You had to download a bunch of files and copy them onto 20 or more disks. Nowadays, distributions are released as an ISO image file. The ISO image file is a complete disk image of a DVD as a single file. You do this through 1. Software application. You can use software applications to burn the ISO image file onto a DVD. 2. Bootable USB stick. You can use a bootable USB stick to boot the Linux OS in your formatted drive supported by Linux to have the Linux OS on your system. However, beginners still often run into configuration problems when they try to use Linux just like Windows. To cover just about any situation, it makes the OS like a learned man or expert technical support by including lots of application software such as high-end internet database servers to common games. Although having lots of options is good, it can become overwhelming to new users, just like how wholesaling is not recommended for a new real estate investor. We need to start things step by step to master increasingly complex concepts, just as we learn to read increasingly complex books. Because of this need, Core Distributions programs a series of questions during the installation process to determine which applications to load by default, what hardware is connected to the PC, and how to configure hardware. There's a double-edged sword strength and weakness for this. It helps expert Linux users become productive, but it confuses beginners. New users often load too many programs or don't load enough and later discover their computer won't do what they want. Specialized Linux distributions. Specialized Linux distributions contain only a subset of applications that would make sense for a specific area of use. Remember, the applications available in computers used to be target applications for offices or the corporate world to make them more productive, such as office products for business users, which makes them the basic applications needed in computers. Specialized distributions attempt to auto-configure and troubleshoot hardware devices, which makes installing an enjoyable process. The installation is often the hard part of the computer system because the beginning is always hard. Once the system is up and running, any action that makes it unusable should be avoided. Examples of specialized Linux distributions that are easy to use for beginners are 1. Fedora, a free distribution built from Red Hat Enterprise Linux source code. 2. Ubuntu, a free distribution for school and home use. 3. MX Linux, a free distribution for home use. 4. Linux Mint, a free distribution for home entertainment use. 5. Puppy Linux, a free distribution that runs well on older PCs. That's just a small sampling of specialized Linux distributions. Linux has seemingly become complicated because of its open source philosophy. There are literally hundreds of specialized Linux distributions, and more are popping up all the time on the internet. No matter your specialty, you'll probably find a distribution already built for you. Many of these specialized Linux distributions are based on the Debian Linux distribution. They use the same installation files as Debian, but package only a small fraction of a full-blown Debian system. Note, Live DVD allows you to test specialized or full-blown distributions with your hardware before installing the system. Linux is not as complicated as we think as long as we are patient, because the combination is more than the sum of its parts. It will reward us through the compound effect of relationships of concepts we learn if we stay on track. In the next chapter, we will dig deep into writing scripts, particularly writing for graphical desktops, to understand how the graphics we see on our screen work. Understanding the shell. Now that you know a few shell basics, such as reaching the shell and rudimentary commands, it's time to explore the actual shell process. To understand it, you need to know how it operates in different circumstances. A shell is not just a CLI, it is a complicated interactive running program. Entering commands and using the shell to run scripts can raise some interesting and confusing issues. Understanding the shell process and its relationships help you resolve these issues or avoid them altogether. This chapter takes you through learning about the shell process and how it operates in various situations. We'll explore how subshells are created as well as the relationship to their parent shell. The different commands that create child processes are examined along with those that don't. Built-in commands. We also cover some shell tips and tricks you can try to make your CLI experience more productive. Investigating shell types. The shell program that the system starts when you log into the system depends on your user ID configuration. In the /etc/passwd file, the user ID has its default shell program listed in the field number 7 of its entry. This default shell program is started when the user either logs into a virtual console terminal or starts a terminal emulator in the GUI. In the following example, the user Christine has the GNU Bash shell as their default shell program. cat/etc/passwd. The bash shell program, or bash, typically resides in the /usr/bin directory on modern Linux systems. However, on your Linux system, you may find it in the /bin directory. The which bash command can help here by providing the directory and file name to use for the bash shell. A long listing reveals that the bash file, or the bash shell, is an executable program with a trailing asterisk on the file's name. Note, typically on modern Linux systems, the /bin directory is symbolically linked to the /usr/bin/directory, which is why the user Christine has /bin/bash listed as their default shell program, but the bash shell program actually resides in the /usr/bin/directory. Symbolic or soft links were covered in Chapter 3, Basic Bash Shell Commands. Several other programs are on this particular Linux system. They include TCSH, which is based on the original C shell. Another shell on this system is ZSH, which is a more elaborate version of the bash shell. It also has a few TCSH features as well as other elements. Tip: if you don't find some of these shells on your Linux system, you may be able to install them. Chapter 9, Installing Software, can help you accomplish this task. A soft link, see Chapter 3 of the C shell, points to the TCSH shell. On Debian-based Linux systems, such as Ubuntu, you often find Dash, which is a version of the Ash shell. Note: a brief description of various shells was included in Chapter 1, starting with Linux shells. You may be interested in learning even more about shells other than the GNU Bash shell. Additional alternative shell information is in Chapter 23, Working with Alternative Shells. On most Linux systems, you'll find the various installed shells that can be used as the user's default shell within the /etc/shells file as shown here. A user can set any of these different shell programs on this system as their shell. However, due to its popularity, it is rare to use any other shell instead of bash as an account's default interactive shell. The default interactive shell, also called a login shell, starts whenever a user logs into a virtual console terminal or starts a terminal emulator in the GUI. Another shell, SH, is the default system shell. The default system shell is used for system shell scripts, such as those needed at startup. Often, you see a distribution with its default system shell, SH, pointing to the bash shell, using a soft link. An example of this is shown here on a CentOS distribution. However, be aware that on some distributions, the default system shell is linked differently, such as on this Ubuntu distribution. In this case, the default system shell /usr/bin/sh points to the dash shell instead of the bash shell. Tip: for bash shell scripts, these two different shells, default interactive shell and default system shell, can cause problems. Be sure to read about the important syntax needed for a bash shell script's first line in Chapter 11, Basic Script Building, to avoid these issues. You are not forced to stick with your default interactive shell. You can start any shell available on your distribution simply by typing its name. However, there is no fanfare or message displayed to indicate what shell you are currently using, but help is available from the $0 variable. The command echo $0 will display the name of your current shell, providing the needed reference. Note: the echo $0 command shows the current shell in use only when issued at the shell's prompt. If used in a shell script, it will display the script's name instead. This is covered in Handling User Input chapter. With our handy $0 variable, we'll display the shell we are currently using. Start the shell by typing the command dash and show the new shell's name via echo $0 again. Note: in the previous example, notice the dash in front of the bash response from the first echo $0 command. This indicates that this shell is the user's login shell. The $ prompt is a CLI prompt for the dash shell. You can leave the dash shell program and the bash shell for that matter by typing the command exit. Jumping back and forth, through the various shells seems simple, but there is more to the action happening behind the scenes. To understand this process, the next section explores the relationship between a login shell program and a newly started shell program. Exploring parent and child shell relationships. The default interactive shell, or login shell, that starts when a user logs into a virtual console terminal or starts a terminal emulator in the GUI is a parent shell. As you have read so far in this book, a parent shell process provides a CLI prompt and waits for commands to be entered. When the bash command or other shell program name is entered at the CLI prompt, a new shell program is created. This is a child shell. A child shell also has a CLI prompt and waits for commands to be entered. Because you do not see any relevant messages when you type bash and spawn a child shell, another command can help bring clarity. The ps command was covered in chapter 4, more bash shell commands. Using this with the negative option before and after entering a shell is useful. The first use of ps-f shows two processes. One process has a process ID of 6160, second column, and is running the bash shell program, last column. Parent and child bash shell processes. When a child shell process is spawned, only some of the parent's environment is copied to the child shell environment. This can cause problems with items such as variables. How to prevent such problems is covered in Chapter 6, using Linux environment variables. A child shell is also called a subshell. A subshell can be created from a parent shell, and a subshell can be created from another subshell. In the preceding example, the bash command was entered 3 times. Effectively, this created 3 subshells. The ps --forest command shows the nesting of these subshells. Figure 5.2 also shows this subshell nesting. The ps-f command can be useful in subshell nesting because it displays who is whose parent via the ppid column. The bash shell program can use command line options to modify the shell start. Table 5.1 lists a few of these available switches to use with the bash command. Subshell nesting. The bash command line options. Option -c string description reads commands from string and processes them. -i starts an interactive shell, allowing input from the user. -l acts as if invoked as a login shell. -r starts a restricted shell, limiting the user to the default directory. -s reads commands from the standard input. You can find more help on the bash command and even more command line parameters by typing man bash. The bash --help command provides additional assistance as well. Tip: if you'd like to see the version of the bash shell, just type bash --version at the command line. This won't create a subshell, but instead displays the current version of your system's GNU bash shell program. Not only does the exit command allow you to leave child subshells, but you can log out of your current virtual console terminal or terminal emulation software as well. Just type exit in the parent shell and you gracefully exit the CLI. Also, a subshell is sometimes created when you run a shell script. We learn more about that topic in Chapter 11. Next, we'll cover how a subshell is spawned using a process list. Looking at process lists, on a single line, you can designate a list of commands to be run one after another. This is done by entering a command list using a semicolon between the commands. In the preceding example, The commands all executed one after another with no problems. However, while using commands in this manner is called a list, it is not a process list. For a command list to be considered a process list, the commands must be encased in parentheses. Though the parenthesis addition may not appear to be a big difference, they do cause a very different effect. Adding parentheses and turning the command list into a process list created a subshell to execute the commands. Note, a process list is a command grouping type. Another command grouping type puts the commands between curly brackets and ends the command list with a semicolon. The syntax is as follows: close bracket command, semicolon, close bracket. Using curly brackets for command grouping does not create a subshell as a process list does. To indicate if a subshell was spawned, a command using an environment variable is needed here. Environment variables are covered in detail in chapter 6. The command needed is echo bash dash subshell. If it returns 0, then there is no subshell. If it returns 1 or more, a subshell was created. First, the example using just a command list is executed with the echo $bash dash sub underscore sub dash shell tack onto the end. Creating functions. In this chapter, we will discuss exploring basic script functions, returning a value from a function, using variables in functions, investigating array variables and functions, considering function recursion, creating a library, using functions on the command line. Often, while writing shell scripts, you'll find yourself using the same code in multiple locations. If it's just a small code snippet, it's usually not that big a deal. However, rewriting a large chunks of codes multiple times in your shell script can get tiring. The bash shell provides a way to help you out by supporting user-defined functions. You can encapsulate your shell script code into a function and use it as many times as you want, anywhere in your script. This chapter walks you through the process of creating your own shell script functions and demonstrate how to use them in other shell script applications. Exploring basic script functions. As you start writing more complex shell scripts, you'll find yourself reusing parts of code that perform specific tasks. Sometimes it's something simple, such as displaying a text message and retrieving an answer from the script users. Other times, it's a complicated calculation that's used multiple times in your script as a part of a larger process. In each of these situations, it can get tiresome writing the same blocks of code over and over in your script. It would be nice to just write the block of code once and be able to refer to that block of code anywhere in your script without having to rewrite it. The bash shell provides a feature allowing you to do just that. Functions are blocks of script code that you assign a name to and reuse anywhere in your code. Whenever you need to use that block of code in your script, you simply use the function name you assigned it, referring to as calling the function. This section describes how to create and use functions in your shell scripts. Creating a function. You can use one of two formats to create functions in bash shell scripts. The first format uses the keyword function, along with the function name you assign to the block of code. Function, space name, opening bracket, enter commands, closing bracket. The name attribute defines a unique name assigned to the function. Each function you define in your script must be assigned to a unique name. The commands are one or more bash shell commands that make up your function. When you call the function, the bash shell execute each of the commands in the order in which they appear in the function, just as in a normal script. The second format for defining a function in a bash shell script more closely follows how functions are defined in other programming languages. Name, open and close, parenthesis, space, open, bracket, enter commands, enter close bracket. The empty parentheses after the function name indicate that you're defining a function. The same naming rules apply in this format as in the original shell script function format. Using functions. To use a function in your script, specify the function name on a line just as you would any other shell command. Cat test1, bin bash, hashtag using a function in a script, function, func1, opening bracket, echo, this is an example of a function, closing bracket, initial or count equals to 1, while space opening bracket count is less than or equal to 5, do func1, count equals to count plus 1, done. Echo, this is the end of the loop. Func1, echo, now this is the end of the script. Each time you reference the func1 function name, the bash shell returns to the func1 function definition and executes any commands you define there. The function definition doesn't have to be the first thing in your shell script, but be careful. If you attempt to use a function before it's defined, you'll get an error message. The first function, func1, was defined after a couple of statements in the script, which is perfectly fine. When the func1 function was used in the script, the shell knew where to find it. However, the script attempted to use the func2 function before it was defined. Because the func2 function wasn't defined, when the script reached the place where we used it, it produced an error message. You also need to be careful about your function names. Remember, each function name must be unique or you'll have a problem. If you redefine a function, the new definition overrides the original function definition without producing any error messages. The original definition of the func1 function works fine, but after the second definition of the func1 function, any subsequent uses of the function utilize the second definition. Returning a value from a function. The bash shell treats functions like mini-scripts, complete with an exit status. There are 3 different ways you could generate an exit status for your functions. First, the default exit status. By default, the exit status of a function is the exit status returned by the last command in the function. After the function executes, you use the standard $? Variable to determine the exit status of the function. The exit status of the function is 1 because the last command in the function failed. However, you have no way of knowing whether or not any of the other commands in the function completed successfully. Look at this example. This time, because the function ended with an echo statement that completed successfully, the exit status of the function is 0, even though one of the commands in the function failed. Using the default exit status of a function can be dangerous practice. Fortunately, we have a couple of other solutions. Second, using the return command. The bash shell uses the return command to exit a function with a specific exit status. The return command allows you to specify a single integer value to define the function exit status, providing an easy way for you to programmatically set the exit status of your function. The DBL function doubles the integer value contained in the $value variable provided by the user input. It then returns the result using the return command, which the script displays using the $question variable. You must be careful, however, when using this technique to return a value from a function. Keep the following 2 tips in mind to avoid problems. Remember to retrieve the return value as soon as the function completes. Remember that an exit status must be in the range of 0 to 255. If you execute any other commands before retrieving the value of the function using the $question variable, the return value from the function is lost. Remember that the $question variable returns the exit status of the last executed command. The second problem defines a limitation for using this return value technique. Because an exit status must be less than 256, the result of your function must produce an integer value less than 256. Any value over that returns an error value. You cannot use this return value technique if you need to return either large integer values or string value. Instead, you need to use another method demonstrated in number 3, using function output. Just as you can capture the output of a command to a shell variable, you can also capture the output of a function to a shell variable. You can use this technique to retrieve any output from a function to assign to a variable. This command assigns the output of the DBL function to the result shell variable. Here is an example of using this method in a script. The new function now uses an echo statement to display the result of the calculation. The script just captures the output of the DBL function instead of looking at the exit status for the answer. There is a subtle trick that this example demonstrates. You'll notice that DB1 function really outputs 2 messages. The read command outputs a short message querying the user for the value. The bash shell script is smart enough to not consider this as part of the stdout output and ignores it. If you had used an echo statement to produce this query message to the user, it would have been captured by the shell variable as well as the output value. Note, using this technique, you can also return floating point and string values, making this an extremely versatile method for returning values from functions. Using variables in functions, you might have noticed in the test 5 example in the previous section that we use a variable called $value within the function to hold the value that it processed. When you use a variable in your functions, you need to be somewhat careful about how you define and handle them. This is a common cause of problems in shell script. This section goes over a few techniques for handling variables both inside and outside of your shell script functions. Passing parameters to a function. As mentioned earlier, in the returning a value from a function section, the bash shell treats functions just like mini-scripts. This means that you can pass parameters to a function just like a regular script. Functions can use the standard parameter environment variables to represent any parameters passed to the function on the command line. For example, the name of the function is defined in the $0 variable, and any parameters on the function command line are defined using the variables $1, $2, and so on. You can also use the special variable $hashtag to determine the number of parameters passed to the function. When specifying the function in your script, you must provide the parameters on the same command line as the function, like this: func1, $value1, space 10. The function can retrieve the parameter values using the parameter environment variables. Here's an example of using this method to pass values to a function. The addEm function in the text6 script first checks the number of parameters passed to it by the script. If there aren't any parameters, or if there are more than 2 parameters, addEm returns a value of -1. If there's just one parameter, addEm adds the parameter to itself for the result. If there are 2 parameters, addEm adds them together for the result. Because the function uses the special parameter environment variables for its own parameter values, it can directly access the script parameter values from the command line of the script. The following example fails. Even though the function uses the $1 and $2 variables, they aren't the same $1 and $2 variables available in the main part of the script. Instead, if you want to use those values in your function, you have to manually pass them when you call the function. When we pass the $1 and $2 variables to the function, they become available for the function to use, just like any other parameter. Handling variables in a function. One thing that causes problems for shell script programmers is the scope of a variable. The scope is where the variable is visible. Variables defined in functions can have different scope than regular variables. That is, they can be hidden from the rest of the script. Functions use 2 types of variables: global, local. The following section describe how to use both types of variables in your functions. Global variables. Global variables are variables that are valid anywhere within the shell script. If you define a global variable in the main section of a script, you can retrieve its value inside the function. Likewise, if you define a global variable inside the function, you can retrieve its value in the main section of the script. By default, any variables you define in the script are global variables. Variable defined outside the function can be accessed within the function just fine. The $value variable is defined outside the function and assign the value outside the function. When the DBL function is called, the variable and its value are still valid inside the function. When the variable is assigned a new value inside the function, that new value is still valid when the script references the variable. This practice can be dangerous, however, especially if you intend to use your functions in different shell scripts. It requires that you know exactly what variables are used in the function, including any variables used to calculate values not returned to the script. Here's an example of how things can go bad. Because the $temp variable was used in the function, its value is compromised in the script, producing a result that you may not have intended. There's an easy way to solve this problem in your functions, as shown in the next section. Local variables. Instead of using global variables in functions, any variables that the function uses internally can be declared as local variables. To do that, just use the local keyword in front of the variable declaration, local temp. You can also use the local keyword in an assignment statement while assigning a value to the variable. The local keyword ensures that the variable is limited to within the function. If a variable with the same name appears outside the function in the script, the shell keeps the two variable values separate. That means you can easily keep your function variables separate from your script variables and share only the ones you want to share. Now, when you use the temp variable within the func1 function, it doesn't affect the value assigned to the temp variable in the main script. Investigating array variables and functions. Chapter 5, Understanding the Shell, discuss an advanced way of allowing a single variable to hold multiple values by using arrays. Using array variable values with functions is a little tricky, and there are some special considerations. This section describes a technique that allows you to do that. Passing arrays to functions. The art of passing an array variable to a script function can be confusing. If you try to pass the array variable as a single parameter, it doesn't work. If you try using the array variable as a function parameter, the function only picks up the first value of the array variable. To solve this problem, you must disassemble the array variable into its individual values and use the values as function's parameters. Inside the function, you can reassemble all the parameters into a new array variable. Here's an example of doing this. The script uses myArray variable to hold all the individual array values to place them all on the command line for the function. The function then rebuilds the array variable from the command line parameters. Once inside the function, the array can be used just like any other array. The addArray function iterates through the array values, adding them together. You can put any number of values in the myArray array variable, and the addArray function adds them. Summary. In this chapter, we learned how to install and configure server operating systems, including steps like updating firmware, configuring the BIOS or UEFI, preparing the disk, and connecting the server to the network. You also learned about the various ways you can manage the server, both locally and across the network. Finally, we covered the basics of virtualization, including the relationship between the host and guest, the role of the hypervisor, the types of hypervisors, and how resources are shared by the VMs. Exam essentials: install and configure a server operating system, describe the steps in the process and identify which are required and which are optional. Understand the importance of creating a performance baseline. Identify the components of virtualization and describe their roles. These components include but are not limited to the host and guest, the management interface, and the hypervisor. You should also be able to describe how CPU, memory, and other resources are shared by the VMs. Web. To provide security to a web server, it can be configured to require and use HTTPS, which uses SSL to encrypt the connection with no effort on the part of the user, other than being aware that the URL must use HTTPS rather than HTTP. Disk subsystem. Disk latency is one of the major causes of slow web performance. The disk system should be as fast as possible. Using high-speed solid-state drives can be beneficial, and if possible, you should deploy either a RAID 0 or RAID 5 configuration, either of which will improve the read performance. If fault tolerance is also a consideration, then go with RAID 5 since RAID 0 will give you no fault tolerance. RAM. Memory is also critical to a web server. 80% of the web request will be for the same 20% of the content. Therefore, plenty of memory may ensure requested pages may still be contained in memory from which access is faster. You can help this situation by deploying web caching. This can be done on the proxy server if you use one. CPU is important but not a critical issue for a web server unless the server will be performing encryption and decryption. If that is the case, it may be advisable to use a network card with its own processor for this process. Application. In many cases, this server is the middle tier in a three-tier architecture that accepts users' requests to its application and then communicates with the database server where content is stored, as shown in figure 2.5. The presentation tier, the user interface of the application, the main function is to show something the user can understand and reply to user action. The logic tier, the layer process the business logic of the application, calculations, logical decisions, data processing. Data tier, this is the database where the information is stored. The information is passed back to the business logic on query. Messaging. Messaging servers run instant messaging software and allow users to collaborate in real time through either chat or video format. Here are some of the components that should be maximized. Memory. Users have varying habits when it comes to messaging. Some never use it and others use it constantly. So this is hard to predict and you may have to monitor the server usage and adjust memory accordingly. Disk. Include disk space for the operating system and the instance messaging software.
Writing scripts for graphical desktops, creating text menus, doing window, getting graphic. Over the years, shell scripts have acquired a reputation for being dull and boring. This doesn't have to be the case. However, if you plan on running on your scripts in a graphical environment, there are plenty of ways to interact with your script user that don't rely on the read and echo statements. This chapter dives into a few methods you can use to add life to your interactive scripts so that they don't look so old-fashioned. Creating text menus. The most common way to create an interactive shell script is to utilize a menu, offering your users a choice of various options, helps guide them through what the script can and can't do. Menu scripts usually clear the display area and then show a list of available options. The user can select an option by pressing an associated letter or number associated to each option. Figure 18.1 shows the layout of a sample menu. The core of a shell script menu is the case command. See Chapter 12 using structure commands. The case command performs specific commands depending on what character your user selects from the menu. The following sections walk you through the steps you should follow to create a menu-based shell script. Create the menu layout. The first step in creating a menu is, obviously, to determine what elements you want to appear in the menu and lay them out the way that you want them to appear. Figure 18.1, displaying a menu from a shell script. Before creating the menu, it's usually a good idea to clear the monitor display. Doing so enables you to display your menu in a clean environment without distracting text. The clear command uses the terminal settings information of your terminal session, see Chapter 2, Getting to the Shell, to clear any text that appears on the monitor. After the clear command, you can use the echo command to display your menu elements. By default, the echo command can display only printable text characters. When you're creating menu items, it's often helpful to use non-printable items such as the tab and new line characters. To include these characters in your echo command, you must use the -e option. Thus, the command echo -e code 1./t display disk space results in the output line 1 display disk space. This greatly helps in formatting the layout of the menu items. With just a few echo commands, you can create a reasonable looking menu. The -en option on the last line displays the line without adding the new line character at the end. This gives the menu a more professional look because the cursor stays at the end of the line waiting for the user's input. The last part of creating the menu is to retrieve the input from the user. This is done using the read command, see Chapter 14, Handling User Input. Because we expect only single character input, the nice thing to do is to use the -n option in the read command to retrieve only one character. Doing so allows the user to enter a number without having to press the enter key. Read -n1 option. Next, you need to create your menu functions. Create the menu functions. Shell script menu options are easier to create as a group of separate functions. This approach enables you to create a simple, concise case command that is easy to follow. To do that, you must create separate shell functions for each of your menu options. The first step in creating a menu shell script is to determine what functions you want your script to perform and lay them out as separate functions in your code. It is common practice to create stub functions for functions that aren't implemented yet. A stub function is a function that doesn't contain any commands yet, or possibly just an echo statement indicating what should be there eventually. The stub function enables your menu to operate smoothly while you work on the individual functions. You don't have to code all the functions for your menu to work. You'll notice that the functions starts out with a clear command. This enables you to start the function on a clean monitor screen without the menu showing. One thing that helps out in the shell script menu is to create the menu layout itself as a function. This strategy enables you to easily redisplay the menu at any time just by calling the menu function. Add the menu logic. Now that you have your menu layout and your functions, you just need to create the programming logic to put the two together. As mentioned earlier, this requires the case command. The case command should call the appropriate function according to the character selection expected from the menu. It's always a good idea to use the default case command character, the asterisk, to catch any incorrect menu entries. The following code illustrates the use of the case command in a typical menu. This code first uses the menu function to clear the monitor screen and display the menu. The read command in the menu function pauses until the user presses a character on the keyboard. After that's been done, the case command takes over. The case command calls the appropriate function based on the return character. After the function completes, the case command exits. Putting it all together, now that you've seen all the parts that make up a shell script menu, let's put them together and see how they all interoperate. Here's an example of a full menu script. This menu creates three functions to retrieve administrative information about the Linux system using common commands. It uses a while loop to continually loop through the menu until the user selects option 0, which uses the break command to break out the while loop. You can use this template to create any shell script menu interface. It provides a simple way to interact with your users. Using the select command, you may have noticed that half the challenge of creating a text menu is just creating the menu layout and retrieving the answer that you enter. The bash shell provides a handy little utility for you that does all this work automatically. The select command allows you to create a menu from a single command line and then retrieve the entered answer and automatically process it. The format of the select command is as follows. The list parameter select variable in list, enter do, enter space commands, done, enter done. The list parameter is a space separated list of text items that build the menu. The select command displays each item in the list as a numbered option and then displays a special prompt defined by the PS3 environment variable for the selection. Here is a simple example of the select command in action. The select statement must all be on one line in the code file. That's indicated by the continuation character in the listing. When you run the program, it automatically produces the following menu. When you use the select command, remember that the result value stored in the variable is the entire text string and not the number associated with the menu item. The text string values are what you need to compare in your case statements. Doing Windows, using text menus is a step in the right direction, but there's still so much missing in our interactive scripts, especially if you try to compare them to the graphical Windows world. Fortunately, for us, some resourceful people out in the open source world have helped us out. Dialog Package is a nifty little tool originally created by Savio Lum and currently maintained by Thomas E. Dickey. This package recreates standard window dialogues in a text environment using ANSI escape control codes. You can easily incorporate these dialogues in your shell scripts to interact with your script users. This section describes the dialog package and demonstrates how to use it in shell scripts. This package recreates standard Windows dialog logs in a text environment using ANSI escape control codes. You can easily incorporate these dialogues in your shell scripts to interact with your script users. This section describes the dialog package and demonstrates how to use it in shell scripts. Note: the dialog package isn't installed in all Linux distributions by default. If it's not installed by default, because of its popularity, it's almost always included in the software repository. Check your specific Linux distribution documentation for how to load the dialog package. For the Ubuntu Linux distribution, the following is the command to install it: sudo space apt-get space install space dialog. The dialog package. The dialog command uses command line parameters to determine what type of Windows widget to produce. A widget is the dialog package term for a type of Windows element. The dialog package currently supports the type of widgets shown in Table 18.1. Widget, calendar, description, provides a calendar from which to select a date. Widget, checklist, displays multiple entries where each entry can be turned on or off. Widget, form, allows you to build a form with labels and text fields to be filled out. Widget fselect description provides a file selection window to browse for a file. Widget gauge description displays a meter showing percentage of completion. Widget infobox display a message without waiting for a response. Widget input box description display a single text from box for text entry. Widget input menu description provides an editable menu. Widget menu description displays a list of selections from which to choose. Widget MSG box description displays a message and requires the user to click an OK button. As you can see from table 18.1, you can choose from lots of different widgets to give your scripts a professional look with little effort. To specify widget on the command line, use the double dash format, dialog space double dash widget space parameters, where widget is the widget name as seen in table 18.1 and parameters defines the size of the widget window and any text required for the widget. Each dialog widget provides output in two forms, using stderr, using the exit code status. The exit code status of the dialog command determines the button selected by the user. If an OK or Yes button is selected, the dialog command returns a 0 exit status. If a Cancel or No button is selected, the dialog command returns a 1 exit status. You can use the standard $? Variable to determine which button was clicked in the dialog widget. If a widget returns any data, such as menu selection, the dialog command sends the data to stderr. You can use the standard bash shell technique of redirecting the stderr output to another file or file descriptor. Dialog space double dash input box space quote enter your age colon quote space 10 space 20 space 2 redirected or greater than to h.text. This command redirects the text entered in the text box to the h.text file. The following sections look at some examples of the more common dialog widgets you'll use in your shell scripts. The text parameter is any string you want to place in the window. The dialog command automatically wraps the text to fit the size of the window you create. Using the height and width parameters, if you want to place a title at the top of the window, you can also use the double dash title parameter along with the text of the file of the title. Here's an example of using the MSG box widget, $space dialog space double dash title space testing space double dash MSG box space quote this is a test space 10 space 20. After you enter this command, the message box appears on the screen of the terminal emulator session you're using. Figure 18.2 shows what this looks like. If your terminal emulator supports the mouse, you can click the OK button to close the dialog. You can also use keyboard commands to simulate a click. Just press the Enter key. The Yes/No widget. The Yes/No widget takes the MSG box widget one step further, allowing the user to answer a yes or no question displayed in the window. It produces two buttons at the bottom of the window, one for yes and another for no. The user can switch between buttons by using the mouse, the tab key, or the keyboard arrow keys. To select the button, the user can press either the space bar or the enter key. Here's an example of using the yes/no widget. Dialog space double dash title space quote please answer space double dash yes no space quote is this thing on space 10 space 20. Enter. Echo space $sign question mark. This code produces the widgets shown in figure 18.3. The exit status of the dialog command is set depending on which button the user selects. If the button is clicked, the exit status is 1, and if the yes button is clicked, the exit status is 0. The input box widget. The input box widget provides a simple text box area for the user to enter a text string. The dialog command sends the value of the text string to stderr. You must redirect that to retrieve the answer. Figure 18.4 shows what the input box widget looks like. As you can see, the input box provides two buttons, OK and Cancel. If the Cancel button is clicked, the exit status of the command is 1. Otherwise, the exit status is 0. You'll notice that when you use the cat command to display the contents of the text file, there's no new line character after the value. This way, you can easily redirect the file contents to a variable in a shell script to extract the string entered by the user. The text box widget. The text box widget is a great way to display lots of information in a window. It produces a scrollable window containing the text from a file specified in the parameters. $sign dialog space double dash text box space /etc/pass wd space 15 space 45. The contents of the /etc/pass wd file are shown within the scrollable text window as illustrated in figure 18.5. You can use the arrow keys to scroll left and right as well as up and down in the text file. The bottom line in the window shows the location percentage within the file that you're viewing. The text box widget contains only a single exit button, which should be selected to exit the widget. The menu widget. The menu widget allows you to create a window version of the text menu we created earlier in this chapter. You simply provide a selection tag and the text for each item. The first parameter defines a title for the menu. The next two parameters define the height and width of the menu window, and the third parameter defines the number of menu items that appear in the window at one time. If there are more menu items, you can scroll through them using the arrow keys. Following those parameters, you must add menu item pairs. The first element is the tag used to select the menu item. Each tag should be unique for each menu item and can be selected by pressing the appropriate key on the keyboard. The second element is the text used in the menu. Figure 18.6 demonstrates the menu produced by the sample command.
Managing web servers. The most popular use of Linux in the server environment is as a web server. Linux web servers dominate the internet and are also popular for hosting internal corporate intranet applications. Everything from serving static web pages to hosting dynamic web application often runs faster and more efficiently on a Linux server platform. In this chapter, you'll learn how to determine the right web server for your environment, install and configure the APIC web server, install and configure the Nginx web server. Linux web servers. There are lots of different types of web server software packages available for the Linux platform. However, two have risen to the top and are most commonly used in the Linux environment: APIC, Minx. This section describes some background on each server and how to use them in your network environment. APIC. By far the most used web server on the internet is the APIC web server application. It is an open source project maintained by the APIC Software Foundation. Since it's all open source, it is available free of charge for any purpose, both commercial and private, and now is commonly included in most Linux distribution repositories, making it easy to install. Over the years, the APIC Web Server project has pioneered many new features that define just what web servers should support. Loadable dynamic modules, the ability to activate and deactivate features on the fly as the web server is running. Scalable multi-session support, the ability to easily handle multiple client requests at the same time is crucial for modern web servers. Limiting concurrent connections. While multi-user support is crucial, so is the ability to limit the number of clients that can connect at the same time to help prevent system overload. Bandwidth throttling. The ability to regulate the output from the web server to prevent overloading the network, even if the system can handle more connections. Web caching, also called web proxy, the ability to store web pages requested by multiple clients and reading additional requests from the cache rather than from the original data source. Load balancing, also called reverse proxy, the ability to act as a single point of connection for clients and then redirect requests to multiple backend servers for processing. Common Gateway Interface, or CGI, the ability to forward web page content to internal server programs, commonly used for processing embedded scripting code. Virtual hosting, the ability to host multiple domains on a single web server. User-based web page hosting, the ability to allow individual users on the system to host their own web pages. With APIC, all of these features, plus a lot more, are easily enabled or disabled using simple text-based configuration files. APIC server versions. One confusing issue with the APIC web server is that there are currently two separate versions supported. The 1.3x version thread supports older installations of the APIC web server. It's mostly maintained to support bug fixes and security patches for legacy systems. New APIC web server installations should use the 2x version thread. Most Linux distributions differentiate the two versions by calling the 2x version by the name APIC 2. Minx. While it too can operate as a standard web server, the Minx, pronounced Nginx web server, is better known as a reverse proxy server. As you can probably guess, a reverse proxy server does the opposite of what a proxy server does. Instead of processing requests from multiple clients to a single web server, a reverse proxy server processes requests from a single client to multiple servers. This technique is also known as load balancing. A load balancing server receives HTTP requests from clients and sends them to a specific server in a pool of common web servers for processing. Each web server in the pool contains the same data and can process the same HTTP requests. The load balancing process helps distribute the client load on multiple web servers in a high traffic environment, helping prevent overloading and slow performance. The remainder of this chapter walks through how to install and set up each of these web servers in your Linux environment. The APIC web server. With the overall popularity of the APIC web server, Most Linux distributions have installed packages that make setting up basic APIC web servers easy. The difficult part comes if you need to customize special features. This section walks through both the installation of a basic web server setup and how to dig into the APIC configuration files to help customize your web environment. Installing an APIC web server. As mentioned, most Linux server distributions include the APIC web server software as easy to install software packages. For example, in the Ubuntu Linux server distribution, the APIC web server package is called APIC 2. You install the basic APIC server using a single package, sudo apt-get install APIC 2. This installs the latest version of the APIC 2 web server, supported by the Ubuntu server version. Once you install the APIC web server, the installation package automatically configures the server to start at boot time and serve data files from the /var /www/html directory on the server. After the APIC server is running, you can open a browser and connect to your Linux server. Figure 20 shows the default index.html file that is created for Ubuntu servers. The default APIC web page for Ubuntu. For Red Hat-based Linux servers, the APIC package is called HTTPD. This is because the name of the APIC server program is HTTPD. You can use the standard DNF package installer to install it. #DNF /install /HTTPD. While not specified in the file name, this is the APIC 2.x version of the server. Unlike the Ubuntu Linux distribution, the Red Hat package doesn't automatically start the APIC web server, nor does it start it at boot time. To do that, you'll need to use the systemctl command. systemctl /start /httpd, systemctl enable /httpd. Since Red Hat servers have firewall protection enabled by default, you'll also need to allow HTTP connections through the firewall. Firewall-cmd /zone equal public /add-service equal http /permanent. The Red Hat-based distributions also serve data files from the /var /www/html directory by default. Figure 20.2 shows the default index.html file that is created for CentOS. The default APIC web page for CentOS. You can start, stop, restart, and check the status of the APIC program using the APIC2CTL utility. Some Red Hat-based distributions such as CentOS use APIC-CTL even for the 2.x versions. Table 20.1 shows the commands you can use with APIC2CTL. The status and full status commands are a handy way to check on the APIC web server. However, they display the APIC status as a web page, which requires a text-based command line browser. Most Linux distributions don't install a command line browser by default. The Lynx command line browser is the most popular and it's available in most Linux distributions repositories. The APIC2CTL utility commands. Command, first column. Description, second column. Start, starts the APIC web server. Stop, stops the APIC server, terminating any active connections. Restart, sends a SIOP signal to the APIC server to restart it, closing any existing connections. Full status, displays a full status report from the APIC server. Status, displays a short status report from the APIC server. Graceful restarts the APIC server, but existing connections are not terminated. Graceful stops the APIC server, but existing connections are not terminated. Config test parses the configuration files and reports any syntax errors. Help displays the list of commands. Advanced features. The core APIC software package for both Ubuntu and Red Hat installs a basic web server without many additional features. To customize the web server to support advanced features such as server-side programming, you'll have to install additional software packages. Unfortunately, different Linux distributions bundle different APIC features into different software packages. Consult your specific Linux distribution documentation to determine which packages you need to install to support the APIC features you want to use. Configuring the APIC server. A great feature of the APIC web server is that it uses simple text-based configuration files to manage the behavior of the server. The configuration file controls every feature of the server, giving you complete control over just how the APIC web servers operates. Unfortunately, there isn't a standard location or file name for the APIC configuration file. The main locations and files that you'll need to remember are as follows: /etc/apic/apic.conf.conf, APIC 1.3x installation for Ubuntu servers, /etc/apic2/apic2.conf, APIC 2 installation for Ubuntu servers. Multiple configuration files. Another confusing issue that you'll most likely run into is that not all of the APIC configuration settings are necessarily stored in one configuration file. Often, Linux distributions move configuration settings for separate features into their own configuration files, and they use the include directive in the main configuration file to include them in the configuration. You will need to consult the documentation for your specific Linux distribution to find out how the APIC configuration files are arranged. The following sections walk through some of the different configuration settings that you'll run into in standard APIC configurations. Basic setup. When you look inside an APIC configuration file, the first thing you'll see are lots of lines that start with a pound sign. The pound sign denotes a comment line, allowing you to embed comments within the configuration file. You define actual configuration settings using a directive keyword and then optionally a value for the setting, such as the following: document without space root, quote /var/www/html, quote. This directive sets the default directory for the APIC server to the /var/www/html directory on the Linux server. As you peruse through the configuration file, you'll see lots of directives setting basic features for the server. Table 20.2 show the main settings that you'll be interested in. By default, settings that you define in the main configuration area are called global settings. They apply to the main APIC web server when it starts. You can also define conditional settings that apply only when specific conditions are met, such as if an environment variable is defined. You define conditional settings as a block of directives, the block using the following format: if without space define variable, the directives specified in this block apply only when clients attempts to access files stored in that directory. APIC logs. The APIC web server creates two types of log files by default. As you can probably guess, the error log keeps track of any error that occur while the APIC web server is running. The location of the error log is defined using the error document directive in the configuration file. Usually, the error log is located in the /var /log/apic2 /error.log file in Ubuntu servers, and in the /var/httpd/error-log file in Red Hat servers. Note the underscore instead of the period in the file name. You can customize the format for entries in the error log using the log format directive in the configuration file. By default, error log entries look like this: #cut #error _log. The access log not only documents the file request, but can also document the browser type of the client, the OS of the client, and the IP address. You can customize the output using the log format directive as well. User web hosting. The default configuration for most Linux distribution APIC servers is to provide one location for hosting files, called the document root. The document root directive defines this location, and for both Ubuntu and Red Hat servers, it is set to the /var/www/html directory by default. Any files or directories that you want to make available to web clients are normally placed under that directory structure. The APIC web server also provides a feature that allows each individual user on the Linux system to host their own files. To enable this feature, add the user without space dir directive to the global configuration settings. The user dir directive specifies the name of the directory in each user's home directory where they can host files. The most common setting is as follows: user dir space public_HTML. To access files in the user's public.html directory, you must specify the username in the URL. For example, to access the file /home/reach_public_html/test.html, you'd use the URL http://localhost/enye/reach/test.html. Web directory permissions. To allow access to files in your public_HTML directory, you must grant read and executive privileges to the user or group account that runs the APIC web server. Not only will that user or group need read and execute privileges to the public_HTML directory, but also to the user's home directory. This can make things somewhat complicated for protecting other files in the user's home directory. Virtual web hosting. The basic configuration for an APIC web server assumes the host is serving files for a single server, namely the server name or IP address that APIC software is running on. However, APIC also allows you to host web pages for multiple domain names or IP addresses on a single physical server. This is ideal for businesses that support multiple customers, such as internet service providers. The ability to host multiple web environments on a single physical server is called the virtual web hosting. There are two ways to implement virtual web hosting in APIC: name-based virtual hosting, IP-based virtual hosting. With name-based virtual hosting, the physical server has multiple host names that point to its IP address in the DNS system. You then must configure the APIC web server to use separate directories based on the host name the client uses in the URL request to connect. You do that using the name virtual host directive and separate virtual host blocks, one for each virtual host. name with no space virtual with no space host space 192.168.1.77. The name without space virtual without space host directive defines the IP address that the server listens on. Then you must create a separate less than virtual without space host greater than block to define the IP address, and use the server without name directive to define the host name that the client uses in the request. Each separate hostname points to a different document without space root area by specifying separate document without space root directives. With space IP-based virtual hosting, the server must listen for incoming requests on multiple IP addresses. Each IP address is assigned a different hostname in the DNS system. With IP-based virtual hosting, you must define multiple IP addresses on the server either by having separate physical network cards in the server or by defining multiple IP addresses for the same network interface using the if without space config network command. After you configure your Linux server to support multiple IP addresses, you must configure the APIC web server to listen to each IP address using multiple listen directives. After that, just define separate less than virtual without space host greater than blocks to define the host name and document without space root area for each IP address. One advantage to IP-based virtual hosting is that you can have two separate APIC programs running at the same time, each one listening on a different IP address. Each APIC program can have a separate configuration, making it easier to separate out settings for each server. Access restriction. While the original intention of web servers was to provide easy access to public data, there are times when it would be handy to provide restricted access to data, such as an internal corporate intranet application. The APIC web server provides a few different methods for implementing authentication, forcing clients to log in before granting access to documents based on the provided authentication. APIC provides authentication features using separate loadable modules. Originally, the APIC web server accomplished that with the mod_auth module, which provided authentication using a text-based file that lists users' accounts and encrypted password. However, that module has been replaced as of APIC 2.1 with other more advanced modules. The more common authentication modules in newer versions of APIC are the following: mod_auth n_file uses a text-based file to list user accounts and encrypted passwords for access. The direct replacement for mod_auth. Mod_auth n_anon uses a list of usernames but no passwords to restrict access. The mod_auth method, now called mod_auth n_file, uses a text-based user file that's created using the htpasswd utility in APIC. To add a new user account to the authentication user file, specify the file using the -c option and then specify the user account to add, like this. Once you create the user file, you must reference it in the APIC configuration file to use for authentication. There are two approaches to doing that. One method is to add the authentication configuration settings in the less than directory greater than section for the block you need to protect in the main APIC configuration file. There are a few different directives needed to tell APIC about the authentication protection. The auth name directive provides the title of the login dialog box that appears when it asks for the user ID and password. The auth user file directive points to the password file created using the htpasswd utility. Managing database servers. Data is as important as talent, strategy, and sales, and is often central to a business success. In fact, data is typically considered a company's most important asset. We are now in a data-driven society, and the sheer volume of useful data is growing astronomically. Protecting and managing this data provides your organization with a base for data analysis that can lead to a competitive advantage, or just plain survival. While you may not be involved in the data analytics side of your company as a system administrator, you are on the data management side. Whatever data your establishment decides to keep and scrutinize, it is up to you to make sure your fellow employees have fast and appropriate access to it through your administration of the database servers. In this chapter, you will learn to understand basic DBMS components, create user accounts within MariaDB, use SQL to query a MariaDB database, install PostgreSQL on Linux, set up roles within PostgreSQL. Linux database servers. We've looked at a lot of text files so far in this book, and they are useful for many different purposes, such as storing configuration information, boot messages, bash scripts, and so on. However, when you have complex data that needs to be stored, processed, and analyzed, simple text files don't work well. Text files are often referred to as flat files because only basic relationships can exist between the data they contain. Databases were created to fill the need for complex connections between individual data items. While data is the focus, there are other pieces that make up a database management system. A DBMS typically consists of the following parts: database data files, query language interface, database engine. Organizing the data. Back in the 1970s, a database management system architecture called a relational DBMS was first conceived. This still popular model organizes data into three levels. Database. A database is the largest of the three levels, and it is used to group together related data. While you can have a large single database on a system, it's typical to create a database for every application on a server that needs one. Each database is required to have its own unique name, so it's wise to name the database in a way that relates to the application. Table. There are typically multiple tables per database. This mid-level organization further refines the data's groupings. For example, if the database contains tree information for a site that sells live fruit trees through a website, one table in the database might be specifically for apple trees, another table for cherry trees, another table for pear trees, and a fourth table for orange trees. Grouping data in a database into tables is called data normalization. Field. The finest level of detail for data in a database is the field. Using the apple tree table in our tree database as an example, the fields for a single apple tree may be item, number, apple tree type, description, tree size, apple color, blooming period, pollinator group, harvest period, and growth zones. In the apple tree table, each apple tree sold by the company would have its own record. A table record is a collection of fields about the same item. So in our apple tree table, each type of apple tree sold would have its own record, identified by the item number. This item number is a primary key.
Primary keys are used to uniquely identify each record within a table. It's helpful to see a pictorial view of a database table. Sticking with our fruit trees for sale application, a representation of database apple tree table is shown snipped in figure 21.1.
Media installation type. You have some choices when it comes to the media you use to deliver the installation files or the image, although in most cases this choice will be dictated by the scenario. In this section, you'll learn about media options, network. A network installation is handy when you have many installations to do, and installation by CD is too much work. In a network installation, the installation CD is copied to a shared location on the network, then individual workstations boot and access the network share. The workstations can boot either through a boot disk or through a built-in network boot device known as PXE-ROM. Boot ROMs essentially download a small file that contains an OS and network drivers and has enough information to boot the computer in a limited fashion. At the least, it can boot the computer so that it can access the network share and begin the installation. Optical. This means the files are located on a CD or DVD with the size of these files, typically a DVD. This means performing the installation involves booting the target system to the DVD that will invoke the installation process. Universal Serial Bus. Most systems will allow you to boot from a USB device, but you must often change the BIOS or UEFI settings to look for USB first. Using a large USB drive, you can store all the necessary installation files on the one device. Embedded. A Windows embedded OS brings the same kinds of interface design and functionality to a handheld device. Installing the system is done using an image. Imaging. One way in which operating systems can be deployed quickly and with consistency is to create images of completed installations and use disk imaging software to copy the image to a drive. Not only does this speed the deployment process, but the image can be pre-configured according to the company policy with regard to the role the server will play. Cloning. Cloning is the process of making a copy of an existing operating system installation and copying it to another system. This can take several forms. In this section, you'll learn more about cloning. Virtual machine cloning. Another of the advantages of a virtualized environment is the ability to maintain an inventory of images for quick use. You can even maintain multiple instances of a VM, all clones of one another, for fault tolerance or in scenarios where high availability is a requirement. Physical clones. When you make a copy of an existing physical server, it is called a physical clone. This copy can be used to deploy another physical server or to create a VM. Typically, when an organization decides to create a virtual network, they start by cloning the physical servers and using the clone files to create VMs. Template dock deployment. A clone is an exact image of a system. VM clones are not suited for mass deployment or of virtual machines. A template is a more generalized image that is intended for multiple uses. Template acts as a baseline image for a VM. Physical to virtual. Partition and volume types. During the installation, you will be required to create a partition or volume to hold the installation if it doesn't already exist. Templates acts as a baseline image for a VM with the predefined configurations as per your organization's TOO specifications for managing partitions and or volumes, and additional issues surrounding setting up the partition or volume. Global partition table versus master boot record. Dynamic disk. Partitions can be made dynamic, which as the name implies means they can be configured and reconfigured on the fly. Logical volume management. Logical volume management is the use of drive management tools that allow you to create volume structures that are independent of the physical storage devices. File system types. Configuring and maintaining server functions and features.
Po ito yung SSD na sabi niyo makabit yung SSD NVMe na malagyan yung may ganong port.
Oh, nasa akin yung yung NVMe. Pero yung hard drive, iniwan.
Yung NVMe na dati wala yun hard drive lang po.
Oo nga, hard drive lang yung iniwan ko sa inyo. Kasi kailangan ko ang kailangan ko kasi nun is makita yung, kasi yung NVMe ko na SSD, tsaka yung hard drive, same lang ng ng storage. So, kung kaya ko,
may nakasulat yun na na ballpen lang nakalagay Garrett.
wala.
Oo. Nilagyan kasi namin ng pangalan yun sir.
Wala. Kasi, tsaka imposible.
Kailangan niyo ba yung files niyo sir or ano pa?
Oo, kailangan ko yung files ko eh.
Hindi na, wala na kasi dito sir. Yun yung sir, alam ko kasi dalawang port yung marami na lang ang iniwan dito sir. Yun kasi yung itatry namin sir eh.
Imposible kasi yung RAM lang eh. Kasi iniwan ko yung storage na yun para ma-replicate yung setup na yung storage saka yung dalawang RAM. Kasi kung yung dalawang RAM lang na yun, edi sana chinek nyo na lang dun sa Kasi DDR4 lang naman yun eh.
Opo sir, yun nga sir. Kasi yung compatibility kasi ng RAM ang inaano po natin doon. Yung compatibility ng RAM ang inaano natin sa... Kasi yung hard drive sir, wala namang problema kasi pero naman talaga lahat naman may slot for hard drive. Ang inaano natin nun dati yung sa RAM, kung compatible yung 16 gig yung dalawa. Tapos sabi niya sir, kung mayroong slot for SDM.
Hindi, kung compatible, makikita yun sa specs eh. So, kumbaga, pwedeng i-check siya sa, di ba, sa website.
So, hindi na namin kasi yun, alam ko kasi pinadala na namin sa iyo kasi wala namang problema sa amin sa hard drive kasi pwede naman kami mag-format ng hard drive namin po. Maglagay kami ng hard drive namin na.
Wala eh. Wala. Chinek ko dun sa hindi ko
Wala, stick pa kami naghahanap eh. Hindi pwede mawala yun eh kasi may iniwan na hard drive. May mga pangalan sa kagasya. Nalala ko kasi nung nagpunta kayo, nung binuksan ko yung laptop niya, wala nga doon yung hard drive. Tapos umakit ako sa taas, nakita ko yung hard drive niya, may nakasulat ng Garrett, naka-ballpen lang po yun. Nakasulat.
Kasi
kung hard drive lang kailangan nyo, pwede naman namin kayo bigyan ng hard drive sir eh. Nga lang, kung may files, yun ang problema.
Sige, ang alam ko.
Kung kailangan niyo po ng yung hard drive, mabibigyan namin kayo sir, yung files na hindi namin maibaba.
Sige. I-check ko kasi alam ko meron kayong meron akong, kailangan ko yung files eh kasi nandoon yung yung meron akong record, basta meron akong dun sa work dun about so sige, check ko yung record kasi alam ko ni-record ko yung conversation natin nung time na yun eh. To-check ko ulit, i-check ko.
Sige sir, check na lang sir kung
Sige.
I-check na rin po namin sir.
Sige.
Opo, sige sir. Pero magta-try pa rin kami maghanap dito sir. Nalungkot na nga namin dito lahat pero subukan pa rin namin sir mag-try ulit.
Sige. Pahanap ako kasi para imposible yun eh na yun nga na parang dalawang RAM lang, 'di ba? Yung tas yung walang storage. So yun. Sige, pahanap na lang po.
Sige sir.
Sige. Salamat.
Thank you po.
Basic web page authentication. The other method to provide basic authentication is to use a special file name called the HT access in the directory you need to protect. The .htaccess file contains the same authentication directives that we used in the main configuration file. To tell APIC to use the .htaccess file, the less than directory greater than block must contain the allow without space override directive. Using the .htaccess file decentralize the authentication configurations instead of placing them all in the main configuration file. There's also an auth without space group without space file directive that allows you to bundle user accounts into groups. You can then grant the entire group access to specific areas on the web server. The mod_access authentication method is another popular way to restrict access to web pages. Instead of using a user ID or password challenge, it allows you to restrict pages based on the IP address of the clients. It uses simple deny and allow directives to list individual IP addresses or network addresses to deny or allow access. Here's an example of using that method. The order directive determines which rule set is checked first. In this example, we set it to deny or block all clients but only allow clients that are on the 192.168.1.0 subnet. Hosting dynamic web applications. In the old days, all content provided in web pages was static. To update the information on your website, you had to manually open the appropriate HTML file, enter the changes to the content, and then save the new version. In this day of constantly changing content, creating a secure web server. Protecting data transmitted across the internet has become a high priority for most corporations. These days, it's recommended to use the secure version of HTTP or HTTPS for all web transactions. The APIC web server supports HTTPS sessions, but it requires quite a bit of work. You must have a privileged private or public key pair to use for the encryption, plus have a signed certificate to validate your public key to clients. Creating an HTTPS server with APIC involves 6 steps. 1. Install the APIC SSL module. 2. Create a public or private key pair. 3. Create a certificate signing request. 4. Have the CSR signed by a trusted certificate authority to create certificate. 5. Install the certification and key files in your APIC setup. 6. Configure APIC to use certificate. The bottom line: determine the right web server for your environment. Web servers are the heart of the internet, and Linux is the main server platform used for supporting them. There are many different web server software packages available for Linux, but the two most popular are APIC and Minx. The APIC web server is the oldest and most popular web server package. It is highly customizable and has defined many of the features expected from web servers. The Minx web server is relatively new to the web server game but is a powerful player. It can support larger client bases on the same physical hardware than APIC, making it ideal for high-traffic environments. It also has made a name for itself in the reverse web proxy world. A reverse web proxy sits in front of multiple backend application servers and provides load balancing for clients. Master it. Your company wants to implement load balancing using the several web servers to host your corporate website. The website uses PHP to retrieve data stored in a database, to produce the website content. Describe a good web server solution to meet these requirements. Install and configure the Epic Web Server. The Epic Web Server is available for installation from the standard Ubuntu and Red Hat repositories. Adding features to the Epic Web Server often requires installing additional packages. Customizing the Epic Web Server is as easy as changing configuration settings. You use the user without space dir directive to allow users to create their own websites on the server, separate from each other. You use the virtual without space host directives to host web pages for multiple domains on the same physical server. You can also implement client authentication on your website, requiring clients to log in to access content. The Epic server also provides for secure transactions by using HTTPS and encrypting network traffic between the client and the server. Master it. You've received a frantic phone call from the company web administrator informing you that after changing the configuration file, she can't start the Epic Web Server. It keeps failing. What command should you use to see why the Epic server won't start? Install and configure the Nginx Web Server. With the growing popularity of the Nginx Web Server, both the Ubuntu and Red Hat server repositories include it. After installing Nginx, you can customize it by changing the nginx.conf configuration file. Many of the configuration directives for the Nginx are similar to the Epic, so migrating from one to the other is fairly simple process. Master it. Customers are complaining that they can't connect to your corporate website running on the Nginx server. What commands can you use to check the status of the server and restart it if necessary? In the representation, each row is a record in the table, which is why sometimes database table records are called rows. Each column with the apple tree table is a field, which are why fields are sometimes called columns. Notice that some fields for the records contain the same data, while others do not. For example, item numbers 3247 and 3248 share all the same data in their record fields, except for the primary key, item number, and 3 without space size. One record has standard STD in that field, and one contains dwarf. A record in a table is a single occurrence of all the values in the record's data fields. Field can be different type of data. Table 21.1 shows these standard database data types for an RDBMS. RDBMS data types. Data type on first column, description on second column. Bool, Boolean value representing either true or false. Char, character string of a fixed n characters in length. Date, date expressed in quadruple Y dash double M dash double D format. Date time, date and time expressed in quadruple Y dash double M dash double D double space double H space colon space double M space colon space SS format. These data types are slightly different depending on which RDBMS you use. Also, they may add a few additional types of data. Querying the data. Created in the 1970s, structured query language was declared a standard by the American National Standards Institute in the mid-1980s. Pronounced SQL. This language is still used to communicate with databases using an RDBMS, and the standard has continued to evolve, making it stronger and more flexible. What's exciting about SQL is that when you learn the language syntax, you can use it on nearly all relational databases with few modifications. So, when you have a Linux RDBMS installed in your system, you'll have place to learn and practice using SQL. SQL consists of specific instruction commands that are crafted into statements to interface with the database. SQL commands are typically grouped into 4 different categories, though some special SQL commands fall outside of these categorizations. Data Definition Language, or DDL, Data Manipulation Language, or DML, Transaction Control Language, or TCL, Data Control Language, or DCL. We'll only be using a few basic commands in this chapter that fall into the DDL and DML categories, as well as a few that don't fall into any of these groupings. Table 21.2, a few basic SQL commands. Column 1, command, category, column 2, third column, description. First command, create, category, DDL, description, creates a table, database or user account. Second command, describe. Second category, not applicable. Second description, list a table's field definitions. First command, drop. Second category, DTL. Third category, DDL. Third description, deletes a table, a database, or a user account. Fourth command, grant. Fourth category, DTL. Fourth description, grants access to the selected item for the designated user account. Notice that the commands are in uppercase. This is typical of most SQL commands. Be aware that with some RDBMS, you can use either lowercase or uppercase, but good form dictates using only uppercase for SQL commands. Controlling the data. Access to the data that resides in the database is managed by the database engine. When an application wants to view or modify data, it has to go through the database engine to do so, as portrayed in figure 21.2. The database engine in some DBMS continue to run in the background as a daemon on Linux. Daemons, covered in Chapter 10, Booting Linux, are programs that continue to run in the background, offering a specific service. In the case of a DBMS, that service is access to data managed by the database engine. One nice aspect about this structure is that the application doesn't have to reside on the same computer system as the database engine. Various instances of the app could run on different systems, sending requests to database engine on the primary database server, similar to what is shown in figure 21.3. The Linux RDBMS we're going to focus on in this chapter include MySQL, MariaDB, and PostgreSQL. They each are relational and use SQL interface. Installing and using MySQL or MariaDB. Released in 1996, MySQL is one of the more popular RDBMS used for web servers on Linux. The LAMP, Linux System, Epic Web Server, MySQL Database Server, and PHP Programming Language platform can be found in Linux servers around the world still today. MySQL was revolutionary at the time of its release because it used indexing data to speed up data queries. The MySQL developers didn't start out trying to compete with commercial databases. Instead, They just want to create a simple but fast database system. So the fancy RDBMS features were left out, and speed was the focus. Because of this development emphasis, MySQL quickly became the standard RDBMS used in many high-profile internet web applications. Over time, while continuing to maintain the emphasis on speedy data queries, additional RDBMS features were added, which strengthened MySQL's popularity. MySQL can run on many different platforms besides Linux, can scale its processing into multiple CPUs, provide security at the user and host levels, support many different human languages, and so on. Understanding the difference between MySQL and MariaDB, you can think of MariaDB and MySQL as identical twins, but their developers may disagree with that statement. A more accurate claim concerning these two database systems is that MariaDB maintains nearly 100% compatibility with MySQL, so the code that you wrote for a MySQL database system should work perfectly to interact with the MariaDB server. In 2010, Oracle purchased Sun Microsystems, which had purchased MySQL AB, the original developers of MySQL, in 2008. When Oracle took over the development of MySQL, the original developer and some of the team left the project to start their own open source RDBMS project, MariaDB. This is perfectly legal with open source licensing. Over the last several years, the MariaDB project has gained respect due to this and its MySQL compatibility. Many Linux distributions have moved to MariaDB as a MySQL replacement package in their repositories. These distributions include Red Hat, Linux, and Ubuntu. Conducting a MariaDB installation. Installing MariaDB is fairly simple. You need super user privileges, of course, and the correct package name, MariaDB-server. Installing package was covered in Chapter 3, Installing and Maintaining Software in Ubuntu, and Chapter 5, Installing and Maintaining Software in Red Hat. Here is a snip example of installing MariaDB on Ubuntu after updating the system's package information. Sudo space apt space update, then sudo space apt space install space MariaDB-server. Installing MariaDB on a Red Hat base distribution is fairly straightforward. Here is a snip example of an installation on CentOS using the root account. dnf space dist space installed space MariaDB-server. Even though some distributions installation process sets the MariaDB service to start when the system boots, it's a good idea to go ahead and enable it yourself. Also, start the service as shown in this snip example on CentOS using the root account. Systemctl space status space MariaDB, then systemctl space start space MariaDB, then systemctl space status space MariaDB again. The MariaDB server is now enabled to start when the system boots. Also, it is currently active. After you've accomplished installing the server and enabling it, MariaDB is ready to start managing your data. Real-world scenario: installing the MariaDB server on your Ubuntu system. SQL code you write for MariaDB will also work for a MySQL server. Since many modern Linux distributions now support MariaDB as a replacement package for MySQL, it makes sense to install and focus on the MariaDB server. When you have the RDBMS installed, you can work on creating SQL statements to interact with it. The following steps will take you through installing the MariaDB server RDMS software on an Ubuntu distribution. 1. Log into your Ubuntu Linux system using the sysadmin account and the password you created for it. 2. Update the package information on your Ubuntu system by typing sudo space apt space update and pressing enter. Enter your account's password if the system asks for one. 3. After you receive the command line prompt back, install the MariaDB package by typing sudo space apt space install space MariaDB -server and pressing enter. Enter your account's password if the system asks for one. 4. During the installation process, when you receive the "Do you want to continue?" prompt, type the Y and press enter. When you receive the command line prompt back, check to see if the installation was successful by typing dpkg space -s space MariaDB -server space vertical line space grep space status and pressing enter. If you receive a message similar to status, install space OK space installed, continue on to the next step. If you do not receive this message, troubleshoot the installation. You can get additional help from Chapter 3. Set the MariaDB server to start when the system is booted by typing sudo space systemctl space enable space MariaDB and pressing enter. Enter your account's password if the system asks for one. 7. Start the MariaDB server by typing sudo space systemctl space start space MariaDB and pressing enter. Enter your account's password if the system asks for one. 8. Check to ensure that MariaDB service is enabled, will start at boot and active, is currently running by typing systemctl space status space MariaDB and pressing enter. Look through the commands output for the words enabled and active. If you do not see these words, go back to step 6 and reissue the commands in step 6 and 7, noting any error messages. If you do see these words, congratulations, your installation of MariaDB on Ubuntu was successful and the RDBMS is ready to manage your data. If you are running a Red Hat-based Linux system, the process for installation is different enough from Ubuntu that it is worth your time to try it for yourself. Real-world scenario: installing the MariaDB server on your Red Hat-based systems. Skip accessing a MariaDB database. You access and manage data within the MariaDB server through database user accounts. By default, a special all-powerful account called root, sound familiar, is installed as an account in the RDBMS. However, since this account has full access to everything in MariaDB, it is considered a poor security practice to use it for user-level access and management of data. It's best to create a single database account for every user account that needs access. This good security practice allows you to limit a user's access to a particular application's database and protect other managed MariaDB databases from accidental or intentional disturbance. When you've newly installed a MariaDB server, you will need to either log into the root system account or use sudo to gain super user privileges interface with MariaDB and create the first user account. The command to access the SQL interface to MariaDB is MySQL. When you are in the interface, your prompt will look like this: MariaDB space bracket parenthesis none close parenthesis close bracket greater than. This is one difference between MySQL and MariaDB. For MySQL, the prompt looks like this: MySQL space bracket opening parenthesis none close parenthesis close bracket greater than. To create your first user account, you may want the system's hostname, which can be obtained a variety of ways, including through the hostname command. The hostname can be used within the database account username. It's a good practice to use the same username for the database account as the Linux system's account's username. The SQL interface syntax to create a database user account is as follows: create space user space username at hostname space identified space by space quote password colon semicolon. Notice that at the end of the SQL syntax line, there is a semicolon. This lets the SQL interface know that you have completed entering the syntax for this statement. That small but important piece of SQL syntax is easy for those who are new to SQL to miss. An example of creating a first MariaDB database user account on an Ubuntu system using sudo to gain super privileges is shown here. Hostname without space. It will show Ubuntu server. Then sudo space MySQL. It will show sudo password for sysadmin. Then you'll type it without seeing any signal that you are typing it. Then create user. Then type the command create space user with all capitals space quote sysadmin at ubuntu-server quote. You don't have to put the user account name and host name in single quotation marks, but it's needed in this case because of the dash in the host name. Notice that you can put the SQL statement on 2 lines. That's because the interface doesn't care about line returns produced by the enter key like the bash shell does. Instead, the SQL interface is watching for a semicolon to end the statement. After you've created the user account, you can view it as shown here. MariaDB space opening bracket opening parenthesis none closing parenthesis closing bracket greater than space capital select space user space capital from space MySQL dot user semicolon. Managing database servers. Understand basic DBMS components. A database management system typically consists of a database engine, the database files for the database, and a query language interface, which typically uses standard SQL or something relatively compliant with standard SQL. These components assist in fulfilling the need to manage complex connections between individual data items. Master it. You have installed an RDBMS on your Linux system. The various applications that access this database reside on different servers across your local network. However, these servers are in different buildings on your company's campus. Recently, the power was cut to the campus due to a mistake by power utility supply company. You did not have any backup power systems in place and all your servers went down. Now that the power has been restored and your systems are back up and running again, none of the applications can access database. The system on which your RDBMS resides is running the primary database server, and there are no network firewall problems. What should you investigate next to resolve the issue? Solution: the database engine typically runs in the background as a daemon on Linux and provides access to the database data to local and, if configured, remote applications. The next item to investigate is whether the RDBMS daemon is currently running. If it is not, use super user privileges and the systemctl command to start the service. Then enable the service so that the next time the database server reboots, the RDBMS daemon is started automatically. Create user accounts within MariaDB. Managing and querying data within MariaDB server is accomplished through database user accounts. Typically, an account is created for every user account on the Linux system that needs to manage and or query data in the database. It is also considered a good practice to limit user access to only those databases associated with applications the user can access. Master it. Imagine you are the system administrator on a new Linux server. You have completed the installation of MariaDB and need to create a database for the application that will be using MariaDB as its RDMS. What are the next few steps to take after starting the MariaDB service and enabling it to start at system boot? Solution: your next major step is to create a database administrator account for yourself so that you do not have to use super user privileges or the root account to create the database. To do this, you will need to escalate your privileges to super user and issue the MySQL command to enter into the SQL interface. After that, your next step is to issue the appropriate create space user command along with the username of the account, the host name of the system, optional, and a password to access the SQL interface of MariaDB. After you have completed creating this account, you should log out of the MySQL interface and log back in using the new credentials. Now that this is accomplished, you can move forward with creating the database. Use SQL to query a MariaDB database. MariaDB uses several standard SQL commands plus a few more to manage databases, create tables, populate them with data, and query that data. The times that may cause you a little heartburn are when you need to use SQL commands that fall outside of the standards. However, that is fairly rare when interacting with MariaDB SQL interface. Master it. You have recently created a table named artificial without space flowers within Floris database. The artificial flower records listed in this table have only a few fields: product ID, which is the primary key, flower name, flower color without space, and stem color without space. The store manager of the florist shop wants to check the data you've entered into this table. What step should you take after you have logged into the MariaDB server's command line where this data exists? Solution: the first step is to log into the MariaDB's SQL interface using your database server username and password. Next, in the SQL interface, Connect to the database using the use space florist semicolon command. After that, you can display the data to the screen using the SQL command select all uppercase space asterisk space from uppercase space artificial without space flowers semicolon. Keep in mind that if there is a lot of data in this table, it will scroll off the screen. The store manager may prefer a report from which they can view the data as opposed to looking it on your computer screen. Install PostgreSQL on Linux. The PostgreSQL, also called Postgres RDBMS, has some features that make it popular in segments of the Linux community. For instance, it has data reliability structures and generally supports standard SQL with a few exceptions. Installing PostgreSQL can be a little tricky as its installation process is slightly different depending on the Linux distribution you are using. Master it. You are a system administrator for a Linux system whose customers want to use the PostgreSQL RDBMS on the system. This particular system is a Red Hat Linux distribution. What steps do you need to take to accomplish this task? Solution. The package name for PostgreSQL on a Red Hat or Red Hat based system is small letter PostgreSQL -server without space. So, to install it, you need to escalate your privileges to super user status and issue commands similar to DNF space install space PostgreSQL -server. After the installation, to finish this task, you will need to escalate your account's privileges and run PostgreSQL database initialization by issuing the following command with the super user privileges /user usr/bin/postgresql -setup space /inetdb. When this is completed, be sure to enable PostgreSQL to start at boot and start the daemon. Setup roles within PostgreSQL. Roles are used to access and manage data within a PostgreSQL server. It is considered a good practice to determine what privileges a user needs for using PostgreSQL database and then create a role with the appropriate privileges. This structure provides protection for the data and appropriate security tracking of database servers. Master it. You're the database administrator of the PostgreSQL database on your Linux system. Your database user role is named admin. This role has super user privileges in the database as well as the ability to create roles in databases. What if any, changes should be made to your account to improve the security levels of administering this database? Solution. Providing permissions of create role without space and uppercase and super space user uppercase to other database roles besides Postgres is considered risky. It would be best to remove the create role and super space user from the admin role and only use the Postgres account for those functions. While it is troublesome to have to log in to the Postgres account to add roles for the database, it does provide an extra layer of security around the data. The bottom line: understand basic hypervisor components. Hypervisors are used to create and manage VMs and are generally categorized as Type 1, Type 2, or hybrid. There are pros and cons associated with each category. For example, when creating a VM using a Type 2 hypervisor, host machine resources need auditing to determine if the VM's requirements can be met, while a Type 1 hypervisor eliminates the need for the physical host OS, it still can consume significant resources to run VMs. Creating a VM using hypervisor software is done using many different methods, such as P2V, cloning, using templates, or employing OVF files. Master it. You need to create and deploy several VMs that contain the same brand new applications and meet the same environment. After reviewing the various options, which method would you choose to create these VMs and why? Generate a container with a bash shell. Containers each have their own set of binaries and needed libraries to support their application stack or environment, but they share the physical host operating system. Starting and stopping containers instead of performing software upgrades within them is one reason why they are so popular for development and operations, or DevOps. Docker is one such container engine that is extremely popular. It uses a daemon on the Linux system to listen for requests from the individual containers as well as from a Docker command line interface that allows you to control the container environment. Master it. Imagine you are a system administrator for an Ubuntu Linux system, and the development team is considering Docker containers to use in their production of applications. To let them try this environment, you need to install Docker to create and manage containers. Your Ubuntu system is specifically a server distro, so you want to manage the containers from the command line. What steps can you take to quickly install the Docker engine and generate a test CentOS container with access to the bash shell for the software developers to try? Manage the Snap Universal Package System. The Snap Universal Package System employs the snap command to install and manage snap packages. The snap daemon updates this package on a regular basis through the appropriate snap channel. When run, snaps operate in an isolated sandbox, protecting other data and applications on a Linux system, including other running apps. Master it. You have recently visited the Snap store and found a wonderful Snap applications that will assist in your orchestration management of containers. Multipass. After installing it and running it through several tests, you decide to use it in your production environment. However, you'd like to also keep up to date with the new developments in this special Snap package. Besides reading about up-and-coming multipass features, how can you stay informed using a Snap package? Install the Flatpak framework. Software packages, Flatpaks, in the Flatpak Universal Package System focus on a single software applications and are a single self-contained compressed package file that holds all the binaries and dependencies needed for the app to work. Though Flatpak is similar to Snap, Flatpaks are currently available only for desktop applications on Linux systems. Master it. You are a system administrator for a CentOS desktop Linux system used by developers for creating the company's main software product. The developers are interested in a different text editor that will allow them to efficiently operate as they update the company's software app. Because there is a consideration to move development from the current Linux distro to another one that also uses Flatpak, you decided to install this text editor's Flatpak package that is available in FlatHub. What steps should you take to get this framework and text editor installed for the developers on this current system? Containers. Containers are virtual entities, but they are different from virtual machines and serve distinct purposes. Whereas a VM provides an entire guest operating system, a container's focus is typically on a single app, application stack, or environment. A container gathers all the files necessary to run an application. The runtime files, library files, database files, and any operating system specific files. The container becomes self-sufficient for the application to run, and everything the application needs is stored within the container. Instead of a hypervisor, a container is managed by a container engine. Figure 22.4 shows a diagram example of a container. Notice in the figure that the physical machine's operating system is shared among the containers. However, each container has its own set of binaries and needed libraries to support its app, application stack, or environment. Exploring container types. A container's focus depends on its purpose in life. Two container focal points are described here. Application containers. These containers focus on a single application or an application stack, such as a web server. Application containers are heavily used in development and operations. Software developers can modify their company's app in a newly created container. This same container with the modified app is then tested and eventually moved into production on the host machine. The old production container is destroyed. Using containers in this way eliminates production and development environment differences and provides little to no downtime for app users. Thus, containers are popular in continuous software development environments. The example in figure 22.4 showed two applications container. Operating system containers. While containers are useful for developers, system admins can love them too. You can use a container that provides a fully functioning Linux OS space and is isolated from your host machine. Some in system administration use containers to test their application and needed libraries on various Linux distributions. Other system admins, prior to upgrading their host system distro, try out their environment on an upgraded Linux distribution. You can also employ VMs for these different evaluations, but containers provide a faster to deploy and more lightweight test area. Keep in mind that virtualizing an application typically does not make it perform faster and should not be the primary motivation for moving it to a virtualized environment. Although containers allow you to quickly deploy applications, they will not cause an app to run more swiftly. Some hypervisors are termed efficient hypervisor, but that is only when there is a small performance difference between the physical environment and its virtualized self. Looking at container software, Linux has been in the forefront of container development, making it a popular choice for developers. Two main container packages are commonly used in Linux, as described here. LXC. The LXC package was developed as an open source standard for creating containers. Each container in LXC is a little more involved than just a standard lightweight application container, but not quite as heavy as a full virtual machine. Placing it somewhere in the middle, LXC containers include their own bare-bones operating system that interfaces with the host system hardware directly, without requiring a host operating system. Because LXC containers include their own mini operating system, they are sometimes referred to as virtual machines, although that term isn't quite correct as LXC containers still require a host operating system to operate. Software packaging. Software packaging has some troublesome issues. As an example, there are several packages and libraries needed called dependencies to make PostgreSQL, covered in Chapter 21, Managing Database Servers, fully functional. So when you install the PostgreSQL using apt or the PostgreSQL-server package using DNF, the needed dependencies are installed too. If a dependency is not available or the wrong version of it is installed, your database may not function correctly or securely. In addition, when the database server is set up and run, it is not fully isolated from the other software and services on the system. At some point in time, software package developer, sometimes called publishers, realized that system administrators and app developers were having all the fun with containers. It became apparent that software could be delivered and implemented on Linux systems in their own container-like environment. As a result, package developers began exploring this brave new world of software distribution. Using a container-like package system resolves many of the problems in our PostgreSQL example. A compressed software package holds all the needed dependencies, and each is the correct version. These packages are installed and run in a protected sandbox, making them unavailable to adversely affect other software and services on the system. This includes newer versions of the software package itself, so you could run two versions of PostgreSQL on the same system. In this section, we take a look at two container-like package formats, more appropriately called universal package systems. One is Snap and the other is Flatpak. Looking at Ubuntu Snap, Canonical, keepers of the Ubuntu distribution, introduced a new package system around 2015. However, it was released to the world in a limited form focused on only cloud-based applications and available only on the Ubuntu distribution. Over time, this package format called Snap became so popular that it was made available to other major Linux distributions, including Red Hat. Snap is now used not only for cloud-based applications, but also for desktop, server, and Internet of Things apps. Exploring the Snap package system. The Snap package system consists of many different components in its framework. The following parts are important for system administrators: Snap packages. Software packages in the Snap format are called snaps and focus on a single software application. For example, you could install the multipass orchestration snap on your system. The snaps download as a single self-contained compressed package file that holds all the binaries and dependencies needed for the app to work. Snaps are distribution independent. In other words, they don't require any modification for their apps to run on a different Linux distribution than the one for which they were originally packaged. This simplifies application version testing for the system administrator and package building for the package managers. However, keep in mind, not all Linux distributions support Snap. A popular aspect of Snap concerns heightened security. When you run an app installed from a Snap package, it operates in a sandbox. This way, it is isolated from other data and applications on a Linux system, including other running apps. Snap channels. A common problem with managing system applications is maintaining an older version of the app. There could be additional products or hardware that need to be upgraded prior to the installation of the latest and greatest software version. Sometimes your customers may refuse to sanction an application upgrade. Whatever the reason, a Snap channel can help. Snap channels are Snap delivery pathways. Your Snap package is updated using a set channel, though you can switch channels if desired. Configuring and maintaining server functions and features. Baselining. When all applications have been installed and proper services enabled, you need to create what is called a performance baseline. This snapshot should be taken during a period of normal activity. You can use third-party monitoring tools, or you can rely on some that are built into the system, such as the Performance Monitor tool in Windows Server 2020. Documentation. Save the performance baseline as a reference point for future readings. It is impossible to know when something abnormal is happening unless you know what is normal. Performance metrics. When monitoring resources, you select performance counters that represents aspects of the workload the resource is undergoing. But first, you need to know what normal is for your server. Comparison against performance baseline. This is because you have to define what is normal for your network. This is done by creating a set of performance metrics during normal operations when all is working well. While earlier in this chapter, we listed some rough guidelines about certain metrics, that is all they are, guidelines. Directory connectivity, enterprise network joint servers, workstations, and other devices in security associations called domains or realms. Such associations are what make the concept of single sign-on possible. This means that any user can log into the network using any device that is a domain member and receive all their assigned rights and privileges by using a single sign-on. You can join the server to the domain during the installation in some cases, but most administrators do this after the successful installation of the operating system. Store management. Store management comprises a set of activities that are designed to ensure that data is always there when you need it. Partitioning. When all of the volumes have been configured as you would like them, you must create a partition on one of the volumes to contain the operating system. Be mindful of the space required for the operating system and include some additional space. Figure 2.7, joining the server to the domain. Formatting. Once the partition has been created, it must be formatted with the file system. The file system choices will be driven by the operating system. We'll look at file systems in a bit. You can format the partition during the installation. Using the Windows Server 2012 R2 example, you choose the format option shown in Figure 2.8. Connectivity. In data scenarios where high availability or fault tolerance are required, don't forget to take advantage of concepts like multiple NICs or NIC teaming to provide additional bandwidth or a backup connection. Provisioning. These steps include analyze the storage request to determine capacity, security, and connectivity requirements. Identify the storage solution based on requirements, hard drive, SSD, cloud, storage array. Approve the selection and schedule the purchase and deployment. Partitioning. Partitioning was covered earlier in this chapter in the section Store Management. Page or swap or scratch location and size. These are files located on the hard drive that are utilized temporarily to hold items moved from memory when there is a shortage of memory required for that particular function. The running programs believe that their information is still in RAM, but the OS has moved the data to the hard drive. Every operating system seems to have its own recommendations as to the optimum size of this file, but in all cases, the swap file should be on different drive than the operating system if possible. Databases from the beginning. Every story must begin somewhere. Databases are no different. The grouping of data into logical constructs first appeared in technical articles in 1960, written by Bachman. As he explained, a database management system, DBMS, describes how data can be gathered, guided, and protected. Before that, persistence layers for applications usually were represented by flat file databases on mainframes. Back then, the most popular flat file types were the Index Sequential Access Method, ISAM, and Virtual Storage Access Method, VSAM. Flat file databases, however, have several disadvantages. They cannot link data from one file into another, so this task is the responsibility of the software developer. This task includes opening each file, accessing the data in each file by coding data access paths, and loading the dataset of interest in a volatile memory. Flat file databases are fixed form files, so any change to their structure creates a huge effort for the developers because of the absence of an abstraction layer between the software and its data. All programs consuming the modified flat file need to be updated to avoid the wrong data being pulled into memory and the corruption of the data residing in the flat file. Data redundancy was achieved by replicating it in multiple flat files, but the problem was maintaining consistency between the copies. DBMS were developed to address this need and improve the overall functionality of all sorts of applications. DBMS were more expensive than flat files. They demanded more specialized professionals, and at that time, most companies needed to invest in the professional development of their workforce. The costs of licensing, infrastructure, and personnel imposed a barrier on the initial adoption of DBMS. But, as with any new and improved technology, the benefits of database systems outweigh older flat file solutions, increasing adoption drastically. 1960s, Bachman's job paved the way for the creation of the CODASIL data model created by a consortium of companies to develop data processing capabilities for COBOL. This data model introduced the concept of DDL, Data Definition Language, and DML, Data Manipulation Language. File management systems flourished, enabling easier ways to access data at rest. IBM developed the Database Management Systems ICS, later renamed IMS. IMS was responsible for the persistent layer of the Apollo project and was directly involved in the Apollo 11 mission's computerized systems. The Sabra system, developed by IBM and American Airlines, allowed user access to data over the network, enabling American Airlines to automate reservation booking. It was first in the industry to achieve such automation. 1970s, database technologies experienced rapid growth. E.F. Codd's relational database model introduced the core concepts of database theory, including the entity relation model in 1976. Codd presented key definitions still in use until today, such as tables, columns, primary keys, and foreign keys. According to Codd, a table is a representation of a relation, for example, products, users, offices, and departments, and each relation is composed of several data domains as columns. For example, a relation of offices consists of the following data domains: address, available space, available facilities, and number of employees. Each data domain in this example has its own numeric relation. For example, available space should be a number representing the area in a specific metric system. Summary: Web APIs are HTTP-based services that any software application can use to access and possibly manipulate data. Web APIs are designed to work by using common communication standards, protocols, given sets of available operations, specifications, and data exchange formats, JSON, XML, and the like. Web APIs are commonly split among four possible scopes of use: public or open, when anyone has or can acquire access; partner, when access is restricted to business associates; internal or private, when access is limited to the organization's network; composite, when they orchestrate multiple public, partner, or internal API calls. To fulfill their role, web APIs require a uniform set of rules, constraints, and formats that depend on the chosen architectural style or messaging protocol. The most used standards nowadays are REST, SOAP, gRPC, and GraphQL, each of which has distinctive characteristics, trade-offs, and supported formats. This book focuses mostly on REST, but Chapter 10 is dedicated to GraphQL. ASP.NET Core is the high-performance cross-platform open-source web development framework that we will use to design and develop web APIs throughout this book. ASP.NET Core's modern architectural principles allow developers to build lightweight, highly modular apps with a great level of testability and maintainability. ASP.NET Core architecture allows developers to customize the app capabilities and workloads by using discrete and reusable components to perform specific tasks. These components fall into two main categories, both of which are registered and configured in the app's entry point, the program.cs file. Services required to provide functionalities and instantiated through dependency injection. Middleware responsible for handling the HTTP request pipeline. ASP.NET Core supports two paradigms for building web APIs: controllers, which offer great versatility and a full set of supported features, and minimal APIs, a simplified approach that allows us to write less code while reducing overhead. The minimal API approach, introduced in .NET 6, can be a great way to build simple web APIs in a time-efficient fashion and is great for developers who are looking for a sleek, modern programming approach. ASP.NET Core web apps can overcome most performance problems due to resource-intensive thread blocking calls by using TOP, an asynchronous programming model that allows the main thread to start tasks in a non-blocking way and resume execution upon their completion. Web APIs at a glance. Almost all applications need data, especially web-based applications, in which large numbers of clients interact with a centralized entity, typically an HTTP-based service to access information and possibly update or manipulate them. In this book, we'll learn how to design and develop a specific type of HTTP-based service that has the sole purpose of providing data to these clients, allowing them to interact with the information they require in a uniform, structured, and standardized way, a web API. In the first section of this chapter, we'll see the distinctive characteristics of a web API and learn how it can be applied to several real-world scenarios Web APIs. An application programming interface is a type of software interface that exposes tools and services that computer programs use to interact with each other and exchange information. The connection required to perform such exchanges is established by means of common communication standards or protocols, given sets of available operations, specifications, and data exchange formats, JSON, XML, and the like. From that definition, we can easily see that the main purpose of an API is to allow parties to communicate by using a common syntax or abstraction that simplifies and standardizes what happens under each hood. The overall concept is similar to that of real-world interfaces, which also provide a common syntax to allow different parties to operate. A perfect example is the plug socket, an abstraction used by all national electrical systems to allow household appliances and electronic devices to interact with the power supply through given voltage, frequency, and plug type standards. Figure 1.1 shows the main components that form an electrical grid, an interconnected network for generating, transmitting, and delivering electricity from producers to residential consumers. As we can see, each component handles electricity in a different way and communicates with the others by using various protocols and adapters, cable lines, transformers, and so on, with the ultimate goal of bringing it to people's houses. When the residential units are connected to the grids, the electricity can be used by home appliances, TV sets, ovens, refrigerators, and so on, through a secure, protected, easy-to-use interface, the AC power plug. If we think about these sockets work, we can easily understand how much they simplify the technical aspects of the underlying power grid. Home appliances don't have to know how such a system works as long as they can deal with the interface. A web API is the same concept brought to the World Wide Web. An interface accessible through the web that exposes one or more plugs, the endpoints, which other parties, the clients, can use to interact with the power supply, the data, by using common communication protocols, HTTP, and standards JSON or XML formats. Throughout this book, the term Web API will be used interchangeably to mean both the interface and the actual web application. Figure 1.2 illustrates the purpose of a web API within a typical service-oriented architecture environment. SOA is an architectural style built around the separation of responsibility of various independent services that communicate over network. As we can see, the Web API plays a key role because it is responsible for retrieving the data from the underlying database management system and making it available to the services. Web App 1, such as React Informative Website, which fetches data from the Web API to display it to end users through HTML pages and components. Mobile App 1, such as Android App, and Mobile App 2, which can be the iOS port of the same app, which also fetches data and show them to end users through their native user interfaces. Web App 2, such as a PHP management website, which accesses the Web API to allow administrators to interact with and possibly modify the data. Cloud Service 1, such as a data warehouse, which periodically pulls data from the Web API to feed its internal repository to persist some access logs, for example. Cloud Service 2, such as machine learning software, which periodically retrieves some test data from the Web API and uses it to perform predictions and provide useful insights. What we've just described
is an interesting scenario that can help us understand the role of Web API within a rather common service-based ecosystem. But we're still discussing an impersonal, theoretical approach. Let's see how we can adopt the same architecture to a specific real-world scenario. Real-world example. In this section, we instantiate the abstract concept depicted in Figure 1.1 into a concrete, credible, and realistic scenario. Everyone knows what a board game is, right? We're talking about tabletop games with dice, cards, and playing pieces, and stuff like that. Suppose that we work in the IT department of a board gaming club. The club has a database of board games that includes gaming info such as name, publication year, minimum to max players, playtime, minimum age, complexity and mechanics, as well as some ranking stats, number of ratings and average rating, given by club members, guests, and other players over time. Let's also assume that the club wants to use this database to feed some web-based services and applications, such as the following. An end-user website, accessible to everyone, to showcase the board games and their ratings, as well as provide some additional features to registered users, such as ability to create lists. A mobile app, also publicly accessible with the same features as the website, and an optimized UI or UX user experience interface for smartphones and tablets. A management portal, available to a restricted list of authorized users that allows those users to perform, create, read, update, and delete or CRUD operations in the database and carry out other administration-based tasks. A data analysis service hosted on a third-party platform. As we can easily guess, a great way to fulfill such requirements would be to implement a dedicated web API. This approach allows us to feed all these services without exposing the database server and its underlying data model to any of them. Figure 1.3. Several board game related web applications and services fed by a single MyGList web API. Again, the web API is the playmaker, fetching the data source containing all the relevant MyBGList DBMS and making it available to other services. MyBGList website, a React.js website entirely hosted on a content delivery network following the Jamstack approach, where users can browse the board game catalog and add games to a set of predefined lists, own, want to try, want to buy, and so on, as well as add their own custom lists. MyBGList mobile app, a React Native app available for Android and iOS that allow users to perform the same actions that are available on the MyBGList website, browse and add to lists. MyBGList management portal, an ASP.NET web applications hosted on a dedicated virtual machine server within a secure private cloud that system administrators can access to add, update, and delete board games as well as perform maintenance-based tasks. MyBGList Insights, a software as a service that periodically pulls data from the web API to feed its internal repository and to perform logging, monitoring, and performance analysis and business intelligence tasks. This web API is the one we'll be working with throughout the following chapters. Type of web APIs. Now that we know the general picture, we can spend some time exploring the various architectures and messaging protocols available to web API developers nowadays. As we'll be able to see, each type has characteristics, pros, and cons that make it suitable for different applications and businesses. Before looking at various architectures, let's briefly summarize the four main scope of use in which each web API commonly falls. Public APIs. Public APIs are also called open APIs, not to be confused with the Open API specification. As the name suggests, This term refers to APIs that are meant to be available for use by any third party, often without access limitations. These APIs typically involve no authentication and authorization if they're free to use, or they employ a key or token authentication mechanism if they need to identify the caller for various reasons, such as applying per call costs. Furthermore, because their endpoints are usually accessible from the World Wide Web, public APIs often use various throttling, queuing, and security techniques to avoid being crippled by a massive number of simultaneous requests, as well denial of service attacks. Partner APIs. The APIs that fall into this category are meant to be available only to specifically selected and authorized partners such as external developers, system integrator companies, whitelisted external internet protocols, and the like. Partner APIs are used mostly to facilitate business-to-business activities. An example would be an e-commerce website that wants to share its customers' data with a third-party business partner that needs to feed its own customer relationship management and marketing automation systems. These APIs typically implement strong authentication mechanisms and IP restriction techniques to prevent them from being accessed by unauthorized users. They're definitely not meant to be consumed by end users or public clients such as standard websites. Internal APIs, also known as private APIs. These APIs are meant for internal use only, such as to connect different services owned by the same organization, and are often hosted within the same virtual private network, web farm, or private cloud. An internal API, for example, can be used by the internal enterprise resource planning software to retrieve data from various internet business sources, payroll, asset management, project management, procurement, and so on, as well as create high-level reports and data visualizations. Because these APIs are not exposed to the outside, they often implement mild authentication techniques depending on the organization's internal security model and its performance and load balancing tweaks. Composite APIs, sometimes referred to as API gateways. These APIs combine multiple APIs to execute a sequence of related or interdependent operations with a single call. In a nutshell, they allow developers to access several endpoints at the same time. Such an approach is used mostly in microservice architecture patterns, in which executing a complex task can require the completion of a chain of subtasks handled by several services in a synchronous or asynchronous way. A composite API acts mostly as an API orchestrator, ensuring that the various subtasks required to perform the main call are successful and capable of returning a valid result, or invalidating the whole process if they aren't. A common use scenario ensures that multiple third-party services fulfill their respective jobs, such as when we need to delete a user record and all its personal info permanently in our internal database and in several external data sources without creating atomicity problems, such as leaving potentially sensitive data somewhere, because the orchestrated calls can be of multiple types. Public, partner, or internal composite APIs often end up being hybrids, which is why they're generally considered to represent a different API type.
Configuring network settings. For servers, it's a necessity to have your Linux system connected to some type of network, whether it's the need to share files and printers on a local network or serve web pages on the internet. Your Linux server will most likely require some type of network connection. In this chapter, you will learn to find and examine the network configuration files for your server, view and change network configuration settings using command line tools, troubleshoot common network problems. Network settings. When you first installed your Linux server software, you were required to specify the network settings for your server to operate in network environment. Most Linux workstation setups can use the dynamic host configuration protocol, which allows the workstation to request network information from a DHCP server on the network automatically. You don't have to configure anything. Unfortunately, Linux servers are a bit different. Since clients must know exactly where to find the server on the network, Linux servers should have a static IP address assigned. While that's possible to do via DHCP, depending on your network, it's also possible that you'll need to set the static IP address manually in the server configuration. That makes the job of configuring a Linux server for the network a little bit harder. There are 5 main pieces of information you need to configure for your Linux system to interact on a network: the host address, the network subnet address, the default router, sometimes called the gateway, the system hostname, a DNS server address for resolving hostnames. Unfortunately, different Linux distributions use different methods for storing the network information required for the system. The following sections walk through the standard network configurations for both Ubuntu and Red Hat servers. Ubuntu servers. If you choose to manually configure the network settings during the Ubuntu server installation, a form appears for you to select which network interface to configure, as you've previously installed in Ubuntu. When you select a specific interface and set it to manual settings, a new form appears for you to fill out. In this form, you'll need to specify the values for each of the network settings. The installation service then automatically sets these values in the appropriate network configuration files for you. However, if you ever need to change the network settings, it helps to know where to find that information. Since version 17.04 Ubuntu servers utilize the NetPlan tool to manage network settings for the server, the NetPlan tool doesn't actually handle network traffic itself. That job is left to systemd network D application. Instead, NetPlan just makes the job of configuring network settings easier and then passes that information onto the systemd-network D application. NetPlan uses a simple series of text-based configuration files located in the /etc/netplan directory to define all of the required network settings. These files use the YAML ain't markup language text format to define the network settings. There can be multiple files in the /etc/netplan directory, and each file definition builds off prior files in the directory in lexicographical order. This allows you to split multiple network settings into multiple files, making it easier to define settings for multiple network interfaces if necessary. Listing 12.1 shows a sample NetPlan configuration file for an Ubuntu server. In this example, the Ubuntu server has 2 network interface cards. The ENP0S3 interface uses DHCP to obtain dynamic IP address from a DHCP server on the network. The ENP0S8 interface uses a static IP address of 192.168.1.80 on the network. The /24 at the end of the address indicates the subnet mask is 255.255.2.5.0. The file also specifies the default gateway or router and the name server DNS server address. If you make any changes to the YAML files, you'll need to do either reboot the server for the changes to take effect or use the netplan command line tool to have netplan forward the changes to the systemd-networkd application by using the apply option. Netplan space apply. The netplan tool automatically informs the systemd network D application that settings have been changed so it can update information. Working with data files. When you have a large amount of data, it's often difficult to handle the information and make it useful. The Linux system provides several CLI tools to help you manage large amounts of data. This section covers the basic commands that every system administrator, as well as any everyday Linux user, should know how to use to make their lives easier. Sorting. Often, to understand the data within text files, you need to reformat file data in some way. The sort utility sorts a file's data. It makes no changes to the original file. It only reads the file, sorts its data, and displays the sorted data to stdout. If you want to order a file's content alphabetically, simply enter the sort command followed by the name of the file you want to sort. Nano alphabet key.txt, cut alphabet key.txt, sort alphabet key.txt. It's pretty simple. However, things aren't always as easy as they appear. Take a look at this example. Nano number key.txt, cut number key.txt, sort number key.txt. If you were expecting the numbers to sort in numerical order, you were disappointed. By default, the sort command interprets numbers as characters, producing a sorted output that you may not want. Add the N option to the command to sort the text based on their numerical values, if that's what you are seeking. Sort -n number key.txt. There are several useful sort parameters you can use depending on what kind of sort is needed. Table 8.4 Commonly used sort command options: single dash, letter B, double dash, ignore leading blanks, description, ignore leading blanks when sorting. D, dictionary order, considers only blanks and alphanumerical characters. Don't consider special characters. F, ignore case. By default, sort orders capitalize letters first. This parameter ignores case. G, general numeric sort. Use general numerical value to sort. Viewing sorted data is helpful, but what do you do if you want to keep that sorted data? stdout redirection can help here. Nano number key sci-fi.txt, cut number key sci-fi.txt. Sort -n -t code -k to number key sci-fi.txt greater than sorted sci-fi.txt. Cut sorted sci-fi.txt. Keeping sorted data is especially handy when you've used a complex sort like the previous one. Another useful function when dealing with text data is searching for it. We'll cover that topic next. Searching. You may need to locate a text file within the virtual directory structure or just search through a file or text. For text. Either way, Linux provides you lots of options to accomplish your task. Locating files. A simple utility to use in finding files quickly is the locate program. What makes it fast is that this command searches a database that is pre-filled with file names and their locations. Red Hat servers. When you select to configure network settings in Red Hat installation process, a dialog box appears showing you the available network interfaces. After you select an interface and click the Configure button, a form appears allowing you to set the network configuration for that interface. Select the IPv4 settings tab at the top to set the necessary network information for the interface. The installation program saves the configuration settings you enter to one or more files in the /etc/sysconfig/network-scripts directory. Each network interface has its own file. Sample CentOS network interface configuration settings. Type equal Ethernet. Proxy underscore method equal none. Browser underscore only equal no. Boot proto equal none. Def route equal yes. IPv4-failure-fatal equal no. IPv6 init equal yes. IPv6 underscore autoconf equal yes. IPv6-diffroute equal yes. IPv6-failure-fatal equal no. Red Hat servers use the Network Manager tool to manage the network configurations and interfaces. If you make any changes to these files, you'll need to either reboot the server or restart the Network Manager service using the following command. systemctl restart Network Manager. This forces the Network Manager program to read the network configuration files and start the appropriate interfaces you have defined. Using network command line tools. Since most Linux server environments don't use a graphical desktop, you'll need to become familiar with the Linux command line tools to change any of the network configuration settings after installation. There are quite a few different command line tools that you have at your disposal. This section covers the ones you're most likely to run into. Network Manager tools. While the Network Manager tool is most often used in graphical workstation environments, Red Hat servers utilize the command line tools that it provides. NMTUI provides a simple text-based menu tool. NMCLI provides a text-only command line tool. Both of these tools help guide you through the process of setting the required network information for your Linux system. The NMTUI tool displays a stripped-down version of the graphical tool where you can select a network interface and assign network properties to it, as shown in Figure 12.5. The NMCLI tool doesn't attempt to use any type of graphical capabilities. It just provides a command line interface where you can view and change the network settings. By default, the command displays the current network devices and their settings. The NMCLI command uses command line options to allow you to set the network settings. Sample #NMCLI /con /add /type /ethernet /con -name -ethl -if name -enp0s3 -ip4. This is a quick way to change network settings directly from the command line. Other tools. If your Linux distribution doesn't support one of the Network Manager tools such as Ubuntu servers, there are a few legacy command line tools that you can use. ETH with no space tool displays Ethernet settings for a network interface. ifconfig displays or sets the IP address and netmask values for a network interface. IP displays or sets the IP address, netmask, and router values for a network interface. IWconfig sets the SSID and encryption key for a wireless interface. Route sets the default router address. Bond binds two or more network cards together. The following sections take a closer look at each of these tools. Finding locate. Be aware that locate may not be installed by default on your Linux distribution. If you'd like to have it, the package name is locate, and you can use the instructions for installing software packages in Chapter 3. If your distro is Ubuntu or Ubuntu based, on Chapter 5. If you are using a Red Hat, for CentOS. To find a file with locate command, just enter locate followed by the file's name you want to find. If the file is on your system and you have permission to view it, the locate utility will display the file's directory path and name as demonstrated here on an Ubuntu distribution. Locate space .bash _ history. Another nice feature of locate is that it uses a pattern to find files. This allows you to employ partial file names and regular expressions. And with the command options, ignore case. Table shows a few of the more commonly used locate command options. Short, first column, letter A. Long, second column, all. Description, third column. Display only file names that match all the patterns instead of displaying files that match only one pattern in the pattern list. B. Base name. Display only file names that match the pattern and do not include any directory names that match the pattern. C. Count. Display only the number of files whose name matches the pattern instead of displaying file names. I. Ignore case. Ignore case in the pattern for matching file names. Q. Quiet. Do not display any error messages such as permission denied when processing. R. Reg XP. Capital R. Use the regular expression R instead of the pattern list to match file names. Where you can run into problems with locate is when a file is newly created. Here's an example of using the touch command to create a file and then it tries to find it with the local utility. Touch new file.txt, ls new file.txt, locate new file.txt. When a file is newly created, often it is not yet listed in the locate database. Typically, this database is updated only periodically. Also, when you have a newly installed Linux system, the database may not even yet exist. To fix both of these issues, you'll need to obtain superuser privileges and run the update db command. This will update the database named /var/lib/mlocate/mlocate.db or create and update it. That's much better. Now that database is updated, the newly created file can be found by the locate utility. The locate command is useful when you want to find files by their name, but it's not useful when you're trying to find a file based on its size or who owns it. This is where the find command can help. Finding files. The find command is flexible. It allows you to locate files based on data, such as who owns the file, when the file was last modified, permissions set on the file, and so on. Its command line format is a little different. Find space path, space option, space expression. The path argument is a starting point directory because you designate a starting point in a directory tree. and find will search through that directory and all its subdirectories recursively for the file or files you seek. You can use a single period to designate your present working directory as the starting point directory. The expression command argument and its preceding option control what type of filters are applied to the search, as well as any settings that may limit the search. Table shows more commonly used option and expression combinations. Column 1, option, cmin. Column 2, expression, n. Description, display names of files whose status changed n minutes ago. Option, empty. Expression, not applicable. Displays names of files that are empty and are a regular text file or a directory. GID, n. Display name of files whose group ID is equal to n. Group name, display name of files whose group is name. INUM, n. Display name of files whose inode number is equal to n. Name, pattern, display name of files whose name matches pattern. Many regular expression arguments may be used in the pattern and need to be enclosed in quotation marks to avoid unpredictable results. Replace name with iname to ignore case. Size, n. Display names of files whose size matches n. Suffixes can be used to make the size more human readable, such as G for gigabytes. One nice feature of Find is that it will display all the files in your present working directory and any subdirectories that have no data in them. Find space dot space dash empty. Unlike locate, you can quickly find files that were newly created without updating a database. Touch, another new file that text. Find /home /sysadmin -name, another new file that text. You can search for files whose status was recently changed, just such as when data has been added to the file. You can modify these find command searches at any location with the virtual directory system. However, you may want to use super user privileges to get accurate results and avoid an overload of permission denied messages. Both locate and find are useful for discovering a file's location or performing a basic file analysis. However, neither of these commands can search through and display a file's contents. We'll cover a utility that does offer that feature next. Searching for and through files. When you need a utility that lets you search for files that contain certain data, grep is the winner. The command line format for the grep command is as follows: grep, options, pattern, file. In the following example, the text files we've used or created for this chapter are listed in a single column format via the ls *1 **text command. Two of those files contain the word pi, but which ones? The grep command can easily determine the correct answer. In the preceding example, the pattern used with grep was pi, and then in the current directory, all the text files *text were searched. The grep command lists and search results by displaying each file's name that contained the pattern and then shows the entire text line that has the pattern. There are some nice options you can use in your grep searches. Table 8.7 shows some of the more commonly used grep utility options. The grep command's commonly used options: C, short, first column, C, long, second column, count, description, display a count of text file records that contain a pattern match. D. Action. Directories equal action. When a file is a directory, if action is set to read the directory as if it were a regular text file. If action is set to skip, ignore the directory, and if action is set to recurse, act as if the R, or recursive option was used. E. Extended reg XP. Designate the pattern as an extended regular expression. I. Ignore case. Ignore the case in the pattern as well as in any text file records. R. Capital R, comma, small r. Recursive. Search a directory's contents, and for any subdirectory within the original directory tree, consecutively search its contents as well recursively. Small letter v. Invert match. Display only text files records that do not contain a pattern match. When searching through larger sections of the virtual directory structure for files containing certain data, it's a good idea to employ the D space skip option so that grep doesn't complain at you when it encounters a directory file. Regular expressions. Instead of looking for a word using grep, you can conduct a search using a regular expression. A regular expression is a pattern template you define for a utility such as grep, which uses a pattern template to filter text. Basic regular expressions include characters such as a dot followed by an asterisk to represent multiple characters and a single dot to represent one character. They also may use brackets to represent multiple characters such as bracket A, comma E, comma I, comma O, comma U, bracket or a range of characters such as A to Z, bracket A space Z. To find text file records that begin with particular characters, you can precede them with caret symbol. For finding text file records where particular characters at the record's end, succeed them with the $sign symbol. In addition to BREs, there are extended regular expressions, which have more complex pattern templates. When using grep with EREs, you must add the E option to the command. An ERE pattern example is word 1, vertical line word 2, which tells grep that if a text line contains either word 1 or word 2, display it. If you'd like a more in-depth look at regular expressions, our favorite resource is Linux Command Line and Shell Scripting Bible. You can conduct rather complex searches with grep by using regular expressions. The grep can even handle extended regular expressions if you use the E option. The grep E command is the more modern version of the egrep utility. The grep E command is the more modern version of the egrep utility. The two are functionally the same, but egrep is now deprecated. When a command is deprecated, this means that it may not be available in the future, so you should stop using it as soon as possible and start using its modern equal. Compressing. Linux contains several file compression utilities that allow you to easily compress large files into smaller files that take up less space. While this may sound great, it often leads to confusion and chaos when you're trying to determine which utility to use. The following popular utilities are available on Linux: gzip, bzip2, xz. The advantages and disadvantages of each of these data compression methods are explored in this section. gzip. The gzip utility was developed in 1992 as a replacement for the old compress program, achieving text-based file compression rates of 60 to 70%. gzip has long been a popular data compression utility. To compress a file, simply type in gzip followed by the file's name. The original file is replaced by a compressed version with a .gz file name extension. To reverse the operation, type in gunzip followed by the compressed file names. Archiving. Backing up files is often called archiving, especially in the Linux world. There are several programs you can employ for managing backups. Some of the more popular products are Amanda, Bakula, Bareos, Duplicity, and Backup PC. Yet often these GUI or web-based programs have command line utilities at their core, which include the following: CPIO, DD, rsync, tar. The tar command was originally used to write files to a tape device for archiving. However, it can also write the output to a file, which has become a popular way to archive data in Linux, and that's the command we'll focus on in this chapter. The tar command copies the selected files and stores them in a single file. This file is called a tar archive file. If this archive file is compressed using a data compression utility, the compressed archive file is called a tarball. The tar program has several useful options. Table describes the more commonly used ones for creating data backups. First column, short, C. Second column, long, create. Description: creates a tar archive file. The backup can be a full or incremental backup, depending upon other selected options. U. Update. Appends files to an existing tar archive file but only copies those files that were modified since the original archive file was created. G. Listed incremental. Creates an incremental or full archive based upon metadata stored in the provided file. Z. gzip. Compress a tar archive file into a tarball using gzip. J. bzip2. Compresses a tar archive file into a tarball using bzip2. J. xz. Compress a tar archive file into a tarball using xz. V. verbose. Displays each file's name as each file is processed. Notice that there are some compression options in Table 8.8. When you use a compression utility along with an archive and restore program for data backups, it is vital that you use a lossless compression method. A lossless compression is just as it sounds. No data is lost. The gzip, bzip2, and xz utilities provide lossless compression. Obviously, it is important not to lose data when doing backups. To create an archive using the tar utility, you have to add a few arguments for the options and the command. In the preceding example, three options are used. The C option creates the tar archive. The V option displays the file names as they are placed into the archive file. The F option designates the archive file name, which is archive.tar. So that's tar space dash cvf archive.tar n asterisk the text, which is the file we created earlier. Though not required, it is considered good form to use the .tar extension on tar archive files. The example command's last argument designates the files to copy into this archive. If you are backing up lots of files or large amounts of data, it's a good idea to employ a compression utility. This is easily accomplished by adding an additional switch to your tar command options. Here, gzip compression is used to create a tarball. There are a couple of things to note in this example. First, look at the tar. Removing leading messages. The tar utility strips off the first forward slash in file names so that they can be restored anywhere in the future. If that forward slash was left in there, the files would only go back to their original location in the virtual directory structure, which is not very flexible. The next thing to note in the preceding example is that the tarball file name has the .tar.gz file extension. It is considered good form to use the .tar extension and tack on an indicator showing the compression method that was used. However, you can shorten it to .tgz if desired. Whenever you create data backups, it is a good practice to verify them. Table provides some tar command options for viewing and verifying data backups. The tar commands commonly use archive verification options. Column 1 short, D, column 2 long, compare diff, description, compares a tar archive files members with external files and lists the differences. T, list, displays a tar archive files contents. W, verify, verifies each file as the file is processed. This option cannot be used with the compression options. Backup verification can take several different forms. You might ensure that the desired files, sometimes called members, are included in your backup by using the V option on the tar command in order to watch the files being listed as they are included in the archive file. You can also verify that desired files are included in your backup after the fact. Use the T option to list a tarball or archive files contents. Table 8.10 lists some of the options that you can use with tar utility to restore data from a tar archive file or tarball. Several options used to create the backup, such as G, are also available when restoring data. First column short, X, second column long, extract, get. Description, third column, extract files from a tarball or archive file and place them in the current working directory. Z, gunzip, decompress files in a tarball using gunzip. J, banzip2, decompresses files in a tarball using banzip2. Extracting files from an archive or tarball is very simple using the tar utility. In the previous example, a new subdirectory extract is created. The tarball is moved to the new subdirectory and then the files are restored from the tarball. Notice that instead of putting the files in the top level of the new subdirectory, extract, they were instead placed in the var/log subdirectory. That's because tar removed the leading forward slash of the original files but kept the rest of the directory references. This is a rather useful feature of the tar utility. These quotas, these are limits assigned to each user. These limits can be implemented with a warning to users when they are filling their allocated space so they can delete some data or take some action that keeps them within their limits. In the figure, all users are being given 100 millibytes of space and will be warned when they get 50 millibytes. Compression. Another tactic you can use to better utilize the space you have is to compress files that are used infrequently. This can be done in Windows at both the file and the folder levels. In the advanced attributes of the file or folder properties, select Compress Contents to save disk space, as shown in figure 2.10. Be aware that when you do this to files and folders that are frequently accessed, you will place a load on the CPU of the server because it decompresses the file to make it available and then compresses it again when saved. The duplication. In many cases, data is located multiple times on the same drive. This process can be done after the data is on the drive, or it can be implemented inline, which means data being written to the drive is examined first to see if it already exists on the drive. Monitoring. Uptime. Uptime is the description of the ratio of time a system spends up and running as opposed to offline and available. Generally speaking, increasing the number of nines involves spending money to provide the resources necessary to deliver that uptime. Thresholds. These alerts are designed to allow technicians to react to a system performance issue before it impacts the business. Performance. When discussing the performance of system resources such as memory and CPU, you need to know the major metrics that are used to assess performance of each resource. Memory. Different server roles place different demands on the memory, so there may be specific metrics called counters in Windows of interest you can learn about by consulting the vendor documentation. Memory. Percentage committed bytes in use, the amount of virtual memory in use. If this over 80%, you need more memory. Disk. On several of the server roles we discussed, disk was the critical resource. When monitoring the disk subsystem, you must consider two issues: the speed with which the disk is being accessed and the capacity you have available. Let's examine those metrics in more detail. Input or output operations per second. This input or output operations per second represents the number of reads and writes that can be done in 1 second. One of the advantages of newer solid-state drives is that they exhibit much higher IOPS values than traditional hard disk drives. Capacity versus utilization. The second metric of interest when designing a storage solution is capacity. When planning and managing storage capacity, consider the following questions. For example, if data is located on a RAID 1 or mirror drive, you need twice as much space for data. As the number of drives in the array go up, the amount of space required for the parity information goes down as percentage of the space in the drive. How fast are the needs growing? Remember that your needs are not static, they are changing at all times and probably growing. You can calculate this growth rate manually or you can use capacity planning tools. Are there major expansions on the table? Network. As you learned, the NIC can become a bottleneck in the system if it cannot keep up with the traffic. Here are some common counters monitored by server administrators. Network interface. If this value is more than 70% of the bandwidth of the interface is saturated or not keeping up.
Load balancer. A load balancer evenly distributes incoming traffic among web servers that are defined in a load balance set. Figure shows how a load balancer works. As shown, users connect to the public IP of the load balancer directly. With this setup, web servers are unreachable directly by clients anymore. For better security, private IPs are used for communication between servers. A private IP is an IP address reachable only between servers in the same network. However, it is unreachable over the internet. The load balancer communicates with the web servers through private IPs.
In figure, after a load balancer and a second web server are added, we successfully solved no failover issue and improved the availability of the web tier. Details are explained below. If server 1 goes offline, all the traffic will be routed to server 2. This prevents the website from going offline. We will also add a new healthy web servers to the server pool to balance the load. If the website traffic grows rapidly and 2 servers are not enough to handle the traffic, the load balancer can handle this problem gracefully. You only need to add more servers to the web server pool, and the load balancer automatically starts to send requests to them. Now the web tier looks good. What about the data tier? The current design has one database, so it does not support failover and redundancy. Database replication is a common technique to address those problems. Let us take a look. Database replication. Quoted from Wikipedia, database replication can be used in many database management systems, usually with a master or slave relationship between the original master and the copies, slaves. A master database generally only supports write operations. A slave database gets copies of the data from the master database and only supports read operations. All the data modifying commands like insert, delete, or update must be sent to the master database. Most applications require a much higher ratio of reads to writes. Thus, the number of slave databases in a system is usually larger than the number of master databases. Figure shows a master database with multiple slave databases. Advantages of database replication: better performance. In the master to slave model, all writes and updates happen in master nodes, whereas read operations are distributed across slave nodes. This model improves performance because it allows more queries to be processed in parallel. Reliability. If one of your database servers is destroyed by a natural disaster, such as typhoon or an earthquake, data is still preserved. You do not need to worry about data loss because data is replicated across multiple locations. High availability. By replicating data across different locations, your website remains in operation even if a database is offline, as you can access data stored in another database server. In the previous section, we discussed how a load balancer helped to improve system availability. We asked the same questions here. What if one of the database goes offline? The architectural design discussed in figure can handle this case. 1. If only one slave database is available and it goes offline, read operations will be directed to the master database temporarily. As soon as the issue is found, a new slave database will replace the old one. In case multiple databases are available, read operations are redirected to other healthy slave databases. A new database server will replace the old one. Empathy statement. I'm truly sorry for the difficulties you've encountered. Your experience matters greatly to us, and we'll do everything we can to make it right. I deeply regret the inconvenience this has caused you, and assure you that we're committed to finding a solution. I empathize with the frustration you're feeling right now, and I'm dedicated to addressing your concerns effectively. It must be incredibly frustrating to deal with this issue, and I appreciate you bringing it to our attention so we can fix it. I can imagine how upsetting this situation is for you. and I want to make sure we resolve it to your satisfaction. I apologize for the trouble this has caused you, and I'm here to assist you every step of the way. I can understand why you're upset, and I want to assure you that we're taking your concern seriously. I genuinely feel for the inconvenience this has caused and will do everything in my power to rectify it. I know this situation has been tough for you, and I appreciate your patience as we work towards a resolution. I feel terrible that you've had to experience this issue, and I'm here to ensure we find a satisfactory solution. I understand that this situation has been incredibly frustrating, and I want to help make it right for you. I'm sorry that you're facing this problem, and I appreciate your patience as we resolve it together. I can empathize with how this issue can affect you, and I am committed to resolving it promptly. I understand how challenging this situation must be, and I am dedicated to finding a swift resolution for you. I apologize for any stress this situation has caused and assure you that your satisfaction is our priority. I'm truly sorry for the inconvenience you've experienced, and I want to make sure we fix this for you. I can see why this situation is upsetting, and I'm here to help you find a resolution as quickly as possible. I deeply regret the issues you've encountered, and I'm committed to resolving them to your satisfaction. I understand how frustrating this must be, and I'm here to assist you in any way I can to resolve this issue. I apologize for the inconvenience and appreciate your patience as we work to resolve this matter for you. I can imagine how stressful this situation is, and I'm here to help make it right for you. I feel terrible that you've had to deal with this issue, and I'm dedicated to resolving it to your satisfaction. I understand the frustration this has caused, and I appreciate your patience as we address it. I'm sorry that this issue has caused you such inconvenience, and I'm here to help find a solution. I can empathize with your frustration and want to assure you that we're working diligently to resolve it. I regret that you've encountered this issue and appreciate your patience as we work towards a resolution. I understand how upsetting this situation is, and I'm here to assist you in finding a satisfactory solution. I'm truly sorry for the inconvenience this has caused, and I'm committed to making it right for you. Focus on appreciation and support. As we conclude, I hope I've provided the clarity and solutions you needed. Did I manage to exceed your expectations and leave you satisfied? Before concluding, I hope I've been able to resolve your mobile issue effectively. Did I leave you with a positive experience and a smile? Thank you for your time today. Before we end, can you confirm if I've met your expectations and provided the support you needed for your mobile plan? Before we hang up, I want to ensure you're fully satisfied with the troubleshooting provided. Did I manage to make your experience positive? As our conversation comes to a close, I hope I was able to meet your needs. Did I manage to resolve your issue and leave you satisfied? Number 2, highlight resolution and feedback. I'm glad we were able to resolve your issue today. To help us improve our service, would you be willing to take a brief survey about your experience? Number 3, focus on value and future benefits. This plan optimizes your budget and future-proofs your mobile experience with features that adapt to your evolving needs. Are you ready to unlock its potential? 4, highlighting expertise and confidence. Selecting the optimal plan can be intricate. With my expertise, I've guided you towards a solution that delivers the most value and functionality for your specific needs. appealing to efficiency and exclusivity. Let's streamline the process. Choosing this plan today eliminates countless hours of research and comparison. We've done the work for you, ensuring you receive the best possible solution. Building trust and positive resolution. I understand this issue can be frustrating. Rest assured this solution addresses the root cause and ensures a smoother mobile experience moving forward. Are there any other concerns I can help with today? 7. Demonstrating expertise and proactive service. By going beyond the immediate issue, we've ensured a stable and efficient mobile experience for the future. Is there anything else you'd like to discuss today? B. We don't just fix problems, we prevent them. This approach not only resolves the current issue but also identifies potential future roadblocks to keep your mobile experience seamless. 8. Focus on future satisfaction and 5-star feedback. We've prioritized a long-term solution that surpasses resolving the immediate issue. By sharing your positive experience through a 5-star survey, you help us continue providing exceptional service. Additional tips: tailor the closing to the specific situation and customer needs. Maintain a clear, confident, and professional tone. Use these closings as a springboard to transition into the next steps: activation, survey, further support. Let us take a look at the design. First, a user gets the IP address of the load balancer from DNS. Second, a user connects the load balancer with this IP address. Third, the HTTP request is routed to either server 1 or server 2. Fourth, a web server reads user data from a slave database. Fifth, a web server routes any data modifying operations to the master database. This includes write, update, and delete operations. Now you have a solid understanding of the web and data tiers. It's time to improve the load or response time. This can be done by adding cache, layer, and shifting static content, JavaScript, or CSS, or image or video files to the Content Delivery Network, or CDN. Cache. A cache is a temporary storage area that stores the result of expensive responses or frequently accessed data in memory so that subsequent requests are served more quickly. As illustrated in figure, every time a new web page loads, one or more database calls are executed to fetch data. The application performance is greatly affected by calling the database repeatedly. The cache can mitigate this problem. Cache tier. The cache tier is a temporary data store layer, much faster than the database. The benefits of having a separate cache tier include better system performance, ability to reduce database workloads, and the ability to scale the cache tier independently. Figure shows a possible setup of a cache server. After receiving a request, a web server first checks if the cache has the available response. If it has, it sends data back to the client. If not, it queries the database, stores the response in cache, and sends it back to the client. This caching strategy is called a read-through cache. Other caching strategies are available depending on the type, size, and access patterns. A previous study explains how different caching strategies work on this article. Interacting with cache servers is simple because most cache servers provide APIs for common programming languages. The following code snippet shows typical Memcache APIs. Seconds equal 1. Cache that set parentheses quote my key without space, comma, quote high space there, comma, 3600 asterisk seconds parentheses. Enter. Next line, cache.get parentheses quote my without space key. Considerations for using cache. Here are a few considerations for using a cache system. Decide when to use cache. Consider using cache when data is read frequently but modified infrequently. Since cache data is stored in volatile memory, a cache server is not ideal for persisting data. For instance, if a cache server restarts, all data in memory is lost. Thus, important data should be saved in persistent data stores. Expiration policy. It is a good practice to implement an expiration policy. Once cache data is expired, it is removed from the cache. When there is no expiration policy, cache data will be stored in the memory permanently. It is advisable not to make the expiration data too short, as this will cause the system to reload data from the database too frequently. Meanwhile, it is advisable not to make the expiration date too long, as the data can become stale. Consistency. This involves keeping the data store and the cache in sync. Inconsistency can happen because data modifying operations on data store and cache are not in a single transaction. When scaling across multiple regions, maintaining consistency between the data store and cache is challenging. For further details, refer to the paper titled Scaling Memcache at Facebook, published by Facebook. Mitigating failures. A single cache server represents a potential single point of failure defined in Wikipedia, as POF is a part of a system that, if it fails, will stop the entire system from working. As a result, multiple cache servers across different data centers are recommended to avoid SPOF. Another recommended approach is to over-provision the required memory by certain percentages. This provides a buffer as the memory usage increases. Eviction policy. Once the cache is full, any request to add items to the cache might cause existing items to be removed. This is called cache eviction. Least recently used LRU is the most popular cache eviction policy. Other eviction policies, such as the least frequently used LFU or first in, first out, can be adapted to satisfy different use. Content Delivery Network. A CDN is a network of geographically dispersed servers used to deliver static content. CDN servers cache static content like images, videos, CSS, JavaScript files, etc. Dynamic content caching is a relatively new concept and beyond the scope of this book. It enables the caching of HTML pages that are based on request path, query strings, cookies, and request headers. Refer to the article mentioned in reference material 9 for more about this. This book focuses on how to use CDN to cache static content. Here is how CDN works at the high level. When a user visits a website, a CDN server closest to the user will deliver static content. Intuitively, the further users are from CDN servers, the slower the website loads. For example, if CDN servers are in San Francisco, users in Los Angeles will get content faster than users in Europe. Figure is a great example that shows how CDN improves load time. First, user A tries to get image.png by using an image URL. The URL's domain is provided by the CDN provider. The following two image URLs are samples used to demonstrate what image URLs look like on Amazon and Akamai CDNs. First, https mysite.cloudfront.net/logo.jpg. Second, https://mysite.akamai.com/image-manager/img/logo.jpg. 2. If the CDN server does not have image.png in the cache, the CDN server requests the file from the origin, which can be a web server or online storage like Amazon S3. 3. The origin returns image.png to the CDN server, which includes optional HTTP header, time to live or TTL, which describes how long the image is cached. 4. The CDN caches the image and returns it to user A. The image remains cached in the CDN until the TTL expires. 5. User B sends a request to get the same image. 6. The image is returned from the cache as long as the TTL has not expired. Considerations of using a CDN. Cost. CDNs are run by third-party providers and you are charged for data transfers in and out of the CDN. Caching infrequently used assets provides no significant benefits, so you should consider moving them out of the CDN. 2. Setting an appropriate cache expiry. For sensitive content, setting a cache expiry time is important. The cache expiry time should neither be too long nor too short. If it's too long, the content might no longer be fresh. If it's too short, it can cause repeat reloading of content from origin servers to the CDN. CDN fallback. You should consider how your website or application copes with CDN failure. If there is a temporary CDN outage, clients should be able to detect the problem and request resources from the origin. Invalidating files. You can remove a file from the CDN before it expires by performing one of the following operations. Invalidate the CDN object using APIs provided by CDN vendors. Second, use object versioning. Use object versioning to serve a different version of the object. To version an object, you can add parameter to the URL, such as a version number. For example, version number 2 is added to the query string :image.png ?v equal to. Figure shows the design after the CDN and cache are added. First, static assets, JS, CSS, images, etc. are no longer served by web servers. They are fetched from the CDN for better performance. Second, the database load is lightened by caching data. Stateless web tier. Now it's time to consider scaling the web tier horizontally. For this, we need to move state, for instance, user session data, out of the web tier. A good practice is to store sessions data in the persistent storage such as relational database or NoSQL. Each web server in the cluster can access state data from databases. This is called stateless web tier. Stateful architecture. A stateful server and stateless server has some key differences. A stateful server remembers client data from one request to the next. A stateless server keeps no state information. Figures show an example of stateful full architecture. In figure, user A's session data and profile image are stored in server 1. To authenticate user A, HTTP request must be stored to server 1. If a request is sent to other servers like server 2, authentication would fail because server 2 does not contain user A's session data. Similarly, all HTTP requests from user B must be routed to server 2. All requests from user C must be sent to server 3. The issue is that every request from the same client must be routed to the same server. This can be done with sticky sessions in most load balancer. However, this adds the overhead. Adding or removing servers is much more difficult with this approach. It is also challenging to handle server failures. Stateless architecture. Figure shows the stateless architecture. In this stateless architecture, HTTP requests from users can be sent to any web service which fetch state data from a shared data store. State data is stored in a shared data store and kept out of web servers. A stateless system is simpler, more robust, and scalable. Figure shows the updated design with stateless web tier. In figure, we move the session data out of the web tier and store them in the persistent data store. The shared data store could be a relational database, Memcache or Redis, NoSQL, etc. The NoSQL data store is chosen as it is easy to scale. Autoscaling means adding or removing web servers automatically based on the traffic load. After the state data is removed out of web servers, autoscaling of the web tier is easily achieved by adding or removing servers based on traffic load. Your website grows rapidly and attracts a significant number of users internationally. To improve your availability and provide a better user experience across wider geographical areas, supporting multiple data centers is crucial. Data centers. Figure shows an example setup with 2 data centers. In normal operation, users are GeoDNS routed, also known as Geo routed, to the closest data center with a split traffic of X% in US East and parenthesis 100 minus X% in US West. GeoDNS is a DNS service that allows domain names to be resolved to IP addresses based on the location of a user. In the event of any significant data center outage, we direct all traffic to a healthy data center. In figure, data center 2, US West is offline and 100% of traffic is routed to data center 1, which is US East. Several technical challenges must be resolved to achieve multi-data center setup. First, traffic redirection. Effective tools are needed to direct traffic to the correct data center. GeoDNS can be used to direct traffic to the nearest data center, depending on where a user is located. Data synchronization. Users from different regions could use different local databases or caches. In failover cases, traffic might be routed to a data center where data is unavailable. A common strategy is to replicate data across multiple data centers. A previous study shows how Netflix implements asynchronous multi-data center replication. 3. Test and deployment. With multi-data center setup, it is important to test your website or application at different locations. Automated deployment tools are vital to keep services consistent through all data centers. To further scale our system, we need to decouple different components of the system so they can be scaled independently. Messaging queue is a key strategy employed by many real-world distributed systems to solve this problem. Design a notification system. A notification system has already become a very popular feature for many applications in recent years. A notification alerts a user with important information like breaking news, product updates, events, offerings, etc. It has become an indispensable part of our daily life. In this chapter, you are asked to decide notification system. A notification is more than just mobile push notification. Three types of notification formats are mobile push notifications, SMS message, and email. Figure shows an example of each notification. Step 1. Understand the problem and establish design scope. Building a scalable system that sends out millions of notifications a day is not an easy task. It requires a deep understanding of notification ecosystem. The interview question is purposely designed to be open-ended and ambiguous, and it is your responsibility to ask questions to clarify the requirements. Candidate: what types of notification does the system support? Interviewer: push notification, SMS message, and email. Candidate: is it a real-time system? Interviewer: let us say it is a soft real-time system. We want the user to receive notifications as soon as possible. However, if the system is under a high workload, a slight delay is acceptable. Candidate: what are the supported devices? Interviewer: iOS devices, Android devices, and laptop or desktop. Candidate: what triggers notifications? Interviewer: notifications can be triggered by client applications. They can also be scheduled on the server side. Candidate: will user be able to opt out? Interviewer: yes. Users who choose to opt out will no longer receive notifications. Candidate: how many notifications are sent out each day? Interviewer: 10 million mobile push notifications, 1 million SMS messages, and 5 million emails. Step 2. Propose high-level design and get buy-in. The section shows the high-level design that supports various notification types: iOS push notification, Android push notifications, SMS message, and email. It is structured as follows: different types of notifications, contact info gathering flow, notification sending or receiving flow. Different types of notifications. We start by looking at how each notification type works at high level. iOS push notifications. We primarily need three components to send an iOS push notifications. Provider. A provider builds and sends notification requests to Apple push notification service. To construct a push notification, the provider provides the following data: device token. This is a unique identifier used for sending push notifications. Payload. This is a JSON dictionary that contains a notifications payload. Here is an example. APS, open bracket, alert, open bracket, title, : game request, body, Bob wants to play chess. Action lock key play. Close parenthesis, budge 5 close parenthesis. APNs. This is a remote service provided by Apple to propagate push notifications to iOS devices. iOS device. It is the end client which receives push notifications. Android push notification. Android adopts a similar notification flow. Instead of using APNs, Firebase Cloud Messaging or FCM is commonly used to send push notifications to Android devices. SMS message. For SMS messages, third-party SMS services like Twilio, Nexmo, and many others are commonly used. Most of them are commercial services. Email. Although companies can set up their own email servers, many of them opt for commercial email services. SendGrid and MailChimp are among the most popular email services, which offer a better delivery rate and data analytics. Figure shows the design after including all third-party services. Contact info gathering flow. To send notifications, we need to gather mobile device tokens, phone numbers, or email addresses. As shown in figure, when a user installs our app or signs up for the first time, API servers collect user contact info and store it in the database. Figure shows simplified database tables to store contact info. Email addresses and phone numbers are stored in the user table, whereas device tokens are stored in the device table. A user can have multiple devices, indicating that a push notification can be sent to all user devices. Notification sending or receiving flow. We will first present the initial design, then propose some optimizations. High-level design. Figure shows the design and each system component is explained below. Service 1 to N. A service can be a microservice, a cron job, or a distributed system that triggers notification sending events. For example, a billing service sends emails to remind customers of their due payment, or a shopping website tells the customers that their packages will be delivered tomorrow via SMS messages. Notification system. The notification system is the centerpiece of sending or receiving notifications. Starting with something simple, only one notification server is used. It provides APIs for services 1 to N and builds notification payloads for third-party services. Third-party services. Third-party services are responsible for delivering notifications to users. While integrating with third-party services, we need to pay extra attention to extensibility. Good extensibility means a flexible system that can easily plugging or unplugging of a third-party service. Another important consideration is that a third-party service might be unavailable in new markets or in the future. For instance, FCM is unavailable in China. Thus, alternative third-party services such as Gpush, PushY, etc. are used there. iOS, Android, SMS, email. Users receive notifications on their devices. 3 problems are identified in this design. Single point of failure. A single notification server means SPOF. Hard to scale. The notification system handles everything related to push notifications in one server. It is challenging to scale databases, caches, and different notification processing components independently. Performance bottleneck. Processing and sending notifications can be resource intensive. For example, constructing HTML pages and waiting for responses from third-party services could take time. Handling everything in one system can result in the system overload, especially during peak hours. High-level design improved. After enumerating challenges in the initial design, we improved the design as listed below. Move the database and cache out of the notification server. Add more notification servers and set up automatic horizontal scaling. Introduced message queues to decouple the system components. Figure shows the improved high-level design. The best way to go through the above diagram is from left to right. Service 1 to N. They represent different services that send notifications via APIs provided by notification servers. Notification servers. They provide the following functionalities. Provide APIs for services to send notifications. Those APIs are only accessible internally or by verified clients to prevent spams. Carry out basic validations to verify emails, phone numbers, etc. Query the database or cache to fetch data needed to render a notification. Put notification data to message queues for parallel processing. Here is an example of the API to send an email. Post https api.api.example.com/api/v/sms/send. Request body open bracket to open bracket user dash id 123456 close bracket from open bracket email from dash address at example.com close bracket subject hello world content open bracket type text or plain value hello world exclamation closing bracket. Cache, user info, device info, notification templates are cache. DB, it stores data about user, notification, settings, etc. Message queues, they remove dependencies between components. Message queue serve as buffers when high volumes of notifications are to be sent out. Each notification type is assigned with a distinct message queue, so an outage in one third-party service will not affect other notification types. Workers. Workers are a list of servers that pull notifications events from message queues and send them to the corresponding third-party services. Third-party services, already explained in the initial design. iOS, Android, SMS, email, already explained in the initial design. Next, let us examine how every component works together to send a notification. First, a service calls APIs provided by notification servers to send notifications. Second, notification servers fetch metadata such as user info, device token, and notification setting from the cache or database. Third, a notification event is sent to the corresponding queue for processing. For instance, an iOS push notification event is sent to the iOS PN queue. Fourth, workers pull notification events from message queues. Fifth, workers send notifications to third-party services. Sixth, third-party services send notifications to user devices. Step 3. Design deep dive. In the high-level design, we discuss different types of notifications, contact info gathering flow, and notification sending or receiving flow. We will explore the following in deep dive: reliability, additional component and considerations, notification template, notification settings, rate limiting, retry mechanism, security in push notifications, monitor queued notifications, and event tracking. Updated design. Reliability. We must answer a few important reliability questions when designing a notification system in distributed environments. How to prevent data loss. One of the most important requirements in a notification system is that it cannot lose data. Notifications can usually be deleted or reordered, but never lost. To satisfy this requirement, the notification system persists notification data in a database and implements a retry mechanism. The notification log database is included for data persistence, as shown in figure. Will recipients receive a notification exactly once? The short answer is no. Although notification is delivered exactly once most of the time, the distributed nature could result in duplicate notifications. To reduce the duplication occurrence, we introduce the dupe mechanism and handle each failure case carefully. Here is a simple dedupe logic. When a notification event first arrives, we check if it is seen before by checking the event ID. If it is seen before, it is discarded. Otherwise, we will send out notification for interested readers to explore why we cannot have exactly once delivery. Refer to the reference material. Additional components and considerations. We have discussed how to collect user contact info, send and receive a notification. A notification system is a lot more than that. Here, we discuss additional components including template reusing, notification settings, event tracking, system monitoring, rate limiting, etc. Notification template. A large notification system sends out millions of notifications per day, and many of these notifications follow a similar format. Notification templates are introduced to avoid building every notification from scratch. A notification template is a pre-formatted notification to create your unique notification by customizing parameters, styling, tracking links, etc. Here is an example template of push notifications. Body, colon, next line, you dreamed of it, we dare it, period, open bracket, item space name, close bracket, is back, dash, only until, open bracket, date, close bracket. Next line, CTA, colon, next line, order now. Or, save my, Item name. The benefits of using notification templates include maintaining a consistent format, reducing the margin error, and saving time. Notification setting. Users generally receive way too many notifications daily, and they can easily feel overwhelmed. Thus, many websites and apps give users fine-grained control over notification settings. This information is stored in the notification setting table with the following fields: user-id space big int without space, next line channel space varchar space hashtag push notification, email or SMS. Next line op underscore in space boolean space hashtag op dash in to receive notification. Before any notification is sent to a user, we first check if a user is opted in to receive this type of notification. Configuring and maintaining server functions and features. Network interface or output queue length. The number of packets in the output queue. If this value is over 2, the NIC is not keeping with the workload. Central Processing Unit. Consult the vendor's documentation for information on those counters and what they mean to the performance of the service or application. Common counters monitored by server administrators include processor or processor time, the percentage of time the CPU spends executing a non-idle thread. This should not be over 85% on a sustained basis. Processor's user time represents the percentage of time the CPU spends in user mode, which means it is doing work for an application. If this value is higher than the baseline you captured during normal operation, the service or application is dominating the CPU. Processor or interrupt time, system or processor queue length, the number of threads, which are smaller pieces of an overall operation in the processor queue. If this value is over 2 times the number of CPUs, the server is not keeping up with the workloads. Event logs. Server create log files that record system events, both normal and abnormal. In this section, you'll learn about log management issues and how to ensure that event data is there when you need it. Configuration. You can control the behavior of log files in Windows in several ways. Even if you are using the logs, and you shouldn't allow them to slowly eat up all the space. First, you can limit the amount of space used for each log. Second, you can determine the behavior when the log is full. Third, you can choose to save a log for later viewing. To set the maximum size for a log file, access the properties of the log in Event Viewer. In the maximum log size option, use the spinner control to set the value you want and click OK. To determine what happens when the log is full, access the same dialog box shown in Figure 2.12 and select one of the 3 options. Overwrite events as needed. All these events first. Archive the log when full. Do not overwrite events. Do not overwrite events. Clear logs manually. This can also be done at the command line using the following. The R parameter specifies whether you want to retain the log, and the AB parameter specifies whether to automatically back up the log. Shipping. Log shipping is the implementation of an automated system to back up the transaction log files on a primary database server and then restoring them onto a standby server. A transaction log is a history of actions executed by a database management system used to guarantee that updates that have not yet been committed are saved even in the face of an improper shutdown. Alerting. Usually they are created by implementing a query that searches for events of a certain type and then sets an alert when it finds this. If in event viewer, this is done by attaching a task to the log. Reporting. In some cases, you want to create a report based off the log data you have collected, perhaps to make a presentation to upper management. While there are third-party tools for this, you can also simply pipe the results to a properly formatted table displaying the information you need. Retention or rotation. As you learned earlier, you can control the retention period and the action to be taken when a log is full. Data migration and transfer. Moving data around from digital location to a location can be called either a migration or a transfer. In this section, you'll learn some concepts and considerations related to moving data around. Infiltration or exfiltration. These two terms are used to describe the direction of the data transfer with respect to your organizational network. Data infiltration is when data enters your network. Exfiltration is when data exits your network. For example, a malicious infiltration is when malware gets in the network, whereas malicious exfiltration is when sensitive data exits the network. Rate limiting. To avoid overwhelming users with too many notifications, we can limit the number of notifications a user can receive. This is important because receivers could turn off notifications completely if we send too often. Retry mechanism. When a third-party service fails to send a notification, the notification will be added to the message queue for retrying. If the problem persists, an alert will be sent out to the developers. Security in push notifications. For iOS or Android apps, AppKey and AppSecret are used to secure push notifications, APIs. Only authenticated or verified clients are allowed to send push notifications using our APIs. Interested users should refer to the reference material. Monitor queued notifications. A key metric to monitor is the total number of queued notifications. If the number is large, the notifications events are not processed fast enough by workers. To avoid delay in the notification delivery, more workers are needed. Figure shows an example of queued messages to be processed. Events tracking. Notifications metrics such as open rate, click rate, and engagement are important in understanding customer behaviors. Analytics service implements events tracking. Integration between the notification system and the analytics service is usually required. Figure shows an example of events that might be tracked for analytic purposes. Updated design, putting everything together. Figure shows updated notification system design. In this design, many new components are added in comparison with the previous design. The notification servers are equipped with two more critical features: authentication and rate limiting. We also add a retry mechanism to handle notification failures. If the system fails to send notifications, they are put back in the messaging queue and the workers will retry for a predefined number of times. Furthermore, Notification templates provide a consistent and efficient notification creation process. Finally, monitoring and tracking systems are added for system health checks and future improvements. Step 4. Wrap up. Notifications are indispensable because they keep us posted with important information. It could be a push notification about your favorite movie on Netflix, an email about discounts on new products, or a message about your online shopping payment confirmations. In this chapter, we describe the design of scalable notification system that supports multiple notification formats: push notification, SMS message, and email. We adapted message queues to decouple system components. Besides the high-level design, we dug deep into more components and optimizations. Reliability. We propose a robust retry mechanism to minimize the failure rate. Security. App key or app secret pair is used to ensure only verified clients can send notifications. Tracking and monitoring. These are implemented in any stage of notification flow to capture important stats. Respect user settings. Users may opt out of receiving notifications. Our system checks user settings first before sending notifications. Rate limiting. Users will appreciate a frequency capping on the number of notifications they receive. Chapter 9. Design a web crawler. In this chapter, we focus on web crawler design, an interesting and classic system design interview question. A web crawler is known as robot or spider. It is widely used by search engines to discover new or updated content on the web. Content can be a web page, an image, a video, a PDF file, etc. A web crawler starts by collecting a few web pages and then follow links on those pages to collect new content. Figure shows a visual example of the crawl process. A crawler is used for many purposes. Search engine indexing. This is the most common use case. A crawler collects web pages to create local index for search engines. For example, Googlebot is the web crawler behind the Google search engine. Web archiving. This is the process of collecting information from the web to preserve data for future uses. For instance, many national libraries run crawlers to archive websites. Notable examples are the US Library of Congress and the EU Web Archive. Web mining. The explosive growth of the web presents an unprecedented opportunity for data mining. Web mining helps discover useful knowledge from the internet. For example, top financial firms use crawlers to download shareholder meetings and annual reports to learn key company initiatives. Web monitoring. The crawlers help to monitor copyright and trademark infringements over the internet. For example, Digimarc utilizes crawlers to discover pirated works and reports. The complexity of developing a web crawler depends on the scale we intend to support. It could be either a small school project, which takes only a few hours to complete, or gigantic project that requires continuous improvement from a dedicated engineering team. Thus, we will explore the scale and features to support below. Step 1. Understand the problem and establish design scope. The basic algorithm of a web crawler is simple. 1. Given a set of URLs, Download all the web pages addressed by the URLs. 2. Extract URLs from these web pages. 3. Add new URLs to the list of URLs to be downloaded. Repeat these 3 steps. Does a web crawler work truly as simple as this basic algorithm? Not exactly. Designing a vastly scalable web crawler is an extremely complex task. It is unlikely for anyone to design a massive web crawler within the interview duration. Before jumping into the design, we must ask questions to understand the requirements and establish design scope. Candidate, what is the main purpose of the crawler? Is it used for search engine indexing, data mining, or something else? Interviewer, search engine indexing. Candidate, how many web pages does the web crawler collect per month? Interviewer, 1 billion pages. Candidate, what content types are included? HTML only or other content types such as PDFs and images as well. Interviewer, HTML only. Candidate, shall we consider newly added or edited web pages? Interviewer, yes, we should consider the newly added or edited web pages. Candidate, do we need to store HTML pages scrolled from the web? Interviewer, yes, up to 5 years. Candidate, how do we handle web pages with duplicate content? Interviewer, pages with duplicate contents should be ignored. Above are some of the sample questions that you can ask your interviewer. It is important to understand the requirements and clarify ambiguities. Even if you are asked to design a straightforward product like a web crawler, you and your interviewer may not have the same assumptions. Besides functionalities to clarify with your interviewer, it is also important to note down the following characteristics of a good web crawler. Scalability. The web is very large. There are billions of web pages out there. Web crawling should be extremely efficient using parallelization. Robustness. The web is full of traps. Bad HTML, unresponsive servers, crashes, malicious links, etc. are all common. The crawler must handle all those edge cases. Politeness. The crawler should not make too many requests to a website within a short time interval. Extensibility. The system is flexible so that minimal changes are needed to support new content types. For example, if we want to crawl image files in the future, we should not need to redesign the entire system. Back of the envelope estimation. The following estimations are based on many assumptions, and it is important to communicate with the interviewer to be on the same page. Assume 1 billion web pages are downloaded every month. QPS, 1 billion over 30 days, over 24 hours, over 3,600 seconds, equal 400 pages per second. Peak QPS equal 2 times QPS equal 800. Assume the average web page size is 500K. 1 billion page times 500K equals 500 terabyte storage per month. If you are unclear about digital storage units, go through Power of 2 section in Chapter 2 again. Assuming data are stored for 5 years, 500 terabyte times 12 months times 5 years equal 30 petabytes. A 30 petabyte storage is needed to store 5-year content. Design YouTube. In this chapter, you are asked to design YouTube. The solution to this question can be applied to other interview questions like designing video sharing platforms such as Netflix and Hulu. Figure shows the YouTube homepage. YouTube looks simple. Content creators upload videos and viewers click play. Is it really that simple? Not really. There are lots of complex technologies underneath the simplicity. let us look at some impressive statistics, demographics, and fun facts of YouTube in 2020. Total number of monthly active users 2 billion. Number of videos watched per day 5 billion. 73% of US adults use YouTube. 50 million creators on YouTube. YouTube's ad revenue was 15.1 billion for the full year 2019, up 36% from 2018. YouTube is responsible for 37% of all mobile internet traffic. YouTube is available in 80 different languages. From these statistics, we know YouTube is enormous, global, and makes a lot of money. Step 1. Understand the problem and establish design scope. As revealed in figure, besides watching a video, you can do a lot more on YouTube. For example, comment, share, or like a video, save a video to playlists, subscribe to a channel, etc. It is impossible to design everything within a 45 or 60-minute interview. Thus, it is important to ask questions to narrow down the scope. Candidate, what features are important? Interviewer, ability to upload the video and watch a video. Candidate, what clients do we need to support? Interviewer, mobile apps, web browsers, and smart TV. Candidate, how many daily active users do we have? Interviewer, 5 million. Candidate, what is the average daily time spent on the product? Interviewer, 30 minutes. Candidate, do we need to support international users? Interviewer, yes. A large percentage of users are international users. Candidate, what are the supported video resolutions? Interviewer, the system accepts most of the video resolutions and formats. Candidate, is encryption required? Interviewer, yes. Candidate, any file size requirement for videos? Interviewer, our platform focuses on small and medium-sized videos. The maximum allowed video size is 1 GB. Candidate, can we leverage some of the existing cloud infrastructures provided by Amazon, Google, or Microsoft? Interviewer, that is a great question. Building everything from scratch is unrealistic for most companies. It is recommended to leverage some of the existing cloud services. In the chapter, we focus on designing a video streaming service with the following features: ability to upload videos fast, smooth video streaming, ability to change video quality, low infrastructure cost, high availability, scalability, and reliability requirements. Client-supported, mobile apps, web browser, and smart TV. Back-of-the-envelope estimation. The following estimations are based on many assumptions, so it's important to communicate with the interviewer to make sure she is on the same page. Assume the product has 5 million daily active users. Users watch 5 videos per day. 10% of users upload 1 video per day. Assume the average video size is 300 megabytes. Total daily storage space needed, 5 million times 10% times 300 megabytes equal 150 petabytes. CDN cost. When cloud CDN serves a video, you are charged for data transferred out of the CDN. Let us use Amazon CDN CloudFront for cost estimation. Assume 100% traffic is served from the United States. The average cost per GB is $0.02. For simplicity, we only calculate the cost of video streaming. 5 million times 5 videos times 0.3 gigabytes times $0.02 equal 150,000 per day. From the rough cost estimation, we know serving videos from the CDN costs lots of money. Even though cloud providers are willing to lower the CDN cost significantly for big customers, the cost is still substantial. We will discuss ways to reduce CDN cost in deep dive. Step 2. Propose high-level design and get buy-in. As discussed previously, the interviewer recommended leveraging existing cloud services instead of building everything from scratch. CDN and blob storage are the cloud services we will leverage. Some readers might ask, why not building everything by yourselves? Reasons are listed below. System design interviews are not about building everything from scratch. Within the limited time frame, choosing the right technology to do a job right is more important than explaining how technology works in detail. For instance, mentioning blob storage for storing source videos is enough for the interviews. Talking about detailed design for blob storage could be an overkill. Building scalable blob storage or CDN is extremely complex and costly. Even large companies like Netflix or Facebook do not build everything themselves. Netflix leverages Amazon's cloud services and Facebook uses Akamai CDN. At the high level, the system comprises three components. Client, you can watch YouTube on your computer, mobile phone, and smart TV. CDN, videos are stored in CDN. When you press play, a video is streamed from the CDN. API servers, everything else except video streaming goes through API servers. This includes feed recommendation, generating video upload URL, updating metadata database and cache, user signup, etc. In the question or answer session, the interviewer showed interest in two flows: video uploading flow, video streaming flow. We will explore high-level design for each of them. Video uploading flow. Figure shows the high-level design for the video uploading. It consists of the following components. User. A user watches YouTube on devices such as a computer, mobile phone, or smart TV. Load balancer. A load balancer evenly distributes requests among API servers. API servers. All user requests go through API servers except video streaming. Metadata DB. Video metadata are stored in Metadata DB. It is sharded and replicated to meet performance and high availability requirements. Metadata cache. For better performance, video metadata and user objects are cached. Original storage. A blob storage system is used to store original videos. A quotation in Wikipedia regarding blob storage shows that a binary large object is a collection of binary data stored as a single entity in a database management system. Transcoding servers. Video transcoding is called video encoding. It is the process of converting a video format to other formats, MPEG, HLS, etc., which provides the best video streams possible for different devices and bandwidth capabilities. Transcoded storage. It is a blob storage that stores transcoded video files. CDN. Videos are cached in CDN. When you click the play button, a video is streamed from the CDN. Completion queue. It is a message queue that stores information about video transcoding completion events. Completion handler. This consists of a list of workers that pull event data from the completion queue and update metadata cache and database. Now that we understand each component individually, let us examine how the video's uploading flow works. The flow is broken down into two processes running in parallel. A. Upload the actual video. B. Update video metadata. Metadata contains information about video URL, size, resolution, format, user info, etc. Flow A. Upload the actual video. Figure shows how to upload the actual video. The explanation is shown below. First, videos are uploaded to the original storage. Second, transcoding servers fetch videos from the original storage and start transcoding. Third, once transcoding is complete, the following two steps are executed in parallel. 3A. Transcoded videos are sent to transcoded storage. 3B. Transcoding completion events are queued in the completion queue. 3A.1. Transcoded videos are distributed to CDN. 3B.1. Completion handler contains a bunch of workers that continuously pull event data from the queue. 3B.1.A and 3B.1.B. Completion handler updates the metadata database and cache when video transcoding is complete. 4. API servers inform the client that the video is successfully uploaded and is ready for streaming. Flow B. Update the metadata. While a file is being uploaded to the original storage, the client in parallel sends a request to update the video metadata as shown in figure. The request contains video metadata, including file name, size, format, etc. API servers update the metadata cache and database. Video streaming flow. Whenever you watch a video on YouTube, it usually starts streaming immediately and you do not wait until the whole video is downloaded. Downloading means the whole video is copied to your device, while streaming means your device continuously receives video streams from remote source videos. When you watch streaming videos, your client loads a little bit of data at a time so you can watch videos immediately and continuously. Before we discuss video streaming flow, let us look at an important concept: streaming protocol. This is a standardized way to control data transfer for video streaming. Popular streaming protocols are MPEG, DASH. MPEG stands for Moving Picture Expert Group, and DASH stands for Dynamic Adaptive Streaming over HTTP. Apple HLS. HLS stands for HTTP Live Streaming. Microsoft Smooth Streaming. Adobe HTTP Dynamic Streaming, or HDS. You do not need to fully understand or even remember those streaming protocol names, as they are low-level details that require specific domain knowledge. The important thing here is to understand that different streaming protocols support different video encoding and playback players. When we design a video streaming service, we have to choose the right streaming protocol to support our use cases. To learn more about streaming protocols, here is an excellent article. Videos are streamed from CDN directly. The edge server closest to you will deliver the video. Thus, there is very little latency. Figure shows a high level of design for video streaming. Step 3. Design Deep Dive. In the high-level design, the entire system is broken down into two parts: video uploading flow and video streaming flow. In this section, we will refine both flows with important optimizations and introduce error handling mechanisms. Video transcoding. When you record a video, the device, usually a phone or camera, gives the video file a certain format. If you want the video to be played smoothly on other devices, the video must be encoded into compatible bit rates and formats. Bit rate is the rate at which bits are processed over time. A higher bit rate generally means higher video quality. High bit rate sims need more processing power and fast internet speed. Video transcoding is important for the following reasons. Raw video consumes large amounts of storage space. An hour-long, high-definition video recorded at 60 frames per second can take up a few hundred gigabytes of space. Many devices and browsers only support certain types of video formats. Thus, it is important to encode the video to different formats for compatibility reasons. To ensure users watch high-quality videos while maintaining smooth playback, it is a good idea to deliver higher resolution video to users who have high network bandwidth and lower resolution video to users who have low bandwidth. Network conditions can change, especially on mobile devices. To ensure a video is played continuously, switching video quality automatically or manually based on network conditions is essential for smooth user experience. Many types of encoding formats are available. However, most of them contain two parts. Container. This is like a basket that contains video file, audio, and metadata. You can tell the container format by the file extension such as .avi, .mov, or .mp4. Codecs. These are compression and decompression algorithms aimed to reduce the video size while preserving the video quality. The most used video codecs are H.264, VP9, and HEVC. Directed acyclic graph or DAG model. Transcoding a video is computationally expensive and time-consuming. Besides, different content creators may have different video processing requirements. For instance, some content creators require watermarks on top of their videos. Some provide thumbnail images themselves, and some upload high-definition videos, whereas others do not. To support different video processing pipelines and maintain high parallelism, it's important to add some level of abstraction and let client programmers define what tasks to execute. For example, Facebook's streaming video engine uses a directed acyclic graph programming model, which defines tasks in stages so they can be executed sequentially or parallelly. In our design, we adopt a similar DAG model to achieve flexibility and parallelism. Figure represents a DAG for video transcoding. In figure, the original video is split into video, audio, and metadata. Here are some of the tasks that can be applied on a video file. Inspection. Make sure videos have good quality and are not malformed. Video encodings. Videos are converted to support different resolutions, codec, bit rates, etc. Figure shows an example of video encoded files. Thumbnail. Thumbnails can either be uploaded by a user or automatically generated by the system. Watermark. An image overlay on top of your video contains identifying information about your video. Video transcoding architecture. The proposed video transcoding architecture that leverages the cloud services is shown in figure. The architecture has 6 main components: preprocessor, DAG scheduler, resource manager, task workers, temporary storage, and encoded video as the output. Let us take a close look at each component. Preprocessor. The preprocessor has 4 responsibilities. First, video splitting. Video stream is split or further split into smaller group of pictures. Alignment. GOP is a group or chunk of frames arranged in a specific order. Each chunk is independently playable unit, usually a few seconds in length. 2. Some old mobile devices or browsers may not support video splitting. Preprocessor split videos by GOP alignment for old clients. 3. DAG generation. The processor generates DAG based on configuration files client programmers write. Figure is a simplified DAG representation which has 2 nodes and 1 edge. This DAG representation is generated from the 2 configuration files below. 4. Cache data. The preprocessor is a cache for segmented videos. For better reliability, the preprocessor stores GOPs and metadata in temporary storage. If video encoding fails, the system could use persisted data for retry operations. DAG scheduler. The DAG scheduler splits a DAG graph into stages of tasks and puts them in the task queue in the resource manager. Figure shows an example of how the DAG scheduler works. As shown in figure, the original video is split into 3 stages. Stage 1, video, audio, and metadata. The video file is further split into 2 tasks in stage 2, video encoding and thumbnail. The audio files require audio encoding as part of the stage 2 tasks. Resource manager. The resource manager is responsible for managing the efficiency of resource allocation. It contains 3 queues and a task scheduler as shown in figure. Task queue. It is a priority queue that contains tasks to be executed. Worker queue. It is a priority queue that contains worker utilization info. Running queue. It contains info about the currently running tasks and workers running the tasks. Task scheduler. It picks the optimal task or worker and instructs the chosen task worker to execute the job. The resource manager works as follows. The task scheduler gets the highest priority task from the task queue. The task scheduler gets the optimal task worker to run the task from the worker queue. The task scheduler instructs the chosen task worker to run the task. The task scheduler binds the task or worker info and puts it in the running queue. The task scheduler removes the job from the running queue once the job is done. Task workers. Task workers run the tasks which are defined in the DAG. Different task workers may run different tasks as shown in figure. Temporary storage. Multiple storage systems are used here. The choice of storage system depends on factors like data type, data size, access frequency, data lifespan, etc. For instance, metadata is frequently accessed by workers, and the data is usually small. Thus, caching metadata in a memory is a good idea. For video or audio data, we put them in blob storage. Data in temporary storage is freed up once the corresponding video processing is complete. Encoded video. Encoded video is the final output of the encoding pipeline. Here is an example of the output. Funny underscore 720p.mp4. System optimizations. At this point, you ought to have a good understanding about the video uploading flow, video streaming flow, and video transcoding. Next, we will refine the system with optimizations, including speed, safety, and cost saving. Speed optimization. Parallelize video uploading. Uploading a video as a whole unit is inefficient. We can split a video into smaller chunks by GOP alignment as shown in figure. This allows fast resumable uploads when the previous upload failed. The job of splitting a video file by GOP can be implemented by the client to improve the upload speed as shown in figure. Speed optimization. Place upload centers close to users. Another way to improve the upload speed is by setting multiple upload centers across the globe. People in the US can upload videos to North America Upload Center, and people in China can upload videos to the Asian Upload Center. To achieve this, we use CDN as upload centers. Speed optimization. Parallelism everywhere. Achieving low latency requires serious efforts. Another optimization is to build a loosely coupled system and enable high parallelism. Our design needs some modifications to achieve high parallelism. Let us zoom in to the flow of how a video is transferred from original storage to the CDN. The flow is shown in figure, revealing that the output depends on the input of the previous step. This dependency makes parallelism difficult. To make the system more loosely coupled, we introduce message queues as shown in figure. Let us use an example to explain how message queues make the system more loosely coupled. Before the message queue is introduced, the encoding module must wait for the output of the download module. After the message queue is introduced, the encoding module does not need to wait for the output of the download module anymore. If there are events in the message queue, the encoding module can execute those jobs in parallel. Safety optimization. Pre-signed upload URL. Safety is one of the most important aspects of any product. To ensure only authorized users upload the videos to the right location, we introduce pre-signed URLs as shown in figure. The upload flow is updated as follows. First, the client makes a HTTP request to API servers to fetch the pre-signed URL, which gives the access permission to the object identified in the URL. The term pre-signed URL is used by uploading files to Amazon S3. Other cloud service providers might use a different name. For instance, Microsoft Azure Blob Storage supports the same feature but called it Shared Access Signature. Second, API servers respond with a pre-signed URL. Third, once the client receives the response, it uploads the video using the pre-signed URL. Safety optimization. Protect your videos. Many content makers are reluctant to post videos online because they fear their original videos will be stolen. To protect copyrighted videos, we can adopt one of the following three options. Digital rights management systems. Three major DRM systems are Apple, Fairplay, Google, Widevine, and Microsoft PlayReady. AES encryption. You can encrypt a video and configure an authorization policy. The encrypted video will be encrypted upon playback. This ensures that only authorized users can watch an encrypted video. Visual watermarking. This is an image overlay on top of your video that contains identifying information for your video. It can be your company logo or company name. Cost-saving optimization. CDN is a crucial component of our system. It ensures fast video delivery on a global scale. However, from the back of the envelope calculation, we know CDN is expensive, especially when the data size is large. How can we reduce the cost? Previous research shows that YouTube video streams follow long-tail distribution. It means a few popular videos are accessed frequently, but many others have few or no viewers. Based on this observation, we implement a few optimizations. First, only serve the most popular videos from CDN and other videos from our high-capacity storage video servers. Second, for less popular content, we may not need to store many encoded video versions. Short videos can be encoded on demand. Third, some videos are popular only in certain regions. There is no need to distribute these videos to other regions. Fourth, build your own CDN like Netflix and partner with internet service providers. Building your CDN is a giant project. However, this could make sense for large streaming companies. An ISP can be Comcast, AT&T, Verizon, or other internet providers. ISPs are located all around the world and are close to users. By partnering with ISPs, you can improve the viewing experience and reduce the bandwidth charges. All those optimizations are based on content popularity, user access pattern, video size, etc. It is important to analyze historical viewing patterns before doing any optimization. Here are some of the interesting articles on this topic. Error handling. For a large-scale system, system errors are unavoidable. To build a highly fault-tolerant system, we must handle errors gracefully and recover from them fast. Two types of errors exist. Recoverable error. For recoverable errors such as video segment fails to transcode, the general idea is to retry the operation a few times. If the task continues to fail and the system believes it is not recoverable, it returns a proper error code to the client. Non-recoverable error. For non-recoverable errors such as malformed video format, the system stops the running task associated with the video and returns the proper error code to the client. Typical errors for each system component are covered by the following playbook. Upload error, retry a few times. Split video error. If older versions of clients cannot split videos by GOP alignment, the entire video is passed to the server. The job of splitting videos is done on the server side. Transcoding error, retry, preprocessor error, regenerate DOG diagram, DOG scheduler error, reschedule a task, resource manager queue down, use a replica, task worker down, retry the task on a new worker, API server down. API servers are stateless, so request will be directed to a different API server. Metadata cache server down. Data is replicated multiple times. If one node goes down, you can still access other nodes to fetch data, we can bring up new cache server to replace the dead one. Metadata DB server down. Master is down. If the master is down, promote one of the slaves to act as the new master. Slave is down. If a slave is down, you can use another slave for reads and bring up another database server to replace the dead one. Step 4. Wrap up. In this chapter, we presented the architecture design for video streaming services like YouTube. If there is extra time at the end of the interview, here are a few additional points. Scale the API tier. Because API servers are stateless, it is easy to scale API tier horizontally. Scale the database. You can talk about database replication and sharding. Live streaming. It refers to the process of how a video is recorded and broadcasted in real time. Although our system is not designed specifically for live streaming and non-live streaming have some similarities. Both require uploading, encoding, and streaming. The notable differences are live streaming has higher latency requirement, so it might need a different streaming protocol. Live streaming has lower requirement for parallelism because small chunks of data are already processed in real time. Live streaming requires different sets of error handling. Any error handling that takes too much time is not acceptable. Video takedowns. Videos that violate copyrights, pornography, or other illegal acts shall be removed. Some can be discovered by the system during the upload process, while others might be discovered through user flagging. Design a chat system. In this chapter, we explore the design of a chat system. Almost everyone uses a chat app. Figure shows some of the most popular apps in the marketplace. A chat app performs different functions for different people. It is extremely important to nail down the exact requirements. For example, you do not want to design a system that focuses on group chat when the interviewer has one-on-one chat in mind. It is important to explore the feature requirements. Step 1. Understand the problem and establish design scope. It is vital to agree on the type of chat app to design. In the marketplace, there are one-on-one chat apps like Facebook Messenger, WeChat, and WhatsApp. Office chat apps that focus on group chat like Slack, or game chat apps like Discord that focus on large group interaction and low voice chat latency. The first set of clarification questions should nail down what the interviewer has in mind exactly when she asks you to design a chat system. At the very least, figure out if you should focus on a one-on-one chat or group chat app. Some questions you might ask are as follows. Candidate, what kind of chat app shall we design? One-on-one or group-based? Interviewer, it should support both one-on-one and group chat. Candidate, is this a mobile app or a web app or both? Interviewer, both. Candidate, what is the scale of this app? A startup app or massive scale? Interviewer, it should support 50 million daily active users. Candidate, for group chat, what is the group member limit? Interviewer, a maximum of 100 people. Candidate, what features are important for the chat app? Can it support attachment? Interviewer, one-on-one chat, group chat, online indicator. The system only supports text messages. Candidate, is there a message size limit? Interviewer, yes, Text length should be less than 100,000 characters long. Candidate, is end-to-end encryption required? Interviewer, not required for now, but we will discuss that if time allows. Candidate, how long shall we store the chat history? Interviewer, forever. In the chapter, we focus on designing a chat app like Facebook Messenger with an emphasis on the following features: a one-on-one chat with low delivery latency, small group chat, maximum of 100 people, online presence, multiple device support, the same account can be logged in to multiple accounts at the same time, push notifications. It is also important to agree on the design scale. We will design a system that supports 50 million DAU. Step 2. Propose high-level design and get buy-in. To develop a high-quality design, we should have a basic knowledge of how clients and servers communicate. In a chat system, clients can be either mobile applications or web applications. Clients do not communicate directly with each other. Instead, each client connects to a chat service, which supports all the features mentioned above. Let us focus on fundamental operations. The chat service must support the following functions: receive messages from the clients, find the right recipients for each message and relay the message to the recipients. If a recipient is not online, hold the messages for the recipient on the server until she is online. Figure shows the relationship between clients, sender and receiver, and the chat service. When a client intends to start a chat, it connects the chat service using one or more network protocols. For a chat service, the choice of network protocols is important. Let us discuss this with the interviewer. Requests are initiated by the client for most client or server applications. This is also true for the sender side of a chat application. In figure, when the sender sends a message to the receiver via the chat service, it uses the time-tested HTTP protocol, which is the most common web protocol. In this scenario, the client opens a HTTP connection with the chat service and sends the message, informing the service to send the message to the receiver. The keep alive is efficient for this because the keep alive header allows a client to maintain a persistent connection with the chat service. It also reduces the number of TCP handshakes. HTTP is a fine option on the sender side, and many popular chat applications such as Facebook used HTTP initially to send messages. However, the receiver side is a bit more complicated. Since HTTP is client initiated, it is not trivial to send messages from the server. Over the years, many techniques are used to simulate a server-initiated connection: polling, long polling, and WebSocket. Those are important techniques widely used in the system design interviews, so let us examine each of them. Polling. As shown in figure, polling is a technique that client periodically asks the server if there are messages available. Depending on polling frequency, polling could be costly. It could consume precious server resources to answer a question that offers no as an answer most of the time. Long polling. Because polling could be inefficient, the next progression is long polling. In long polling, a client holds the connection open until there are actually new messages available or a timeout threshold has been reached. Once the client receives new messages, It immediately sends another request to the server, restarting the process. Long polling has a few drawbacks. Sender and receiver may not connect to the same chat server. HTTP-based servers are usually stateless. If you use round robin for load balancing, the server that receives the message might not have a long polling connection with the client who receives the message. A server has no good way to tell if a client is disconnected. It is inefficient. If a user does not chat much, long polling still makes periodic connections after timeouts. WebSocket. WebSocket is the most common solution for sending asynchronous updates from server to client. WebSocket connection is initiated by the client. It is bidirectional and persistent. It starts its life as HTTP connection and could be upgraded via some well-defined handshake to a WebSocket connection. Through this persistent connection, a server could send updates to a client. WebSocket connections generally work even if a firewall is in place. This is because they use port 80 or 443, which are also used by HTTP or HTTPS connections. Earlier, we said that on the sender side, HTTP is a fine protocol to use. But since WebSocket is bidirectional, there is no strong technical reason not to use it also for sending. Figure shows how WebSocket is used for both sender and receiver sides. By using WebSocket for both sending and receiving, it simplifies the design and makes implementation on both client and server more straightforward. Since WebSocket connections are persistent, efficient connection management is critical on the server side. High-level design. Just now we mentioned that WebSocket was chosen as the main communication protocol between the client and server for its bidirectional communication. It is important to note that everything else does not have to be WebSocket. Configuring and maintaining server functions and features. Disparate OS data transfer. When copying data from one location to another, you have many data transfer protocol choices. In this section, you'll learn about some of them. RoboCopy. Robust File Copy is a Microsoft command line tool. It has capabilities above and beyond the built-in Windows copy and Xcopy commands. Ability to tolerate network interruptions and resume copy. Ability to copy file and attributes correctly and to preserve original timestamps, as well as NTFS. File transfer. File transfer protocol is both a TCP or IP protocol and software that permits the transferring of files between computer systems. Because FTP has been implemented on numerous types of computer systems, files can be transferred between disparate systems, for example, a personal computer and a mini computer. It uses ports 20 and 21 by default. Fast Copy. Fast Copy is a file and directory copier that runs under Windows. In 2015, Fast Copy version 2.11 was ported to Mac OS X. Secure Copy Protocol. Secure Copy Protocol is a secure method of transferring files from one device to another. It is another example of a protocol that runs over SSH, which actually provides the encryption. Administrative interfaces. Managing a system and making changes can be done either sitting at the system physically or from remote location. Console. By its strictest definition, working from the console means you are physically sitting at the device. Remote desktop. The computer at which you are seated is the client. The computer you're logging into is the server. The server uses its own video driver to create video output and sends the output to the client using RTP. All keyboard and mouse input from the client is encrypted and sent to the server per processing. Secure Shell. If you don't need access to the graphical interface and you just want to connect a server to operate at the command line, you have two options, Telnet and SSH. Web interface. It is also possible to use HTTP to connect to a server. When doing so, typically a special port number is configured for the connections rather than port 80. Some remote administration tools such as remote server administration tools for Windows use HTTP, and in the case of RSOT, the ports used are 5985 and 5986. The purpose of an operation of virtualization. They are saving power, consolidating, and downsizing. Some would say right-sizing their physical footprint and suffering far fewer bottlenecks caused by resource limitations. Host versus guest. The foundation of virtualization is the host device, which may be a workstation or a server. This device is the physical machine that contains the software that makes virtualization possible, and the containers or virtual machines for the guest operating systems. The host provides the underlying hardware and computing resources, such as processing power, memory disk, and network, to the VMs. Each guest is a completely separate and independent instance of an operating system and application software. Some of these actions may include the following: turning off a VM if not in use, taking CPU resources away from one VM and allocating them to another, turning on additional VMs when required to provide fault tolerance. The exact nature of relationship between the hypervisor, the host operating system, and the guest operating systems depends on the type of hypervisor in use. Virtual networking. It is possible to connect VMs together in a network, and that network can be the same network as the LAN or separate from the LAN.
Just now, we mentioned that WebSocket was chosen as the main communication protocol between the client and server for its bidirectional communication. It is important to note that everything else does not have to be WebSocket. In fact, most features, sign up, login, user profile, etc., of a chat application could use the traditional request or response method over HTTP. Let us drill in a bit and look at the high-level components of the system. As shown in figure, the chat system is broken down into three major categories: stateless services, stateful services, and third-party integration. Stateless services. Stateless services are traditional public-facing request or response services used to manage the login, sign up, user profile, etc. These are common features among many websites and apps. Stateless services sit behind a load balancer whose job is to route requests to the correct services based on the request paths. These services can be monolithic or individual microservices. We do not need to build many of these stateless services by ourselves, as there are services in the market that can be integrated easily. The one service that we will discuss more in deep dive is the service discovery. Its primary job is to give the client a list of DNS host names of chat servers that the client could connect to. Stateful service. The only stateful service is the chat service. The service is stateful because each client maintains a persistent network connection to a chat server. In this service, a client normally does not switch to another chat server as long as the server is still available.
The service discovery coordinates closely with the chat service to avoid server overloading. We will go into detail in deep dive. Third-party integration. For a chat app, push notification is the most important third-party integration. It is a way to inform users when new messages have arrived, even when the app is not running. Proper integration of push notifications is crucial. Refer to Chapter 10, Design a Notification System for more information. Scalability. On a small scale, all services listed above could fit in one server, even at the scale we design, for it is in theory possible to fit all user connections in one modern cloud server. The number of concurrent connections that a server can handle will most likely be the limiting factor. In our scenario, at 1 million concurrent users, assuming each user connections need 10K of memory on the server, this is a very rough figure and very dependent on the language choice. It only needs about 10 gigabytes of memory to hold all the connections on one box. If we propose a design where everything fits in one server, this may raise a big red flag in the interviewer's mind. No technologies would design such a scale in a single server. Single server design is a deal breaker due to many factors. The single point of failure is the biggest among them. However, it is perfectly fine to start with a single server design. Just make sure the interviewer knows this is a starting point. Putting everything we mentioned together, figure shows the adjusted high-level design. In figure, the client maintains a persistent WebSocket connection to a chat server for real-time messaging. Chat servers facilitate message sending or receiving. Presence servers manage online or offline status. API servers handle everything including user login, sign up, change profile, etc. Notification servers send push notifications. Finally, the key value store is used to store chat history. When an offline user comes online, she will see all her previous chat history. Storage. At this point, we have servers ready, services up, running, and third-party integrations complete. Deep down, the technical stack is the data layer. Data layer usually requires some effort to get it correct. An important decision we must make is to decide on the right type of database to use. Relational databases or NoSQL databases. To make an informed decision, we will examine the data types and read or write patterns. Two types of data exist in a typical chat system. The first is generic data, such as user profile, setting, user friend list. These data are stored in robust and reliable relational databases. Replication and sharding are common techniques to satisfy availability and scalability requirements. The second is unique to chat systems, chat history data. It is important to understand the read or write pattern. The amount of data is enormous for chat systems. A previous study reveals that Facebook Messenger and WhatsApp process 60 billion messages a day. Only recent chats are accessed frequently. Users do not usually look up for old chats. Although very recent chat history is viewed in most cases, users might use features that require random access of data, such as search, view your mentions, jump to specific messages, etc. These cases should be supported by the data access layer. The read-to-write ratio is about 1:1 for one-on-one chat app. Selecting the correct storage system that supports all of our use cases is crucial. We recommend key value stores for the following reasons. Key value stores allow easy horizontal scaling. Key value stores provide very low latency to access data. Relational databases do not handle long tail of data. Well, when the indexes grow large, random access is expensive. Key value stores are adopted by other proven reliable chat applications. For example, both Facebook Messenger and Discord use key value stores. Facebook Messenger uses HBase and Discord uses Cassandra. Data models. Just now, we talked about using key value stores as our storage layer. The most important data is message data. Let us take a close look. Message table for one-on-one chat. Figure shows the message table for one-on-one chat. The primary key is message-id, which helps us decide message sequence because two messages can be created at the same time. Message table for group chat. Figure shows the message table for group chat. The composite primary key is channel-id, message-id. Channel and group represent the same meaning here. Channel-id is the partition key because all queries in a group chat operate in a channel. How to generate message-id is an interesting topic worth exploring. Message-id carries the responsibility of ensuring the order of messages. To ascertain the order of messages, message-id must satisfy the following two requirements. IDs must be unique. IDs should be sortable by time, meaning new rows have higher IDs than old ones. How can we achieve those two guarantees? The first idea that comes to mind is the auto-increment keyword in MySQL. However, NoSQL databases usually do not provide such a feature. The second approach is to use a global 64-bit sequence number generator like Snowflake. This is discussed in Chapter 7, Design a Unique ID Generator in a Distributed System. The final approach is to use local sequence number generator. Local means IDs are only unique within a group. The reason why local IDs work is that maintaining message sequence within one-on-one channel or a group channel is sufficient. This approach is easier to implement in comparison to the global ID implementation. Step 3. Design deep dive. In a system design interview, usually you are expected to dive deep into some of the components in the high-level design. For the chat system, service discovery, messaging flows, and online or offline indicators worth deeper exploration. Service discovery. The primary role of service discovery is to recommend the best chat server for a client based on the criteria like geographical location, service capacity, etc. Apic Zookeeper is a popular open source solution for service discovery. It registers all the available chat servers and picks the best chat server for a client based on predefined criteria. 1. User A tries to log into the app. 2. The load balancer sends the login request to API servers. 3. After the backend authenticates the user, service discovery finds the best chat server for user A. In this example, server 2 is chosen and the server info is returned back to user A. 4th, user A connects to chat server 2 through WebSocket. Message flows. It is interesting to understand the end-to-end flow of a chat system. In this section, we will explore one-on-one chat flow, message synchronization across multiple devices, and group chat flow. One-on-one chat flow. Figure explains what happens when user A sends a message to user B. First, user A sends a chat message to chat server 1. Second, chat server 1 obtains a message ID from the ID generator. Third, chat server 1 sends the message to the message sync queue. Fourth, the message is stored in a key value store. Fifth A, if user B is online, the message is forwarded to chat server 2 where user B is connected. 5B, if user B is offline, a push notification is sent from push notification servers. Sixth, chat server 2 forwards the message to user B. There is a persistent WebSocket connection between user B and chat server 2. Message synchronization across multiple devices. Many users have multiple devices. We will explain how to sync messages across multiple devices. Figure shows an example of message synchronization. In figure, user A has two devices, a phone and a laptop. When user A logs into the chat app with her phone, it establishes a WebSocket connection with chat server 1. Similarly, there is a connection between the laptop and chat server 1. Each device maintains a variable called cur-max-message-id, which keeps track of the latest message ID on the device. Messages that satisfy the following two conditions are considered as new messages. The recipient ID is equal to the current login user ID. Message ID in the key value store is larger than cur-max-message-id. With distinct cur-max-message-id on each device, message synchronization is easy as each device can get new messages from the KV store. Small group chat flow. In comparison to the one-on-one chat, the logic of group chat is more complicated. Figures explain the flow. Figure explain what happens when user A sends a message in a group chat. Assume there are three members in the group, user A, user B, and user C. First, the message from user A is copied to each group member's message sync queue, one for user B and the second for user C. You can think of the message sync queue as an inbox for a recipient. This design choice is good for a small group chat because it simplifies message sync flow, as each client only needs to check its own inbox to get new messages. When the group number is small, storing a copy in each recipient's inbox is not too expensive. WeChat uses a similar approach and it limits a group to 500 members. However, for groups with a lot of users, storing a message copy for each member is not acceptable. On the recipient side, a recipient can receive messages from multiple users. Each recipient has an inbox message sync queue, which contains messages from different senders. Figure illustrates the design. Online presence. An online presence indicator is an essential feature of many chat applications. Usually, you can see a green dot next to a user's profile picture or username. This section explains what happens behind the scenes. In the high-level design, presence servers are responsible for managing online status and communicating with clients through WebSockets. There are few flows that will trigger online status change. Let us examine each of them. User login. The user login flow is explained in the service discovery section. After a WebSocket connection is built between the client and the real-time service, user A's online status and last-active-at timestamp are saved in the KV store. Presence indicator shows the user is online after she logs in. User logout. When a user logs out, it goes through the user logout flow as shown in figure. The online status is changed to offline in the KV store. The presence indicator shows a user is offline. User disconnection. We all wish our internet connection is consistent and reliable. However, that is not always the case. Thus, we must address this issue in our design. When a user disconnects from the internet, the persistent connection between the client and server is lost. A naive way to handle user disconnection is to mark the user as offline and change the status to online when the connection reestablishes. However, this approach has a major flaw. It is common for users to disconnect and reconnect to the internet frequently in a short time. For example, network connections can be on and off while a user goes through a tunnel. Updating online status on every disconnect or reconnect would make the presence indicator change too often, resulting in poor user experience. We introduce a heartbeat mechanism to solve this problem. Periodically, an online client sends a heartbeat event to presence servers. If presence servers receive heartbeat event within a certain time, say X seconds from the client, a user is considered as online. Otherwise, it is offline. In figure, the client sends a heartbeat event to the server every 5 seconds. After sending 3 heartbeat events, the client is disconnected and does not reconnect within X equal 30 seconds. These numbers are arbitrarily chosen to demonstrate the logic. The online status is changed to offline. Online status fan out. How do user A's friends know about the status changes? Figure 12.19 explain how it works. Present servers use a publish-subscribe model in which each friend pair maintains a channel. When user A's online status changes, it publishes the event to 3 channels, channel A to B, A to C, and A to D. Those 3 channels are subscribed by user B, C, and D, respectively. Thus, it is easy for friends to get online status updates. The communication between clients and servers is through real-time WebSocket. The above design is effective for small user group. For instance, WeChat uses a similar approach because its user group is capped to 500. For larger groups, informing all members about online status is expensive and time-consuming. Assume a group has 100,000 members. Each status change will generate 100,000 events. To solve the performance bottleneck, a possible solution is to fetch online status only when a user enters a group or manually refreshes the friends list. Step 4. Wrap up. In this chapter, we presented a chat system architecture that supports both one-to-one chat and small group chat. WebSocket is used for real-time communication between the client and server. The chat system contains the following components: chat servers for real-time messaging, presence servers for managing online presence, push notification servers for sending push notifications, key value stores for chat history, persistence, and API servers for other functionalities. If you have extra time at the end of the interview, here are additional talking points. Extend the chat app to support media files such as photos and videos. Media files are significantly larger than text in size. Compression, cloud storage, and thumbnails are interesting topics to talk about. End-to-end encryption. WhatsApp supports end-to-end encryption for messages. Only the sender and recipient can read messages. Interested readers should refer to the article in the reference material. Caching messages on the client side is effective to reduce the data transfer between the client and server. Improve load time. Slack built a geographically distributed network to cache users' data, channels, etc. for better load time. Error handling. The chat server error. There might be hundreds of thousands or even more persistent connections to a chat server. If a chat server goes offline, Service Discovery Zookeeper will provide a new chat server for clients to establish new connections with. Message present mechanism. Retry and queuing are common techniques for resending messages. Design a search autocomplete system. When searching on Google or shopping at Amazon, as you type in the search box, one or more matches for the search term are presented to you. This feature is referred to as autocomplete, type ahead, search as you type, or incremental search. Figure presents an example of a Google search showing a list of auto-completed results when dinner is typed into search box. Search autocomplete is an important feature of many products. This leads us to the interview question. Design a search autocomplete system, also called Design Top Key or Design Top Key most search queries. Step 1. Understand the problem and establish design scope. The first step to tackle any system design interview questions is to ask enough questions to clarify requirements. Here is an example of candidate-interviewer interaction. Candidate: is the matching only supported at the beginning of search query or in the middle as well? Interviewer: only at the beginning of a search query. Candidate: how many autocomplete suggestions should the system return? Interviewer: 5. Candidate: how does the system know which 5 suggestions to return? Interviewer: this is determined by popularity, decided by historical query frequency. Candidate: does the system support spell check? Interviewer: no. Spell check or autocorrect is not supported. Candidate: are search queries in English? Interviewer: yes. If time allows at the end, we can discuss multi-language support. Candidate: do we allow capitalization and special characters? Interviewer: no. We assume all search queries have lowercase alphabetic characters. Candidate: how many users use the product? Interviewer: 10 million DAU. Requirements. Here is a summary of the requirements. Fast response time. As a user types a search query, autocomplete suggestions must show up fast enough. An article about Facebook's autocomplete system reveals that the system needs to return results within 100 milliseconds. Otherwise, it will cause stuttering. Relevant. Autocomplete suggestions should be relevant to the search term. Sorted. Results returned by the system must be sorted by popularity or other ranking models. Scalable. The system can handle high traffic volume. High available. The system should remain available and accessible when part of the system is offline, slows down, or experiences unexpected network errors. Back of the envelope estimation. Assume 10 million daily active users. An average person performs 10 searches per day, 20 bytes of data per query string. Assume we use ESC2 character encoding, 1 character equal 1 byte. Assume query contains 4 words, and each word contains 5 characters on average. That is 4 times 5 equal 20 bytes per query. For every character entered into the search box, a client sends a request to the backend for autocomplete suggestions. On average, 20 requests are sent for each search query. For example, the following 6 requests are sent to the backend by the time you finish typing dinner. Search Q equals C. Search Q equal DI. Search Q equal DIN. Search Q equal DINN. Search Q equal DINNE. Search Q equal DINNER. 24,000 query per second equal 10 million users times 10 queries per day times 20 characters over 24 hours over 3,600 seconds. Peak QPS equal QPS times 2 equal 48,000. Assume 20% of the daily queries are new. 10 million times 10 queries per day times 20 bytes per query times 20% equals 0.4 gigabytes. This means 0.4 gigabytes of new data is added to storage daily. Propose high-level design and get buy-in. At the high level, the system is broken down into 2. Data gathering service. It gathers user input queries and aggregates them in real time. Real-time processing is not practical for large datasets. However, it is a good starting point. We will explore a new, more realistic solution in deep dive. Query service. Given a search query or prefix, return 5 most frequently searched terms. Data gathering service. Let us use simplified example to see how data gathering service works. Assume we have a frequency table that stores the query string and its frequency as shown in figure. In the beginning, the frequency table is empty. Later, users enters queries Twitch, Twitter, and Twilio sequentially. Figure shows how the frequency table is updated. Query service. Assume we have frequency table as shown in table. It has 2 fields. Query. It stores the query string. Frequency. It represents the number of times a query has been searched. When a user types TW in the search box, the following top 5 search queries are displayed, assuming the frequency table is based on table. To get top 5 frequently searched queries, execute the following SQL query. This is an acceptable solution when the data is small. When it is large, accessing the database becomes a bottleneck. We will explore optimizations in deep dive. Step 3. Design deep dive. In the high-level design, we discuss data gathering service and query service. The high-level design is not optimal, but it serves as a good starting point. In this section, we will dive deep into a few components and explore optimizations as follows. Try data structure, data gathering service, query service, scale the storage, try operations. Try data structure. Relational databases are used for storage in the high-level design. However, fetching the top 5 search queries from a relational database is inefficient. The data structure try prefix tree is used to overcome the problem. As try data structure is crucial for the system, we will dedicate significant time to design a customized try. Please note that some of the ideas are from articles 2 and 3. Understanding the basic try data structure is essential for this interview question. However, this is more of a data structure question than a system design question. Besides, many online materials explain this concept. In this chapter, we will only discuss an overview of the try data structure and focus on how to optimize the basic try to improve response time. Try, pronounced try, is a tree-like data structure that can compactly store strings. The name comes from the word retrieval, which indicates it is designed for string retrieval operations. The main idea of try consists of the following. A try is a tree-like data structure. The root represents an empty string. Each node stores a character and has 26 children, one for each possible character. To save space, we do not draw empty links. Each tree node represents a single word or a prefix string. Figure shows a try with search queries 3, try, true, toy, wish, win. Search queries are highlighted with a thicker border. Basic try data structure stores characters in nodes. To support sorting by frequency, frequency info needs to be included in nodes. Assume you have the following frequency table. After adding frequency info to nodes, updated try data structure is shown in figure. How does autocomplete work with try? Before dividing into the algorithm, let us define some terms. P, length of a prefix. N, total number of nodes in a try. C, number of children of a given node. Steps to get top k most search queries are listed below. 1. Find the prefix, time complexity, O, parenthesis P. 2. Traverse the subtree from the prefix node to get all valid children. A child is valid if it can form a valid query string. Time complexity, O, parenthesis C. 3. Sort the children and get top k. Time complexity, O, parenthesis clog C. Let us use an example as shown in figure to explain the algorithm. Assume key equals to 2 and a user types tr in the search box. The algorithm works as follows. Step 1. Find the prefix node tr. Step 2. Traverse the subtree to get all valid children. In this case, nodes 3, 10, bracket true, 35, bracket try, 29 are valid. Step 3. Sort the children and get top 2. True, 35, and try, 29 are top 2 queries with prefix tr. The time complexity of this algorithm is the sum of time spent on each step mentioned above. O, parenthesis P plus O, parenthesis C plus O, parenthesis clog C. The above algorithm is straightforward. However, it is too slow because we need to traverse the entire try to get top key results in the worst case scenario. Below are two optimizations. 1. Limit the max length of a prefix. 2. Cache top search queries at each node. Let us look at these optimizations one by one. Limit the max length of a prefix. Users rarely type a long search query into the search box. Thus, it is safe to say P is a small integer number, say 50. If we limit the length of a prefix, the time complexity for find the prefix can be reduced from O parenthesis P to O parenthesis small constant, aka O1. Cache top search queries at each nodes. To avoid traversing the whole trie, we store top k most frequently used queries at each node. Since 5 to 10 autocomplete suggestions are enough for users, k is a relatively small number. In our specific case, only the top 5 search queries are cached. By caching top search queries at every node, we significantly reduce the time complexity to retrieve the top 5 queries. However, this design requires a lot of space to store top queries at every node. Trading space for time is well worth it as fast response time is very important. Figure shows the updated trie data structure. Top 5 queries are stored on each node. For example, the node with prefix B stores the following: bracket bes, 35, comma, bet, 29, comma, b, 20, comma, b, 15, comma, beer, 10, bracket. Let us revisit the time complexity of the algorithm after applying those two optimizations. 1. Find the prefix node, time complexity, O, parenthesis 1. 2. Return top k. Since top k queries are cached, the time complexity for this step is O, parenthesis 1. As the time complexity for each of the steps is reduced to O, parenthesis 1, our algorithm takes only O, parenthesis 1 to fetch top k queries. Data gathering service. In our previous design, whenever a user types a search query, data is updated in real time. This approach is not practical for the following two reasons. Users may enter billions of queries per day. Updating the trie on every query significantly slows down the query service. Top suggestions may not change much once the trie is built. Thus, it is unnecessary to update the trie frequently. To design a scalable data gathering service, we examine where data comes from and how data is used. Real-time applications like Twitter require up-to-date autocomplete suggestions. However, autocomplete suggestions for many Google keywords may not change much on a daily basis. Despite the differences in use cases, the underlying foundation for data gathering service remains the same because data used to build the trie is usually from analytics or logging services. Figure shows the redesigned data gathering service. Each component is examined one by one. It stores raw data, analytic logs. It stores raw data about search queries. Logs are append only and are not indexed. Table shows an example of the log file. Aggregator. The size of analytic logs is usually very large and data is not in the right format. We need to aggregate data so it can be easily processed by our system. Depending on the use case, we may aggregate data differently. For real-time applications such as Twitter, we aggregate data in a shorter time interval as real-time results are important. On the other hand, aggregating data less frequently, say once per week, might be good enough for many use cases. During an interview session, verify whether real-time results are important. We assume trie is rebuilt weekly. Aggregated data. Table shows an example of aggregated weekly data. Time field represents the start time of a week. Frequency field is the sum of the occurrences for the corresponding query in that week. Workers. Workers are a set of servers that perform asynchronous jobs at regular intervals. They build the Trie data structure and store it in TrieDB. Trie-cache. Trie-cache is a distributed cache system that keeps Trie in memory for fast read. It takes a weekly snapshot of the DB. TrieDB. TrieDB is the persistent storage. Two options are available to store the data. 1. Document store. Since a new Trie is built weekly, we can periodically take a snapshot of it, serialize it, and store the serialized data in the database. Document stores like MongoDB are good fits for serialized data. 2. Key value store. A Trie can be represented in a hash table form by applying the following logic. Every prefix in the Trie is mapped to a key in a hash table. Data on each Trie node is mapped to a value in a hash table. Figure shows mapping between the Trie and hash table. In figure, each Trie node on the left is mapped to the key, to the less than key, comma, value, greater than, pair on the right. If you are unclear how key value stores work, refer to Chapter 6, Design a Key Value Store. Query service. In the high level design, query service calls the database directly to fetch the top 5 results. Figure shows the improved design as previous design is inefficient. 1. A search query is sent to the load balancer. 2. The load balancer routes the request to API servers. 3. API servers get Trie data from Trie-cache and construct autocomplete suggestions for the client. 4. In case the data is not in Trie-cache, we replenish data back to the cache. This way, all subsequent requests for the same prefix are returned from the cache. A cache miss can happen when a cache server is out of memory or offline. Query service requires lightning fast speed. We propose the following optimizations. AJAX request. For web applications, browsers usually send AJAX requests to fetch autocomplete results. The main benefit of AJAX is that sending or receiving a request or response does not refresh the whole web page. Browser caching. For many applications, autocomplete search suggestions may not change much within a short time. Thus, autocomplete suggestions can be saved in a browser cache to allow subsequent requests to get results from the cache directly. Google search engine uses the same cache mechanism. Figure shows the response header when you type System Designs Interview on the Google search engine. As you can see, Google caches the result in the browser for 1 hour. Please note, private in-cache control means results are intended for a single user and must not be cached by a shared cache. Max age equal 3600 means the cache is valid for 3600 seconds, aka an hour. Figure 13.12 Data sampling. For large-scale system, logging every search query requires a lot of processing power and storage. Data sampling is important. For instance, only 1 out of every n request is logged by the system. Trie operations. Trie is a core component of the autocomplete system. Let us look at how trie operations create, update, and delete work. Create. Trie is created by workers using aggregated data. The source of data is from analytics, log, or DB. Update. There are two ways to update the try. Option 1. Update the try weekly. Once a new try is created, the new try replaces the old one. Option 2. Update the individual try node directly. We try to avoid this operation because it is slow. However, if the size of the try is small, it is an acceptable solution. When we update a try node, its ancestors all the way up to the root must be updated because ancestors store top queries of children. Figure shows an example of how the update operation works. On the left side, the search query beer has the original value 10. On the right side, it is updated to 30. As you can see, the node and its ancestors have the beer value updated to 30. Delete. We have to remove hateful, violent, sexually explicit, or dangerous autocomplete suggestions. We add a filter layer in front of the try cache to filter out unwanted suggestions. Having a filter layer gives us the flexibility of removing results based on different filter rules. Unwanted suggestions are removed physically from the database asynchronously so the correct dataset will be used to build try in the next update cycle. Scale the storage. Now that we have developed a system to bring autocomplete queries to users, it is time to solve the scalability issue when the try grows too large to fit in one server. Since English is the only supported language, a naive way to shard is based on the first character. Here are some examples. If we need 2 servers for storage, we can store queries starting with A to M on the first server and N to Z on the second server. If we need 3 servers, we can split queries into A to I, J to R, and S to Z. Following this logic, we can split queries up to 26 servers because there are 26 alphabetic characters in English. Let us define sharding based on the first character as the first level sharding. To store data beyond 26 servers, we can shard on the second or even at the third level. For example, data queries that start with A can be split into 4 servers: AA-AG, AH-AN, AO-AU, and AV-AZ. At the first glance, this approach seems reasonable until you realize that there are a lot more words that start with the letter C than X. This creates an uneven distribution. To mitigate the data imbalance problem, we analyze historical data distribution pattern and apply smarter sharding logic as shown in figure. The Shard Map Manager maintains a lookup database for identifying where rows should be stored. For example, if there are a similar number of historical queries for S and for U, V, W, X, Y, and Z combined, we can maintain 2 shards, one for S and one for U to Z. Step 4. Wrap up. After you finish the deep dive, your interviewer might ask you some follow-up questions. Interviewer: how do you extend your design to support multiple languages? To support other non-English queries, we store Unicode characters in try nodes. If you are not familiar with Unicode, here's the definition. An encoding standard covers all the characters for all the writing systems of the world, modern and ancient. Interviewer: what if top search queries in one country are different from others? In this case, we might build different tries for different countries. To improve the response time, we can store tries in CDNs. Interviewer: how can we support the trending Real-time search queries. Assuming a news event breaks out, a search query suddenly becomes popular. Our original design will not work because, first, offline workers are not scheduled to update the try yet because this is scheduled to run on weekly basis. 2. Even if it's scheduled, it takes too long to build the try. Building a real-time search autocomplete is complicated and is beyond the scope of this book, so we will only give a few ideas. Reduce the working dataset by sharding. Change the ranking model and assign more weight to recent search queries. Data may come as streams, so we do not have access to all the data at once. Streaming data means data is generated continuously. Stream processing requires a different set of systems. APIC Hadoop MapReduce, APIC Spark Streaming, APIC Storm, APIC Kafka, etc. Because all those topics require specific domain knowledge, we are not going into detail here. Congratulations! Step 2 for the web crawler. Propose high-level design and get buy-in. Once the requirements are clear, we move on to the high-level design. Inspired by previous studies on web crawling, we propose a high-level design as shown in figure. First, we explore each design component to understand their functionalities. Then, we examine the crawler workflow step by step. Seed URLs. A web crawler uses seed URLs as a starting point for the crawl process. For example, to crawl all web pages from a university's website, an intuitive way to select seed URL is to use the university's domain. To crawl the entire web, we need to be creative in selecting seed URLs. A good seed URL serves as a good starting point that a crawler can utilize to traverse as many links as possible. The general strategy is to divide the entire URL space into smaller ones. The first proposed approach is based on locality, as different countries may have different popular websites. Another way is to choose seed URLs based on topics. For example, we can divide URL space into shopping, sports, healthcare, etc. Seed URL selection is an open-ended question. You are not expected to give the perfect answer. Just think out loud. URL frontier. Most modern web crawlers split the crawl state into two: to be downloaded and already downloaded. The component that stores URLs to be downloaded is called the URL frontier. You can refer to this as a first in, first out queue. For detailed information about the URL frontier, refer to the deep dive. HTML downloader. The HTML downloader downloads web pages from the internet. Those URLs are provided by the URL frontier. DNS resolver. To download a web page, a URL must be translated into an IP address. The HTML downloader calls the DNS resolver to get the corresponding IP address for the URL. For instance, URL www.wikipedia.org is converted to IP address 198.35.26.96 as of March 5, 2019. Content parser. After a web page is downloaded, it must be parsed and validated because malformed web pages could provoke problems and waste storage space. Implementing a content parser in a crawl server will slow down the crawling process. Thus, the content parser is a separate component. Content scene. Online research reveals that 29% of the web pages are duplicated contents, which may cause the same content to be stored multiple times. We introduce the content scene data structure to eliminate data redundancy and shorten processing time. It helps to detect new content previously stored in the system. To compare two HTML documents, we can compare them character by character. However, this method is slow and time-consuming, especially when billions of web pages are involved. An efficient way to accomplish this task is to compare the hash values of the two web pages. Content storage. It is a storage system for storing HTML content. Content storage. It is a storage system for storing HTML content. The choice of storage system depends on factors such as data type, data size, access frequency, lifespan, etc. Both disk and memory are used. Most of the content is stored on disk because the dataset is too big to fit in memory. Popular content is kept in memory to reduce latency. URL extractor. URL extractor parses and extracts links from HTML pages. Figure shows an example of a link extraction process. Relative paths are converted to absolute URLs by adding the https :/en.wikipedia.org prefix. URL filter. The URL filter excludes certain content types, file extensions, error links, and URLs in blacklisted sites. URL scene. URL scene is a data structure that keeps track of URLs that are visited before or already in the frontier. URL scene helps to avoid adding the same URL multiple times, as this can increase server load and cause potential infinite loops. Bloom, filter, and hash table are common techniques to implement the URL scene component. We will not cover the detailed implementation of the Bloom, filter, and hash table here. For more information, refer to the reference materials. URL storage. URL storage stores already visited URLs. So far, we have discussed every system component. Next, we put them together to explain the workflow. Web crawler workflow. To better explain the workflow step by step, sequence numbers are added in the design diagrams as shown in figure. Step 1. Add seed URLs to the URL frontier. Step 2. HTML downloader fetches a list of URLs from URL frontier. Step 3. HTML downloader gets IP addresses of URLs from DNS resolver and starts downloading. Step 4. Content parser parses HTML pages and checks if pages are malformed. Step 5. After content is parsed and validated, it is passed to the content scene component. Step 6. Content scene component checks if a HTML page is already in the storage. If it's in the storage, this means the same content in different URL has already been processed. In this case, the HTML page is discarded. If it's not in the storage, the system has not processed the same content before. The content is passed to link extractor. Step 7. Link extractor extract links from HTML pages. Step 8. Extracted links are passed to the URL filter. Step 9. After links are filtered, they are passed to the URL scene component. Step 10. URL scene components checks if a URL is already in the storage. If yes, it is processed before, and nothing needs to be done. Step 11. If a URL has not been processed before, it is added to the URL frontier. Step 3. Design deep dive. Up until now, we have discussed the high-level design. Next, we will discuss the most important building components and techniques in depth. Depth in first search, DFS versus breadth first search, BFS. URL frontier, HTML downloader, robustness, extensibility, detect and avoid problematic content. DFS versus BFS. You can think of the web page as a directed graph where web pages serves as nodes and hyperlinks, URLs as edges. The scroll process can be seen as traversing as a directed graph from one web page to others. Two common graph traversal algorithms are DFS and BFS. However, DFS is usually not a good choice because the depth of DFS can be very deep. BFS is commonly used by web crawlers and is implemented by a first in, first out queue. In a FIFO queue, URLs are dequeued in the order they are enqueued. However, this implementation has two problems. First, one, most links from the same web page are linked back to the same host. In figure, all the links in the wikipedia.com are internal links, making the crawler busy processing URLs from the same host. When the crawler tries to download web pages in parallel, Wikipedia servers will be flooded with requests. This is considered as impolite. Standard BFS does not take the priority of a URL into consideration. The web page is large and not every page has the same level of quality and importance. Therefore, we may want to prioritize URLs according to their page ranks, web traffic, update frequency, etc.
Direct Access Bridge. There are two basic options for connecting the VM to the host machine. Direct Access, which uses the physical NIC on the host system. Network Address Translation, which creates a private network on the host system, with the host system acting as a DHCP server. The easiest configuration is to bridge the VM to use the NIC of the host and use its own IP address. But if you want the IP address of the VM to be hidden, then using NOT will ensure that all packets coming from either the VM or its host will appear to come from the host. Network Address Translation. Originally, NAT extended the number of usable internet addresses. It translates private IP addresses to public addresses. VNIX. You probably already put this together from the earlier discussions on virtual networking, but to enable a VM to communicate on either the LAN or a private virtual network, you must assign it a virtual NIC. Multiple VNICs can be added to the same VM for fault tolerance or load balancing. Once the VNIC is added, you assign it a network. Virtual switches. To create a virtual network, as discussed in the previous section, you have to create a virtual switch that will interconnect the VMs and the host. Assigning vSwitch to physical adapters. Resource allocation and provisioning. One of the issues you need to understand is how the host system and the guest operating system share resources. The resources that are allocated to the VMs are called virtual resources, the number of which need not match the number of physical resources in the host machine. Having said that, according to best practices, you probably shouldn't do that. CPU. You can control the allocation of physical CPUs. Use it in one of three ways. Shares VMs on the server. Therefore, they define the relative percentage each VM can use. Reservation. Guaranteed CPU allocation for a virtual machine. Limit. Upper limit for a virtual machine CPU allocation. These settings are used to ensure that the desired VMs have priority to the CPU shares, that certain VMs are always guaranteed CPU time, and that no single VM monopolizes the CPU limits. Although the terminology is slightly different, the concepts are the same. CPU compatibility support. One of the key issues to consider when reviewing compatibility guides is the CPU. AMD, V, and Intel VT. Memory.
Memory resources for virtual machines are allocated using reservations, limits, and shares, in much the same way as CPU time. A virtual machine can use three user-defined settings that affects its memory resource allocation. Limit limits the consumption of memory for a virtual machine. This value is expressed in megabytes. Reservation, shares. The more shares a virtual machine is assigned, the more often it gets a time slice of a memory when there is no memory idle time. In Citrix Zen Server, you can use dynamic memory control, which permits the memory utilization of existing VMs to be compressed so that additional VMs can boot on the host. Once VMs on that host are later shut down or migrated to other hosts, running VMs can reclaim unused physical host memory. Disk. A benefit of virtualization is the ability of VMs to share storage. Thick, provision, lazy, zeroed. Like the classic disk, space required for the virtual disk is allocated during creation. Unlike with a regular drive, if data is present on the disk, it is not deleted until the space is needed for new data. NIC. These virtual NICs can be configured to make use of the physical NICs in the infrastructure to communicate beyond the virtual network to the physical network and even to the internet. It's also possible to create and combine multiple VNICs together to increase the bandwidth available to a VM in the same way that physical NICs can be combined in a process called NIC teaming. Over-provisioning. Rather than having additional physical resources sitting around idle most of the time, you only pay for additional virtual resources when you need them. Scalability. Management interfaces for virtual machines. Hypervisor. Type 1, Type 2, hybrid, cloud models. Public versus private versus hybrid versus community.
APIs. Now that we know how a client can discover the IP address of a server and create a reliable and secure communication link with it, we want the client to invoke operations offered by the server. To that end, the server uses an adapter which defines its application programming interface to translate messages received from the communication link to interface calls implemented by its business logic. See figure. The communication style between a client and a server can be direct or indirect, depending on whether the client communicates directly with the server or indirectly through a broker. Direct communication requires that both processes are up and running for the communication to succeed. However, sometimes this guarantee is either not needed or very hard to achieve, in which case indirect communication is a better fit. An example of indirect communication is messaging. In this model, the sender and the receiver don't communicate directly, but they exchange messages through a message channel, the broker. The sender sends messages to the channel, and on the other side, the receiver reads messages from it. Later in chapter 23, we will see how messages channels are implemented and how to best use them. In this chapter, we will focus our attention on a direct communication style called request response, in which a client sends a request message to the server and the server replies with a response message. This is similar to a function call but across process boundaries and over the network. The request and response messages contain data that is serialized in a language agnostic format.
The choice of format determines a message serialization and deserialization speed, whether it's human readable and how hard it is to evolve it over time. A textual format like JSON is self-describing and human readable, at the expense of increased verbosity and parsing overhead. On the other hand, a binary format like protocol buffers is leaner and more performant than a textual one, at the expense of human readability. When a client sends a request to a server, it can block and wait for the response to arrive, making the communication synchronous. Alternatively, it can ask the outbound adapter to invoke a callback when it receives the response, making the communication asynchronous. Synchronous communication is inefficient as it blocks threads that could be used to do something else. Some languages like JavaScript, C, and Go can completely hide callbacks through language primitives such as async or await. These primitives make writing asynchronous code as straightforward as writing asynchronous code. Commonly used IPC technologies for request-response interactions are HTTP and gRPC. Typically, internal APIs used for server-to-server communications within an organization are implemented with a high-performance RPC framework like gRPC. In contrast, external APIs available to the public tend to be based on HTTP, since web browsers can easily make HTTP response via JavaScript code. A popular set of design principles for designing elegant and scalable HTTP APIs is representational state transfer, or REST, and an API based on these principles is said to be RESTful. For example, these principles include that requests are stateless, and therefore each request contains all the necessary information required to process it. Responses are implicitly or explicitly labeled as cacheable or non-cacheable. If a response is cacheable, the client can reuse the response for a later equivalent response. Given the ubiquity of RESTful HTTP APIs, we will walk through the process of creating an HTTP API in the rest of the chapter. 5.1 HTTP HTTP is a request-response protocol used to encode and transport information between a client and a server. In an HTTP transaction, the client sends a request message to the server's API endpoint, and the server replies back with a response message as shown in figure. In HTTP 1.1, a message is a textual block of data that contains a start line, a set of headers, and an optional body. In a request message, the start line indicates what the request is for, and in a response message, it indicates whether the request was successful or not. The headers are key value pairs with metadata that describes the message. The message body is a container for data. HTTP is a stateless protocol, which means that everything needed by a server to process a request needs to be specified within request itself, without context from previous requests. HTTP uses TCP for the reliability guarantees discussed in Chapter 2. When it runs on top of TLs, it's also referred to as HTTPS.
HTTP 1.1 keeps a connection to a server open by default to avoid needing to create a new one for the next transaction. However, a new request can't be issued until the response to the previous one has been received, aka head of line blocking or HOL blocking. In other words, the transactions have to be serialized. For example, a browser that needs to fetch several images to render an HTML page has to download them one at a time, which can be very inefficient. Although HTTP 1.1 technically allows some type of request to be pipelined, it still suffers from HOL blocking as a single slow response will block all responses after it. With HTTP 1.1, the typical way to improve the throughput of outgoing requests is by creating multiple connections. However, this comes with a price because connections consume resources like memory and sockets. HTTP 2 was designed from the ground up to address the main limitation of HTTP 1.1. It uses a binary protocol rather than a textual one, allowing it to multiplex multiple concurrent request-response transactions, streams, on the same connection. In early 2020, about half of the most visited websites on the internet were using the new HTTP 2 standard. HTTP 3 is the latest iteration of the HTTP standard, which is based on UDP and implements its own transport protocol to address some of TCP's shortcomings. For example, with HTTP 2, a packet loss over TCP connection blocks all streams, HOL, but with HTTP 3, a packet loss interrupts only one stream, not all of them. This book uses the HTTP 1.1 standard for illustration purposes since its plain text format is easier to display. Moreover, HTTP 1.1 is still widely used. 5.2 Resources. Suppose we would like to implement a service to manage the product catalog of an e-commerce application. The service must allow customers to browse the catalog and administrators to create, update, or delete products. Although that sounds simple, in order to expose this service via HTTP, we first need to understand how to model APIs with HTTP. An HTTP server hosts resources, where a resource can be a physical or abstract entity like a document, an image, or a collection of other resources. A URL identifies a resource by describing its location on the server. In our catalog service, the collection of product is a type of resource which could be accessed with a URL like https:// www.example.com/products sort equal price, where HTTPS is the protocol, www.example.com is the hostname, products is the name of the resource, sort equal price is the query string, which contains an additional parameters that affect how the service handles the request. In this case, the sort order of the list of products returned in the response. The URL without the query string is also referred to as the API's /products endpoints. URLs can also model relationships between resources. For example, since a product is a resource that belongs to the collection of products, the product with the unique identifier 42 could have the following relative URL: /products/42. And if the product also has a list of reviews associated with it, we could append its resource name to the product's URL Example /products/42/reviews. However, the API becomes more complex as the nesting of resources increases, so it's a balancing act. Naming resources is only one part of the equation. We also have to serialize the resources on the wire when they are transmitted in the body of request and response messages. When a client sends a request to get a resource, it adds specific headers to the message to describe the preferred representation for the resource. The server uses these headers to pick the most appropriate representation for the response. Generally, in HTTP APIs, JSON is used to represent non-binary resources. For example, this is how the representation of /products/42 might look. Open bracket, quote ID, :42, comma, next line, quote category, quote laptop, comma, next line, quote price, $999, close bracket. 5.3 Request methods. HTTP request can create, read, update, and delete CRUD resources using request methods. When a client makes a request to a server for a particular resource, it specifies which method to use. You can think of a request method as the verb or action to use on a resource. The most commonly used methods are POST, GET, PUT, and DELETE. For example, the API of our catalog service could be defined as follows. POST /products, create a new product and return the URL of the new resource. GET /products, retrieve a list of products. The query string can be used to filter, paginate, and sort the collection. Get /products/42, retrieve product 42. Put /products/42, update product 42. Delete /products/42, delete product 42. Request methods can be categorized based on whether they are safe and whether they are idempotent. A safe method should not have any visible side effects and can safely be cached. An idempotent method can be executed multiple times, and the end result should be same as if it was executed just a single time. Idempotency is a crucial aspect of APIs, and we will talk more about it later in section. 5.4 Response status codes. After the server has received a request, it needs to process it and send a response back to the client. The HTTP response contains a status code to communicate to the client whether the request succeeded or not. Different status code ranges have different meanings. Status codes between 200 and 299 are used to communicate success. For example, 200 OK means that the request succeeded and the body of the response contains the requested resource. Status codes between 300 and 399 are used for redirection. For example, 301 moved permanently means that the request resource has been moved to a different URL specified in the response message location header. Status codes between 400 and 499 are reserved for client errors. A request that fails with a client error will usually return the same error if it's retried, since the error is caused by an issue with the client, not the server. Because of that, it shouldn't be retried.
Some common client errors are 400, bad request, validating the client-side input has failed. 401, unauthorized, the client isn't authenticated. 403, forbidden, the client is authenticated but it's not allowed to access the resource. 404, not found, the server couldn't find the requested resource. Status codes between 500 and 599 are reserved for server errors. A request that fails with a server error can be retried as the issue that caused it to fail might be temporary. These are some typical server status codes. 500, internal server error. The server encountered an unexpected error that prevented it from handling the request. 502, bad gateway. The server, while acting as a gateway or proxy, received an invalid response from a downstream server it accessed while attempting to handle the request. 503, service unavailable. The server is currently unable to handle the request due to temporary overload or scheduled maintenance. 5.5, Open API. Now that we understand how to model an API with HTTP, we can write an adapter that handles HTTP requests by calling the business logic of the catalog service. For example, suppose the service is defined by the following interface. Interface space catalog without space service, open bracket list less than product greater than space get without space products, parentheses, dot inside the parentheses, semicolon. Next line product, get product, parentheses, dot, colon. Next line void, space add without space product, parentheses, dot, with inside the parentheses, semicolon, closing bracket. So when the HTTP adapter receives a get /products request to retrieve the list of all products, it will invoke the get without space products, parentheses, method, and convert the result into an HTTP response. Although this is a simple example, you can see how the adapter connects the IPC mechanism HTTP to the business logic. We can generate a skeleton of the HTTP adapter by defining the API of the service with an interface definition language or IDL. An IDL is a language-independent definition of the API that can be used to generate boilerplate code for the server-side adapter and client-side software development kits in your languages of choice. The OpenAPI specification, which evolved from the Swagger project, is one of the most popular IDLs for RESTful HTTP APIs. With it, we can formally describe the API in a YAML document, including the available endpoints, supported request methods, and response status codes for each endpoint, and the schema of the resources JSON representation. For example, this is how part of the /products endpoint of the catalog service API could be defined. Codes. Although this is a very simple example and we won't go deeper into OpenAPI, it should give you an idea of its expressiveness with its definition. We can then run a tool to generate the API's documentation, boilerplate adapters, and client SDKs. Evolution. An API starts out as a well-designed interface. Slowly but surely, it will have to change to adopt new use cases. The last thing we want to do when evolving an API is to introduce a breaking change that requires all clients to be modified at once, some of which we might have no control over. There are two types of changes that can break compatibility, one at the endpoint level and another at the message level. For example,
If we were to change the /products endpoint to the /new-products, it would obviously break clients that haven't been updated to support the new endpoint. The same applies when making a previously optional query parameter mandatory. Changing the schema of request or response messages in a backward incompatible way can also wreak havoc. For example, changing the type of the category property in the product schema from string to number is a breaking change that would cause the old deserialization logic to blow up in clients. Similar arguments can be made for messages represented with other serialization formats like protocol buffers. REST API should be versioned to support breaking changes by prefixing a version number in the URLs. Sample is /v1/products. However, as a general rule of thumb, APIs should evolve in a backward compatible way unless there is a very good reasons. Although backward compatible APIs tends not to be particularly elegant, they are practical. Idempotency. When an API request times out, the client has no idea whether the server actually received the request or not. For example, the server could have processed the request and crashed right before sending a response back to the client. An effective way for clients to deal with transient failures such as this is to retry the request one or more times until they get a response back. Some HTTP request methods, example put, delete, are considered inherently idempotent as the effect of executing multiple identical requests is identical to executing only one request. For example, if the server processed the same put request for the same resource twice in a row, the end effect would be the same as if the put request was executed only once. But what about requests that are not inherently idempotent? For example, suppose a client issues a post request to add a new product to the catalog service. If the request times out, the client has no way of knowing whether the request succeeded or not. If the request succeeds, retrying it will create two identical products, which is not what the client intended. In order to deal with this case, the client might have to implement some kind of reconciliation logic that checks for duplicate products and removes them when the request is retried. You can see how this introduces a lot of complexity for the client. Instead of pushing this complexity to the client, a better solution would be for the server to create the product only once by making the post request idempotent, so that no matter how many times that specific request is retried, it will appear as if it only executed once. For the server to detect that a request is a duplicate, it needs to be decorated with an idempotency key, a unique identifier, a UUID. The identifier could be part of a header, like idempotency key in Stripe API. For the server to detect duplicates, it needs to remember all the request identifiers it has seen by storing them in a database. When request comes in, the server checks the database to see if the request ID is already present. If it's not there, it adds the request identifier to the database and executes the request. Request identifiers don't have to be stored indefinitely, and they can be purged after some time. Now here comes the tricky part. Suppose the server adds the request identifier to the database and crashes before executing the request. In that case, any future retry won't have any effect because the server will think it has already executed it. So what we really want is for the request to be handled atomically. Either the server processes the request successfully and adds the request identifier to the database, or it fails to process it without storing the request identifier. If the request identifiers and resources managed by the server are stored in the same database, We can guarantee atomicity with ACID transactions. In other words, we can wrap the product creation and request identifier lag within the same database transaction in the post handler. However, if the handler needs to make external calls to other services to handle the request, the implementation becomes a lot more challenging since it requires some form of coordination. Later in chapter 13.2, we will learn how to do just that. Now, assuming the server can detect a duplicate request, how should it be handled? In our example, the server could respond to the client with a status code that signals that the product already exists. But then the client would have to deal with the case differently than if it had received a successful response for the first post request 201 created. So ideally, the server should return the same response that it would have returned for the very first request. So far, we have only considered a single client. Now imagine the following scenario. First, client A sends a request to create a new product. Although the request succeeds, the client doesn't receive a timely response. Second, client B deletes the newly created product. Third, client A retries the original creation request. How should the server deal with the request in step 3? From client A's perspective, it would be less surprising to receive the original creation response than some strange error mentioning that the resource created with that specific request identifier has been deleted. When in doubt, it's helpful to follow the principle of least astonishment. To summarize, an idempotent API makes it a lot easier to implement clients that are robust to failures, since they can assume that requests can be retried on failure without worrying about all the possible edge cases. Summary: communicating over networks is what makes a system distributed. It's all too easy to ignore the leaking complexity that goes into it, since modern programming languages and frameworks make it look like invoking a remote API is no different from calling a local function. I know I did at first and eventually learned this lesson after spending days investigating weird degradations that ultimately turn out to be caused by exhausted socket pools or routers dropping packets. Since then, I spent a great deal of time thinking of everything that can go wrong when a remote request is made. Socket pools can be exhausted, TL certificates can expire, DNS servers can become unavailable, routers can become congested and drop packets. Non-idempotent requests can result in unexpected states, and the list goes on. The only universal truth is that the fastest, safest, most secure, and reliable network call is the one you don't have to make. And I hope that by reading about TCP, TLs, UDP, DNS, and HTTP, you also have rediscovered a profound respect for the challenges of building network applications. HTTP caching. Cruder's application server handles both static and dynamic resources at this point. A static resource contains data that usually doesn't change from one request to another, like a JavaScript or CSS file. Instead, a dynamic resource is generated by the server on the fly, like a JSON document containing the user's profile. Since a static resource doesn't change often, it can be cached. The idea is to have a client browser cache the resource for some time so that the next access doesn't require a network call, reducing the load on the server and the response time. Let's see how the client-side HTTP caching works in practice with a concrete example. HTTP caching is limited to safe request methods that don't alter the server state, like GET or HEAD. Suppose a client issues a GET request for a resource it hasn't accessed before. The local cache intercepts the request, and if it can find the resource locally, it will go and fetch it from the origin server on behalf of the client. The server uses specific HTTP response headers to let clients know that a resource is cacheable, so when the server responds with the resource, It adds a cache control header that defines for how long to cache the resource, or TTL, and an etag header with a version identifier. Finally, when the cache receives the response, it stores the resource locally and returns it to the client. Figure 14. A client accessing a resource for the first time. The age header contains the time in seconds the object was in the cache, which is 0. Now, suppose some time passes and the client tries to access the resource again. The cache first checks whether the resource hasn't expired yet, example, whether it's fresh. If so, the cache immediately returns it. However, even if the resource hasn't expired from the client's point of view, the server may have updated it in the meantime. That mean reads are not strongly consistent, but we will safely assume that this is an acceptable trade-off for our application. If the resource has expired, it's considered state. In this case, the cache sends a GET request to the server with a conditional header like if none match containing the version identifier of the state resource to check whether a newer version is available. If there is, a server returns the updated resource. If not, the server replies with the 304 not modify status code. Figure 14.2. A client accessing a stale resource. Ideally, a static resource should be immutable so that clients can cache it forever, which corresponds to a maximum length of a year according to the HTTP specification. We can still modify a static resource if needed by creating a new one with different URL so that clients will be forced to fetch it from the server. Another advantage of treating static resources as immutable is that we can update multiple related resources atomically. For example, if we publish a new version of the application's website, the updated HTML index file is going to reference the new URLs for the JavaScript and CSS bundles. Thus, a client will see either the old version of the website or the new one depending on which index file it has read, but never a mix of the two that uses the old JavaScript bundle with the new CSS one. Another way of thinking about HTTP caching is that we treat the read path get differently from the write path post put delete because we expect the number of reads to be several orders of magnitude higher than the number of writes. This is a common pattern referred to as the command query responsibility segregation or CQRS pattern. To summarize, allowing clients to cache static resources has reduced the load on our server, and all we have to do was to play with some HTTP headers. We can take caching one step further by introducing a server-side HTTP cache with a reverse proxy. 14.1 Reverse Proxies. A reverse proxy is a server-side proxy that intercepts all communications with clients. Since the proxy is indistinguishable from the actual server, clients are unaware that they are communicating through an intermediary. Figure 14.3. A reverse proxy acts as an intermediary between the clients and the servers. A common use case for a reverse proxy is to cache static resources returned by the server. Since the cache is shared among the clients, it will decrease the load of the server a lot more than any client-side cache ever could. Because a reverse proxy is a middleman, it can be used for much more than just caching. For example, it can authenticate requests on behalf of the server, compress a response before returning it to the client to speed up the transmission, rate limit requests coming from specific IPs or users to protect the server from being overwhelmed, load balance requests across multiple servers to handle more load. We will explore some of these use cases in the next chapters. Nginx and HAP proxy are widely used reverse proxies that we could leverage to build server-side cache. However, many use cases for reverse proxies have been commoditized by managed services, so rather than building out a server-side cache, we could just leverage a content delivery network.
Summary. To create ASP.NET Core Apps, we need to download and install the .NET Core SDK, the .NET Core Runtime, and the ASP.NET Core Runtime. Unless you chose an IDE that automatically does those things, such as Visual Studio, we should also provide ourselves with a suitable IDE such as Visual Studio, a comprehensive .NET development solution for Windows and Mac OS that we'll use throughout this book. Visual Studio can dramatically boost our productivity and help us standardize our development processes thanks to built-in features such as task runners, package managers, integrated source control, and syntax highlighting. Visual Studio includes a lot of useful templates that we can use as boilerplate for creating our apps, including the ASP.NET Core Web API template, which is the perfect choice to start our MyBGList Web API project. Visual Studio's ASP.NET Core Web API template comes with a small group of auto-generated files, a startup file to set up services and middleware, program.cs, a settings file to launch the app with a development web server, launch settings.json, a set of configuration files that store the app's environment-specific settings, app settings.json, a POCO class to emulate a data object, weather forecast.cs, a controller class that can respond to simple HTTP requests with some JSON data, weather forecast controller.cs. After a brief review of the template files and some minor code changes to understand how each of them works, we can start replacing the built-in weather forecast sample classes with some board game related classes. Before going further, it may be useful to test our acquired knowledge with some exercises, simulating a series of requests, backlog items from the client. Depending on our confidence, we can try to fulfill them without any suggestions or follow some high-level guidance. Regardless of chosen complexity level, performing such exercises is a great way to test our current skills and prepare for the topics yet to come. As we can see, the Visual Studio Web API template that we use to create our project provides a neat start page that mentions Swagger, a convenient tool that describes the structure of our API. I'll introduce Swagger later in this chapter. Now we're ready to take a better look at our project. Before we start coding, it might be worth discussing projects and solutions and the roles they're meant to play within the Visual Studio ecosystem. In a nutshell, we can say that a project is a group of source code files that are typically compiled into an executable library or website together, with some required configuration files and a bunch of optional content files such as icons, images, and data files. The MyBGList project includes a small set of .cs and .json files generated by Visual Studio to create our ASP.NET Web API using the configuration settings that we choose. A solution is a container that we can use to organize one or more related projects. When we open a solution, Visual Studio automatically opens all the projects that the solution contains. In our scenario, the solution contains only our MyBGList Web API project and share its name. In the following chapters, we'll add other projects to our solution. Specifically, we'll create some class libraries that we'll want to keep separate from the Web API project so we can use them elsewhere. Such an approach increases the reusability of our code while granting us the chance to keep our projects logically grouped and accessible within the same IDE window. MyBGList project overview. Now that we learned the basics of Visual Studio, let's spend some valuable time reviewing the auto-generated source code of our brand new API projects. The default ASP.NET Core Web API template provides a minimal yet convenient boilerplate that can be useful for understanding the basic structure of a typical project. which is precisely what we need to do before we start coding our board game-related web APIs. Let's start by taking a look at the project's file structure. In the Solution Explorer window, we see that our project contains some important files. Launch settings.json inside the /properties/folder containing the settings for launching the project in development mode. App settings.json containing the apps configuration settings for all the environments, and the nested app settings.development.json containing the settings specific to the development environment only. Program.cs, the Bootstrap class introduced in Chapter 1. Weather forecast.cs, a minimal data transfer object, DTO class that control uses to serve the sample weather forecast JavaScript object notation JSON data using a strongly typed approach. In the following section, we'll briefly review all these files to understand their purposes and the roles they play within the boilerplate. While we perform code review, we'll also make some small yet significant updates of some of the default behaviors to better suit our needs. Eventually, we'll replace the boilerplate files related to weather forecasts with our own board game theme classes. GraphQL. The supremacy of REST was questioned in 2015 with the public release of GraphQL, an open-source data query and manipulation language for APIs developed by Facebook. The main differences between the two approaches are related not to the architectural styles, but to their different ways of sending and retrieving data. As a matter of fact, GraphQL follows most of the RESTful constraints, relies on the same application layer protocol, HTTP, and adopts the same data format, JSON. But instead of using different endpoints to fetch different data objects, it allows the client to perform dynamic queries and ask for the concrete data requirements of a single endpoint. I'll try to explain this concept with an actual example taken from the board game web API scenario. Suppose that we want to retrieve the names and unique IDs of all the users who give positive feedback on the Citadel board game. When we're dealing with typical REST APIs, fulfilling such a task would require the following operations. 1. A web API request to the full-text search endpoint to retrieve a list of board games with a name equal to Citadels. To keep things simple, let's assume that such a call returns a single result, allowing us to get our target board game's info, including its unique ID, which is what we're looking for. 2. Another web API request to the feedback endpoint to retrieve all feedback received from that user's unique ID. Again, let's assume that the feedback ranges from 1, worst gaming experience I've ever had, to 10, best game ever. 3. A client-side iteration such as for each loop to cycle through all the retrieved feedback and retrieve the user ID of those with a rating equal to or greater than 6. 4. A third web API request to the user endpoint to retrieve the users who correspond to those unique IDs. The complete request or response cycle is represented graphically in Figure 1.4. That plan is feasible, yet it undeniably involves a huge amount of work. Specifically, we would have to perform multiple round trips, 3 HTTP requests, and a lot of overfetching the Citadel's game info, the data of all feedback, and the data of all users who give a positive rating to get some names. The only workaround would be to implement additional API endpoints to return what we need or to ease some of the intermediate work. We could add an endpoint to fetch the positive feedback for a given board game ID or maybe even for a given board game name, including the full text query in the underlying implementation. If we're up for it, we could even implement a dedicated endpoint such as API/positive feedbacks by name to perform the whole task. This approach, however, would undeniably affect back-end development time and add complexity to our API and wouldn't be versatile enough to help in similar, non-identical cases. What if we want to retrieve negative feedback instead of instead, or positive feedback for multiple games or for all the games created by a given author. As we can easily understand, overcoming such problems may not be simple, especially if we need a high level of versatility in terms of client-side data fetching requirements. Now let's see what happens with GraphQL. When we take this approach, instead of thinking in terms of existing or additional endpoints, we focus on the query we need to send to the server to request what we need, as we do with the DBMS. When we're done, we send that query to the single GraphQL endpoint and get back precisely the data we ask for within a single HTTP call and without fetching any field we don't need. Figure shows a GraphQL client to server round trip. As we can see, the performance optimizations aren't limited to the web API. The GraphQL approach doesn't require client-side iteration because the server already returns the precise result we're looking for. The GraphQL specification is available at https://spec.graphql.org. I talk extensively about GraphQL in Chapter 10, showing you how to use it alongside REST to achieve specific query-oriented goals. ASP.NET Core. Now that we've seen what web APIs are and how we can use them to exchange data within web applications and services across a network, it's time to introduce the framework that we'll use to create them throughout this book. That framework is ASP.NET Core, a high-performance cross-platform open-source web development framework introduced by Microsoft in 2016 as the successor to ASP.NET. In the following sections, I briefly cover its most distinctive aspects, the overall architecture, the request or response pipeline management, the asynchronous programming pattern, the routing system, and so on. In this book, we're going to use Net 6.0 and the ASP.NET Core Runtime 6.0.11, the latest generally available versions at this writing, and 9th installment released so far, following Net Core 1, 1.1, 2, 2.1, 2.2, 3, 3.1, and Net 5. Each version introduced several updates, improvements, and additional features, but for the sake of simplicity, I'll review the resulting characteristics shipped with the latest version. Furthermore, starting with .NET 5, all even-numbered .NET releases, including .NET 6, are granted with long-term support status, meaning that they will be supported for many years to come as opposed to odd-number versions, which have shorter time frames. Currently, the support period is 3 years for even-numbered versions and 18 months for odd-number versions. REST, Representational State Transfer, is an architectural style specifically designed for network-based applications that use standard HTTP GET, POST, PATCH, PUT, and DELETE request methods. First defined in the now superseded RFC 2616, https://www.rfc2616/rfc2616.xhtml to access and manipulate data. More specifically, GET is used to read data, POST to create a new resource or perform a state change, PATCH to update an existing resource, PUT to replace an existing resource with a new one or create it if it doesn't exist, and DELETE to erase the resource permanently. This approach does not require additional conventions to allow the parties to communicate, which makes it easy to adopt and fast to implement. REST is much more. However, its architectural paradigm relies on 6 guiding constraints that, if implemented correctly, can greatly benefit several web API properties. Client-server approach. RESTful APIs shouldn't force the separation of concerns principle by keeping the UI and data storage concerns apart. This approach is particularly suitable for the World Wide Web, where clients such as browsers have a separate role from web applications and don't know anything about how they were implemented. It's important to understand that separating these concerns not only improves their portability but also keeps them simpler to implement and maintain, thus improving the simplicity, scalability, and modifiability of the whole system. Statelessness. The server should handle all communications between clients without keeping, storing, or retaining data from previous calls, such as session info. Also, the client should include any context-related info, such as authentication keys, in each call. This approach reduces the overhead of each request on the server, which can significantly improve the performance and scalability properties of Web API, especially under heavy load. Cacheability. The data exchange between the client and the server should use the caching capabilities provided by the HTTP protocol. More specifically, all HTTP responses must contain the appropriate caching or non-caching info within their headers to optimize client workload while preventing them from serving stale or outdated content by mistake. A good caching strategy can have a huge effect on the scalability and performance properties of most web APIs. Layered system. Putting the server behind one or more intermediary HTTP service or filters such as forwarders, reverse proxies, and load balancers can greatly improve the overall security aspects of a web API, as well as its performance and scalability properties. Code on demand. COD is the only optional REST constraint. It allows the server to provide executable code or scripts that clients can use to adopt custom behavior. Examples of COD include distributed computing and remote evaluation techniques, in which the server delegates part of its job to clients or needs them to perform certain checks locally by using complex or custom tasks, such as verifying whether some applications or drivers are installed. In a broader sense, such a constraint also refers to the capability rare in the early days of REST yet common in most recent JavaScript-powered web apps to fetch from the server the source code required to build and load the application, as well as problem further REST calls. COD can improve the performance and scalability of Web API, but at the same time, it reduces overall visibility and poses non-trivial security risks, which is why it is flagged as optional. Uniform interface. The last REST constraint is the most important one. It defines the four fundamental features that a RESTful interface must have to enable clients to communicate with the server without the server knowing anything about how they work, keeping them decoupled from the underlying implementation of the Web API. These features are identification of resources. Each resource must be univocally identified through its dedicated unique universal resource identifier. The URI https://mybglist.com/api/game/11, for example, identifies a single board game. Manipulation of resources through representations. Client must be able to perform basic operations on resources by using the resource URI and the corresponding HTTP method, without the need for additional info. To read Board Games 11's data, for example, a client should make a GET request to https://mybglist.com/api/game/11. If the client wants to delete that data, it should make a delete request to the same URI and so on. Self-descriptive messages. Each sender's message must include all the information the recipient requests to understand and process it properly. This requirement is valid for the client and server and is quite easy to implement by means of the HTTP protocol. Both requests and responses are designed to include a set of HTTP headers that describe the protocol version, content type, default language, and other metadata. The web API and connecting clients need only ensure that the headers are set properly. Hate OAS hypermedia as the engine of application state. The server should provide useful information to clients, but only through hyperlinks and URIs or UI templates. This requirement decouples the server from its clients because clients require little to no knowledge of how to interact with the server beyond generic understanding of hypermedia. Furthermore, server functionality can evolve independently without creating backward compatibility problems. A web API that implements all these constraints can be described as RESTful. The widely accepted rules and guidelines, the proven reliability of the HTTP protocol, and the overall simplicity of implementation and development make REST the most popular web API architecture used nowadays. For that reason, most of the web API projects will develop throughout the book use the REST architectural style and follow the RESTful approach with the 6 constraints introduced in this section. Architecture. I've chosen to use ASP.NET Core for our web API projects because the new Microsoft framework enforces several modern architectural principles and best practices that allow us to build lightweight, highly modular apps with a high level of testability and maintainability of the source code. Such an approach naturally guides developers to build or adopt applications composed of discrete and reusable components that perform specific tasks and communicate through a series of interfaces made available by the framework. These components are called services and middleware, and they're registered and configured in the web application's program.cs file, which is the app's entry point. Note, if you're coming from an older ASP.NET Core version, such as 3.1 or 5.0, you may wonder what happened to the startup class and its corresponding startup.cs file, which used to contain the services and middleware configuration settings. This class was removed from the minimal hosting model introduced with the Net6, which merged the program and startup classes into a single program.cs file. Services. Services are components that an application requires to provide its functionalities. We can think of them as app dependencies because our app depends on their availability to work as expected. I use the term dependencies here for a reason. ASP.NET Core supports the dependency injection, software design pattern, an architectural technique that allow us to achieve inversion of control between a class and its dependencies. Here's how the whole services implementation, registration or configuration, and injection process works in ASP.NET Core. Implementation. Each service is implemented by means of a dedicated interface or base class to abstract the implementation. Both the interface and implementation can be provided by the framework, created by the developer, or acquired from a third-party, GitHub, NuGet packages, and the like. Registration and configuration. All services used by the app are configured and registered using their interfaces in the built-in iService Provider class, which is a service container. The actual registration and configuration process happens within program.cs file, where the developer can also choose a suitable lifetime, transient, scope, or singleton. Dependency injection. Each service can be injected into the constructor of the class where it's meant to be used. The framework, through the iService Provider container class, automatically makes available an instance of the dependency, creating a new one or possibly reusing an existing one, depending on the configured service lifetime, as well as disposing of it when it's no longer needed. Typical example of service interface provided by the framework include iAuthorize service, which can be used to implement policy-based permissions, and iEmail service, which can be used to send email messages. Middleware. Middleware is a set of components that operates at the HTTP level and can be used to handle the whole HTTP request processing pipeline. If you remember the HTTP modules and HTTP handlers used by ASP.NET before the advent of ASP.NET Core, you can easily see how middleware plays a similar role and performs the same tasks. Typical examples of middleware used in ASP.NET Core web applications include HTTPS redirection middleware, which redirects non-HTTPS requests to an HTTPS URL, and authorization middleware, which use the authorization service internally to handle all authorization tasks at the HTTP level. Each type of middleware can pass the HTTP request to the next component in the pipeline or provide an HTTP response, thus short-circuiting the pipeline itself and preventing further middleware from processing the request. This type of request blocking middleware is called terminal middleware and usually is in charge of processing the main business logic task of the various apps endpoints. Warning: it's worth noting that middleware is processed in registration order, first in, first out. Always add terminal middleware after non-terminal middleware in the program.cs file. Otherwise, the file won't work. A good example of terminal middleware is static file middleware, which ultimately handles the endpoint URLs pointing to static files, as long as they are accessible. When such a condition happens, it sends the requested file to the caller with an appropriate HTTP response, thus terminating the request pipeline. The HTTP redirection middleware that I mentioned briefly earlier is also terminal middleware because it ultimately responds with an HTTP to HTTPS redirect to all non-HTTPS requests. Note: both static file middleware and HTTPS redirection middleware will terminate the HTTP request only when certain circumstances are met. If the requested endpoint doesn't match their activation rules, such as a URL pointing to a non-present static file for the former or already in HTTPS for the latter, they pass it to the next middleware present in the pipeline without taking action. For this reason, we could say that they are potentially terminal middleware to distinguish them from middleware that always ends the request pipeline when the HTTP request reaches it.
Server maintenance. Given a scenario, perform server hardware maintenance. Like all network devices, servers need some attention from time to time. So let's summarize this section. Once you've installed your servers, you must take additional steps to enable them to perform the roles you chose for them in the network. You need to monitor and maintain the servers so that they continue to perform well. In addition, you want to avoid security-related issues. Out-of-band management. Out-of-band management refers to any method of managing the server that does not use the network. It offers a solution when the network is down or the device is inaccessible. It manages devices with no power and remotely boots devices that have been crashed, turned off, hibernating, or in sleep mode. Remote drive access. One of the things you can do with out-of-band management is to connect to a remote or the drive of a remote server. This is typically done through a serial connection. In many cases, the drive is connected to an OOB or out-of-band switch that provides OOB remote access to multiple devices or to a remote console server. Many servers come with OOB capability built in. The next two sections are two examples. ILO, integrated lights out, is technology embedded into Hewlett-Packard servers that allow for out-of-band management of the server. In figure 8.1, one of the ILO ports is shown in HP Moonshot PC. These hold blade servers. HPIO functions out of the box without additional software installation, regardless of server's state of operation.
giving you complete access to the server from any location via a web browser or the ELO mobile app. ID Rock, a Dell Remote Access Controller card provides out-of-band management for Dell servers. The ID Rack refers to a version of these interface cards that is integrated on the motherboard of the server. Once configured, the port will present a technician with an interface on their computer, which is connected to the port when the connection is established. Remote console access, remote power on or off. Certain out-of-band connections allow you to power off a device and to power it back on. This is one of the great advantages of OOB. You can also use an OOB connection to manage UPS systems. These cards are installed in slots on the UPS, as shown in figure 3.4. Once the card is on the network, you will be able to use several protocols such as SMTP, HTTP, SMTP, Telnet, and SSH to access it. Installing the remote management card. Keep in mind that these cards come with varying levels of functionality. Some give you total control of the device, whereas others may only allow you to monitor the device environment. On a related note, some networks cards offer a feature called Recon LAN. This allows the device to be started up from the network by sending a special packet to the NIC. Although this feature can be helpful, it can also be abused by attackers. The magic packets are layer 2 frames which can be sent by any device on the same LAN as the target. Although this only allows the startup of the server and does not remove any other authentication required to access the server. It may be a function you want to disable, especially if you don't use it. This is another configuration that can be done in the BIOS settings in a fashion similar to the way we disabled the USB ports. Internet Protocol Keyboard Video Mouse. In this particular implementation, it can be done several ways. Each server has a small device between it and the KDM switch that accepts the serial and keyboard or mouse connections.
Program.cs. Now that I've introduced services and middleware, we can finally take a look at the program.cs file, which is executed at the start of the application. First, creates the Web Application Builder Factory class. Second, registers and configures services. Third, builds the web application object. Fourth, registers and configures non-terminal and potentially terminal middleware. Fifth, registers and configures terminal middleware. By analyzing this code, we can easily see that the file is responsible for the following initialization tasks: instantiating the web application, registering and configuring the services, registering and configuring the middleware. More precisely, the web application is instantiated by the Web Application Builder Factory class, creating a web application object. This instance is stored in the app local variable, which is used to register and configure the required services and middleware. Note: both services and middleware are registered and configured by dedicated extension methods, a convenient way to shortcut the setup process and keep the program.cs file as concise as possible. Under ASP.NET Core naming conventions, services are configured mostly by using extension methods with the add prefix, middleware prefix, or use, map, and run. The only difference that concerns us, at least for now, is that the run delegate is always 100% terminal and the last one to be processed. We'll talk more about these conventions and their meaning when we experiment with minimal APIs later. For the sake of simplicity, I split middleware into two categories:
potentially terminal and terminal. The difference should be clear at this point. Potentially terminal middleware ends the HTTP request pipeline only if it matches certain rules, whereas terminal middleware always does, so no wonder it's the last of the pile. Controllers. In ASP.NET Core, a controller is a class used to group a set of action methods, also called actions, that handle similar HTTP requests. From such a perspective, we could say that controllers are containers that can be used to aggregate action methods that have something in common: routing rules and prefixes, services, instances, authorization requirements, caching strategies, HTTP level filters, and so on. These common requirements can be defined directly on the controller class, thus avoiding the need to specify them for each action. This approach, enforced by some powerful built-in naming and coding conventions, helps to keep the code dry and simplifies the app's architecture. Note, DRY is an acronym for Don't Repeat Yourself, a well-known principle of software development that helps us remember to avoid redundancy, pattern repetition, and anything else that could result in a code smell. It's the opposite of wet, write everything twice or write every time. Starting with ASP.NET Core, controllers can inherit from two built-in base classes: controller base, a minimal implementation without support for views; controller, a more powerful implementation that inherits from controller base and adds full support for views. As we can easily understand, the controller base class is meant to be used in web applications that adopt the model view controller pattern, where they're meant to return the data coming from the business logic, typically handled by dependency injected services. In a typical ASP.NET Core web application, the resulting data is returned to the client through the views, which handle the app's data presentation layer by using client-side markup and scripting languages such as HTML, CSS, JavaScript, and the like, or server-side rendered syntaxes such as Razor. When dealing with APIs, we generally don't use views because we want to return JSON or XML data, no HTML, directly from the controller. Given such a scenario, inheriting from the controller base class is the recommended approach in our specific case. Here's a sample web API controller that handles two types of HTTP requests: a GET request to /API/sample to receive a list of items, a GET request to /API/sample/ bracket ID to receive a single item with the specified bracket ID, assuming that it's a unique integer value acting as a primary key. A delete request to /API/sample/ bracket ID to delete the single item with the specified ID. First, adds API specific behaviors. 2. Default routing rules. 3. Action to handle HTTP GET to /API/sample. 4th, action to handle HTTP GET to /API/sample/ bracket ID. 5th, action to handle HTTP delete to /API/sample/ bracket ID. As we can see by looking at this code, we were able to fulfill our given task with few lines of code by taking advantage of some useful built-in conventions: a centralized /API/sample/ routing prefix valid for all action methods thanks to the bracket route, parenthesis, quote, API/bracket controller, quote, parenthesis, bracket attribute applied at the controller level, automatic routing rules for all the implemented HTTP verbs, including the required parameters, thanks to the bracket HTTP GET and bracket HTTP delete attributes applied to the corresponding action methods, automatic routing mapping using the controller middleware default rules because we apply the controller suffix to the class name as long as the app.mapControllers extension method is present in the program.cs file. Furthermore, Because we've used the API controller attribute, we also need some additional conventions specific to web APIs that automatically return certain HTTP status codes depending on the action type and result. We'll talk more about them in Chapter 6 when we delve into error handling. Minimal APIs. Controllers with built-in conventions are great ways to implement web API business logic with few lines of code. In ASP.NET Core 6, however, the framework introduced a minimal paradigm that allows us to build web APIs with even less ceremony. This feature is called Minimal APIs, and despite its young age, it's getting a lot of attention from new and seasoned ASP.NET developers because it often allows for a much smaller and more readable code base. The best way to explain what Minimal API is about is to perform a quick code comparison between a controller-based approach and the new kid on the block. Here's how the same HTTP request that we handled with the sample controller can be handled by Minimal APIs with some minor updates to the program.cs file. First, remove this line and the sample controller class. Second, add this line instead. As we can see, all the implementation is transferred to the program.cs file without the need for a separate controller class. Also, the code can be further simplified or dryified, such as by adding prefix variable that eliminates the need to repeat code/API/sample multiple times. The advantage is visible in terms of code readability, simplicity, and overhead reduction. Tip: the business logic of any minimal API method can be put outside the program.cs file only can be put outside the program.cs file. Only the map methods are required to go there. As a matter of fact, moving the actual implementation to other classes is almost always good practice, unless we're dealing with one-liners. The minimal APIs paradigm isn't likely to replace controllers, but it will definitely ease the coding experience of most small web API projects, such as microservices, and attract most developers who are looking for slick approaches and shallow learning curves. For all these reasons, we'll often use it alongside controllers throughout this book. Task-based asynchronous pattern. Most performance problems that affect web applications are due to the fact that a limited number of threads needs to handle a potentially unlimited volume of concurrent HTTP requests. This is especially true when, before responding to this request, these threads must perform some resource-intensive and often non-cacheable task, being blocked until they eventually receive the result. Typical examples include reading or writing data from a DBMS through SQL queries, accessing a third-party service such as an external website or web API, and performing any other task that requires a considerable amount of execution time. When a web application is forced to deal with a lot of these requests simultaneously, the number of available threads quickly decreases, leading to degraded response times and eventually to service unavailability, HTTP 503 and the like. This scenario is the main goal of most this scenario is the main goal of most HTTP-based denial of service attacks, in which the web application is flooded by requests to make the whole server unavailable. Thread blocking, non-cache HTTP requests are gold mines for DOS attackers because they have a great chance of starving the thread pool quickly. A general rule of thumb in dealing with resource-intensive tasks is to cache the resulting HTTP response aggressively. As stated by REST Constraint 3, cacheability. In several scenarios, however, caching is not an option, such as when we need to write into a DBMS, HTTPS post, or read mutable or highly customizable data, HTTP GET with a lot of parameters. What do we do in those cases? The ASP.NET Core Framework allows developers to deal with this problem efficiently by implementing the C language level asynchronous model, better known as the task asynchronous pattern. The best way to understand how TOP works is to see it in action. Take a look at the following source code. 1. First async, second wait. As we can see, we applied some minor updates to the first action method of the sample controller that we worked with earlier to implement TOP. The new pattern relies on using the async and await keywords to handle a task in a non-blocking way. The async keyword defines the methods returning a task. The await keyword allows the calling thread to start the newly implemented task in a non-blocking way. When the task is completed, the thread continues the code execution, thus returning the resulting comma-separated string. It's worth noting that because we used the await keyword inside the getAction method, we had to mark that method async as well. That's perfectly fine. It means that the method will be awaited by the calling thread instead of blocking it, which is what we want. Our minimal implementation won't have any benefits in terms of performance. We definitely don't need to wait for something as trivial as a literal to-do string, but it should give us an idea of the benefits that the async or await pattern will bring the web application when that sample task that run is replaced by something that requires the server to perform some actual work, such as retrieving real data from a DBMS. I'll talk extensively about asynchronous data retrieval task in Chapter 4, which introduces Microsoft's most popular data access technology for .NET Entity Framework Core. Summary: Web APIs are HTTP-based services that any software application can use to access and possibly manipulate data. Web APIs are designed to work by using common communication standards, protocols, even sets of available operations, specifications, and data exchange format, JSON, XML, and the like. Web APIs are commonly split among 4 possible scopes of use: public or open, when anyone has or can acquire access; partner, when access is restricted to business associates; internal or private, when access is limited to the organization's network; composite, when they orchestrate multiple public, partner, or internal API. To fulfill their role, Web API requires a uniform set of rules, constraints, and formats that depend on the chosen architectural style or messaging protocol. The most used standards nowadays are REST, SOAP, gRPC, and GraphQL, each of which has distinctive characteristics, trade-offs, and support formats. This book focuses mostly on REST, but Chapter 10 is dedicated to GraphQL. ASP.NET Core is the high-performance cross-platform open-source web development framework that we will use to design and develop web APIs throughout this book. ASP.NET Core's modern architectural principles allow developers to build lightweight, highly modular apps with a great level of testability and maintainability. ASP.NET Core architecture allows developers to customize the app's capabilities and workloads by using discrete and reusable components to perform specific tasks. These components fall into 2 main categories, both of which are registered and configured in the app's entry point, the program.cs file. Services, required to provide functionalities and instantiated through dependency injection. Middleware, responsible for handling the HTTP request pipeline. ASP.NET Core supports 2 paradigms for building web APIs: controllers, which offer great versatility and a full set of supported features, and minimal APIs, a simplified approach that allows us to write less code while reducing overhead. The minimal API approach, introduced in .NET 6, can be a great way to build simple web APIs in a time-efficient fashion and is great for developers who are looking for a sleek, modern programming approach. ASP.NET Core web apps can overcome most performance problems due to resource-intensive thread blocking calls by using TOP, an asynchronous programming model that allows the main thread to start tasks in a non-blocking way and resume execution upon their completion. .NET 5. Just when everyone thought that Microsoft had finally taken a clear path with the naming convention of its upcoming frameworks, the Microsoft developer community was shaken again on May 6, 2019 by the following post by Richard Lander, program manager of the .NET team, which appeared on the Microsoft developer blog. The post got an immediate backup from another article that came out the same day, written by Scott Hunter, Program Management Director of the .NET ecosystem. The two posts were meant to share the same big news with the readers. .NET Framework 4.x and .NET Core 3.x would converge in the next major installment of the .NET Core, which would skip a major version number to properly encapsulate both installments. The new unified platform would be called the .NET 5 and would include everything that had been released so far with uniform capabilities and behaviors. .NET Runtime, JIT, AOT, GC, BCL or Base Class Library, C, VB.NET, F Number, ASP.NET, Entity Framework, MI.NET, WinForms, WPF, and Xamarin. Microsoft said they wanted to eventually drop the term core from the framework name because the .NET 5 would be the main implementation of the .NET going forward, thus replacing the .NET Framework and .NET Core. However, for the time being, the ASP.NET Core ecosystem is still retaining the name Core to avoid confusing it with ASP.NET MVC5. Entity Framework Core will also keep the name Core to avoid confusing it with Entity Framework 5 and 6. For all of these reasons, in this book, we'll keep using ASP.NET Core and Entity Framework Core or EF Core as well. .NET 6 came out on November 8, 2021, a year after .NET 5 as expected by the .NET schedule. The most notable improvement in this version is the introduction of Multi-Platform Application UI, also known as MAUI, a modern UI toolkit built on top of Xamarin.Forms that was specifically created to eventually replace Xamarin.Forms and become the .NET standard for creating multi-platform application that can run on Android, iOS, macOS, and Windows from a single code base. The main difference between MAUI and Xamarin is that new approach now shipped as a core workload, shares the same base class library as other workloads such as Blazor, and adopts the most recent SDK style project system introduced with the .NET 5, thus allowing a consistent tooling and coding experience for all .NET developers. In addition to MAUI, .NET 6 introduces a lot of new features and improvements such as C10 language support with some new features such as null parameter checking, required parameters, field keyword, file scope, namespace, top-level statements, async main, target type, new expressions, and more. Implicit using directives, a feature that instructs the compiler to automatically import a set of using statements based on the project type, without the need to explicitly include them in each file. New project templates, which are much cleaner and simpler since they do implement and demonstrate most of the language improvements brought by C version 9 and 10, including those we've just mentioned. Package validation tooling, an option that allows developers to validate that their packages are consistent and well-formed during package development. SDK workloads, a feature that leverages the concepts of workloads introduced with the .NET Core to allow developers to install only necessary SDK components, skipping the parts they don't need. In other words, it's basically a package manager for the SDKs. Inner loop performance improvements, a family of tweaks dedicated to the performance optimization of the various tools and workflows used by developers, such as CLI, Runtime, and MS Build, thereby aiming to improve their coding and building experience. The most important of them is the hot reload, a feature that allows the project source code to be modified while the application is running without the need to manually pause or hit a break. .NET 7 .NET 7 came out on November 8, 2022 and was mostly focused on performance. It was presented by Microsoft as unified, modern, simple, and fast. The optimizations include enhancement to the just-in-time JIT compiler, garbage collector improvements, and runtime updates. One of the most praised changes changes was the introduction of on-stack replacement, OSR, a feature that allows the runtime to change the code executed by currently running methods. Thanks to OSR, long-running methods can switch to more optimized versions during their execution, thus improving the overall startup time. For additional information on how OSR works, check out the official documentation on GitHub. Other improvements include faster code generation for ARM64 architectures, several optimizations to the Mono runtime, new APIs and improvements to the system.text.regular expressions and system.text.json libraries. New metrics for the iMemory cache interface, part of Microsoft.extension's caching library that allow developers to track statistics for one or more memory caches, added support for microseconds and nanoseconds in time span, time only, date time, and date time offset types. Added a new rate limiting middleware, Microsoft.ASP.NET Core.rate limiting that allows developers to configure several rate limiting policies and attach them to the HTTP endpoints using the enable rate limiting attribute. The built-in rate limiting algorithms include fixed window, sliding window, token bucket, and concurrency. HTTP/3 improvement support, HTTP/2 performance improvements. .NET 8, coming out on November 14, 2023, .NET 8 is the successor of .NET 7 and the current long-term support release. The new version brings a lot of performance improvements and new features, including a revamp of the serialization and deserialization functionalities provided by the system.text.json library, such as built-in support for HAP, int128, and uint128 numeric types, new naming policies, snake_case and kebab-case, read-only properties deserialization, and several new extension methods. Many improvements to globalization, including better support for different cultures, UTF-8 support, and improved performance for globalization-related operations. On the ASP.NET Core side, the new release adds several new features to authentication and authorization, such as new ASP.NET Core Identity API endpoints, such as /register and /login, to ease up the implementation of the built-in authentication workflow in JavaScript-based single-page apps. A new iAuthorizations requirement data interface that allows to define custom authorization policies with fewer lines of code. A lot of progress has been made on Blazor, which can now be considered a full-stack web UI framework that can render content either the component or page level in a number of ways. Static server rendering to generate static HTML on the server. Interactive server rendering, ISR, to generate interactive components with pre-rendering on the server. Interactive WebAssembly rendering, CSR, to generate interactive components on the client with pre-rendering on the server. Interactive automatic rendering, IAR, to generate content using the server-side ASP.NET Core runtime at startup, and then switching to the .NET WebAssembly runtime on the client after the Blazor bundle is downloaded and the WebAssembly runtime activates. For additional information regarding the Blazor render modes, check out the following article. Other valuable improvements include SignalR stateful reconnect, minimal APIs, explicit binding to HTTP forms using the from attribute, better anti-forgery capabilities, a more comprehensive AOT deployment model, and so on. This concludes our journey through the recent history of ASP.NET. In the next section, we'll move our focus to the Angular ecosystem, which experienced a rather similar turn of events. Chapter 2. In this second chapter, we'll switch from theory to practice More specifically, we will choose the kind of web application that we want to build and see how we can do it in accordance with the expectations of a typical product owner. In the second part of this chapter, we'll start our deployment journey by setting up our local development environment and creating our first Angular and ASP.NET Core projects. Here's a full breakdown of the topics we're going to cover. A full stack approach, the importance of being able to learn how to design, assemble, and deliver a complete product. Multi-page applications, MPA, single-page applications, SPA, native web application, NWAs, and progressive web applications, PWAs. Key features of and the most important differences between the various types of web applications, as well as how well ASP.NET and Angular could relate to each one of them. A sample SPA project, what we're going to do throughout this book, preparing the workspace, how to set up our workstation to achieve our first goal, implementing a simple Hello World boilerplate that will be further extended in the following chapters. By the end of the chapter, we'll have everything we need to start our full stack development journey. A full stack approach. Learning to use ASP.NET Core and Angular together means being able to work with both the front end, client side, and back end, server side of a web application. To put it in other words, it means being able to design, assemble, and deliver a complete product. Eventually, in order to do that, we'll need to dig through the following: back-end programming, front-end programming, UI styling and UX design, database design, modeling, configuration and administration, web server configuration and administration, web application deployment. At first glance, it can seem that this kind of approach goes against common sense. A single developer should not be allowed to do everything by themselves. Every developer knows that the back end and the front end require entirely different skills and experience. So why in the world should we do that? Before answering this question, we should understand what we really mean when we say being able to. We don't have to become experts on every single layer of the stack. No one expects us to. When we choose to embrace the full stack approach, what we really need is to raise our awareness level throughout the whole stack we're working on. This means that we need to know how backend works and how it can and will be connected to the front end. We need to know how the data will be stored, retrieved, and then served through the client. We need to acknowledge the interactions we will need to layer out between the various components that our web application is made from. And we need to be aware of security concerns, authentication mechanisms, optimization strategies, load balancing techniques, and so on. This doesn't necessarily mean that we have to have strong skills in all these areas. As a matter of fact, we hardly ever will. Nonetheless, if we want to pursue a full stack approach, we need to understand the meaning, role, and scope of all of them. Furthermore, we should be able to work our way through any of these fields whenever we need to. MPAs, SPAs, PWAs, and NWAs. In order to demonstrate how ASP.NET and Angular can work together to their full extent, we couldn't think of anything better than building some small SPA projects with most, if not all, PWA features. The reason for this choice is quite obvious. There is no better approach to demonstrate some of the best features they have to offer nowadays. We'll have the chance to work with modern interfaces and patterns such as the HTML5 push state API, webhooks, data transport-based request, dynamic web components, UI data bindings, and a stateless Ajax-driven architecture capable of flawlessly encompassing all of these features. We'll also make good use of some distinctive PWA features such as service workers and web manifest files. The AJAX acronym stands for Asynchronous JavaScript and XML and is typically used when referring to a set of web development techniques to send and retrieve data from a server synchronously. In practice, modern implementation of these techniques such as Fetch API utilize JSON instead of XML, thus making the term AJAX less precise to describe this type of interaction. Although that noun is still used nowadays, for historical reasons, the term XHR/fetch is a more correct way to properly describe these techniques. If you don't know the meaning of these definitions and acronyms, don't worry. We're going to explore these concepts in the next couple of sections, which are dedicated to enumerating the most relevant features of the following types of web applications: MPAs, SPAs, EWAs, and NWAs. While we're there, we'll also try to figure out the most common product owners' expectations for a typical web-based projects. Multi-page applications. Multi-page applications, also known as MPAs, are those web applications that work in a traditional way. Each time the user asks for or submits data to the server, they render a new page that is sent back to the browser. This is how all websites used to work during the first 20 years of the World Wide Web, and is still the most widely used approach nowadays due to a number of advantages that MPAs can still provide. Excellent SEO performance, a fast and steady learning curve, the ability to manage and customize static and dynamic content, and a lot of great content management systems, frameworks, and UI themes such as WordPress, Joomla, and the like that can be used to build them from the ground up in a few minutes. However, MPAs also come with some significant cons. The required server-side round trips tend to make them quite expensive in terms of bandwidth. Moreover, front-end and back-end development are often tightly coupled, thus making them harder to maintain and update. Luckily enough, most of these issues have been mitigated throughout the years, thanks to the various browser features and technology improvements such as CDN, server-side caching, XHR/fetch request, and so on. At the same time, shuts techniques and add more complexity to the development and deployment phases. That is, unless we choose to rely upon one of the CMS platform that we talked about early on, thus giving up on most of the coding aspects. With all that implies, single-page applications. To put it briefly, an SPA is a web-based application that tries to provide the same user experience as a desktop application. If you consider the fact that all SPAs are still served through a web server and thus accessed by web browsers. Just like any other standard website, we can easily understand how that this desired outcome can only be achieved by changing some of the default patterns commonly used in web development, such as resource loading, DOM management, and UI navigation. In a good SPA, both content and resources, HTML, JavaScript, CSS, and so on, are either retrieved within a single page load or are dynamically fetched when needed. This also means that the page doesn't reload or refresh. It just changes and adapts in response to user actions, performing the required server-side calls behind the scenes. These are some of the key features provided by a competitive SPA nowadays. No server-side round trips. A competitive SPA can redraw any part of the client UI without requiring a full server-side round trip to retrieve a full HTML page. This is mostly achieved by implementing the separation of concerns design principle, which means that the data source, the business logic, and the presentation layer will be separated. Efficient routing. A competitive SPA is able to keep track of the user's current state and location during its full navigation experience using organized, JavaScript-based routers. We'll talk more about that in the upcoming chapters when we introduce the concepts of server-side and client-side routing. Performance and flexibility. A competitive SPA usually transfers all of its UI to the client thanks to its JavaScript SDK of choice, Angular, jQuery, Bootstrap, and so on. This is often good for network performance as increasing client-side rendering and offline processing reduces the UI impact over the network. However, the real deal brought by this approach is the flexibility granted to the UI as the developer will be able to completely rewrite the application's front end with little or no impact on the server, aside from a few of the static resource files. The list can easily grow, as these are the only some of the major advantage of a properly designed competitive SPA. These aspects play a major role nowadays as many business websites and services are switching from their traditional MPA mindset to fully committed or hybrid SPA-based approaches. Progressive web applications. In 2015, another web development pattern pushed its way into the light when Frances Berryman, a British freelance designer, and Alex Rasser, a Google Chrome engineer, used the term PWAs for the first time to refer to those web applications that could take advantage of a couple of new important features supported by modern browsers, service workers, and web manifest files. These two important improvements could be successfully used to deliver some functionalities usually only available on mobile apps, push notifications, offline mode, permission-based hardware access, and so on, using standard web-based development tools such as HTML, CSS, and JavaScript. The rise of PWAs began on March 19, 2018, when Apple implemented support for service workers in Safari 11.1. Since that date, PWAs have been widely adopted throughout the industry thanks to their undeniable advantage over their non-progressive counterparts. Faster load times, smaller application sizes, higher audience engagement, and so on. Here are the main technical features of a PWA according to Google. Progressive works for every user regardless of browser choice using progressive enhancement principles. Responsive fits any form factor, desktop, mobile. Responsive fits any form factor, desktop, mobile, tablet, or firms yet to emerge. Connectivity independent, service workers allow offline use or use on low-quality networks. App-like feel like an app to the user with app-style interactions and navigation. Fresh, always up to date due to the service worker update process. Safe, serve via HTTPS to prevent snooping and ensure content hasn't been tampered with. Discoverable, identifiable as an application by a web manifest.json file, and a registered service worker, and discoverable by search engines. Re-engageable, the ability to use push notifications to maintain engagement with the user. Installable, provides home screen icons without the use Installable provides home screen icons without the use of an app store. Linkable can easily be shared via a URL and does not require complex installation. However, their technical baseline criteria can be restricted to the following subsets. HTTPS, they must be served from a secure origin, which means over TLs with green padlock displays, no active mixed content. Minimal offline mode, they must be able to start even if the device is not connected to the web, with limited functions or at least displaying a custom offline page. Service workers, they have to register a service worker with the fetch event handler, which is required for minimal offline support, as explained previously. Web manifest file, they need to reference a valid manifest.json file with at least 4 key properties: name, short underscore name, start underscore URL, and display, and a minimum set of required icons. For those in reading about this directly from the source, here's the original link from the Google developers website. In addition, here are 2 follow-up posts from Alex Rasser, infrequently noted blog. For those who don't know, Alex Rasser has worked as a senior staff software engineer at Google since December 2008. Although they have some similarities, PWAs and SPAs are 2 different concepts, have different requirements, and differ in many important aspects. As we can see, none of the PWA requirements mentioned previously referred to as PAs or server-side round trips. A PWA can work within a single HTML page and XHR/fetch request, thus also being an SPA. But it could also request other server rendered or static pages and or perform standard HTTP GET or POST request, much like an MPA. It's also the opposite. Any SPA can implement any single PWA technical criteria depending on the product owner's requirement. More on that later. The server-side and client-side frameworks adopted and the developer's ultimate goal. Native web applications. The first good definition of native web applications, also known as NWAs, available on the web can arguably be found in Sam Johnston blog post written on January 16, 2009, which went like this. A native web application is a web application which is 100% supported out of the box by recent standards compliant web browser.
Release and deployment. This chapter covers getting the web API ready for release, adopting a security by design approach, setting up a content delivery network (CDN), creating a Windows Server virtual machine in Microsoft Azure, installing and configuring Internet Information Services (IIS), deploying the web API to Windows Server with Visual Studio. We're close to the end of our journey. Our ASP.NET Core Web API project is mature enough to be classified as a potentially shippable product, a definition used by most agile methodologists to indicate that the application, although still incomplete, has reached a level of maturity solid enough to be shown to product owners, beta testers, and or end users. It's important to understand that this status doesn't mean the app is ready to be delivered to customers. Potentially shippable is a state of confidence from a development perspective. Actual shipping is a business decision that should take other data into account. In this chapter, we'll suppose that the IT project manager assigned to our development team, after carefully reviewing the results of our work, has decided that our web API is ready for its first release. To comply with this decision, we need to publish it somewhere to enable the interested parties, ideally product owners and testers, to access and evaluate it. After a brief introductory part, where we'll perform some required steps to ensure that our ASP.NET Core application is ready for the deployment phase, we'll learn how to publish our project to a Windows Server machine. ASP.NET Core is a platform agnostic, so although we'll target a Windows OS, we could use the same process with minor differences to deploy our app on Linux machine, a Docker container, or any other publishing target. Warning: the topics covered in this chapter concern different skills from those required in the previous chapters. Most of the tasks are typically assigned to deployment engineers or system administrators, not to software, at least in large organizations. But being able to release, deploy, and publish a project is a required learning path for anyone who aims to become a full-stack developer or to work on a small DevOps-oriented team, a rather common scenario for small companies and startups. Pre-publishing tasks. In this section, we'll learn how to get our ASP.NET Core Web API ready to publish in a production environment. Here's what we're about to do. First, define the overall security approach that will guide us through implementation of the various required tasks. Second, determine the domain name that we'll use to make our app publicly available on the World Wide Web. Third, set up a content delivery network (CDN) to achieve transport layer security and caching capabilities, as well as protect our web API from distributed denial of service attempts, brute force attacks, and other web-related threats. Fourth, configure our project to make it ready for production.
We'll also review our current caching and security settings to ensure that the app is ready to be accessed by external users, including potentially malicious parties, while minimizing the risk of request-based attacks, data breaches, and other harmful scenarios. Considering security, the depth and scope of the pre-publishing review we're about to perform are strictly determined by our scenario. We're bringing into production a yet unknown web API, which is meant to be accessed by a limited panel of users and beta testers, and which doesn't contain restricted or sensitive data. Based on these premises, we can reasonably expect that we won't be subject to sophisticated attacks, at least not for some time. This expectation, however, must not lead us to take the risk of attack lightly. According to 2022 Imperva Bad Bot report, 27.7% of internet traffic is made up of automated threats. These bots can be instructed to attack specific websites as well as to scan the internet for potentially vulnerable IP addresses and or TCP ports. When a suitable target is found, these bots will likely carry out some automated attacks on it and signal the outcome to their master, a person or organization that might orchestrate even worse malicious activities. For that reason, whenever we're commissioned to bring one of our web-based projects into production, we should adopt a security by design approach to take the most secure route to fulfill each of our tasks as long as we maintain a decent cost or benefit trade-off. Now that we've defined our overall security approach, let's deal with the first of our pre-publishing tasks, obtaining a suitable domain name. Choosing a domain name. In information technology, a domain name is a string of text that uniquely maps to a numeric internet protocol address, which can be used to access a web resource, typically a website. We can think of it as a human-readable alias of the IP address we want to connect to, which is also machine-readable and understood by all web browsers and web servers. Note, for reasons of space, I'll take for granted that you know most of the basic networking and TCP or IP-related concepts that are used throughout this section. If not, I strongly suggest improving your knowledge by reading http:/2inaction by Barry Pollard. For deployment purposes, we'll register a dedicated mybglist.com domain so that we'll be able to create a custom subdomains and use them to create public endpoints for our users. I won't guide you through the domain purchase process. I take for granted that you'll complete it before continuing to the next section. If you don't want to purchase dedicated domain, you're free to use a subdomain and follow the same instructions. Replacing the subdomain we're going to use in our deployment sample, win-01.mybglist.com with your chosen subdomain. Setting up a CDN. Now that we've determined our domain name, we have another important decision to make, whether to set up a direct binding to the IP address of our web server or set up an intermediate layer such as a CDN service. Each option has advantages and drawbacks. Configuring a CDN will inevitably require additional configuration efforts and will complicate our overall architecture, but it will also grant us valuable caching and security benefits. Tip: in the unlikely case that you don't want or are unable to set up a CDN, you can skip this section and go to the next one. Based on what we learned in Chapter 8, which was about intermediate caching, we already know that adding a CDN service to our network stack will increase the performance of our web API. But we should take into account some relevant security benefits, assuming that we want to stick to the security by design approach that we choose to adopt. Those benefits may vary depending on the CDN service and or the subscription plan, but some of them are usually available, such as the following: IP address masking. The CDN acts as a proxy, hiding the IP address of the origin server, the web server hosting our web API. All requests go to the CDN first and then are forwarded to our origin server. Web Application Firewall. CDNs typically use a dedicated WAF that checks the incoming HTTP request and filters potentially malicious traffic based on a given set of rules, blacklist, and other industry standard security measures. DDoS protection. Most CDNs automatically detect and mitigate DDoS attacks by using rate limiting rules and other advanced techniques. These features alone, which would be difficult and costly for any software development team to implement, are more than enough to make CDN worth the effort. For that reason, we're going to set it up. Before choosing a provider, however, let's consider the result we want to achieve. Using the edge origin pattern. In Chapter 3, which introduced CDNs, I briefly mentioned the edge origin architectural pattern, an infrastructure in which a proxy or CDN service, the edge, publicly serves the content by taking it from a source web server, the origin, that isn't exposed directly. Figure illustrates this concept. As we can see, the end user points the browser to our web API's subdomain, which is handled by the CDN service, Edge. The CDN serves the content back, taking it from its intermediate cache or requesting it from the web server using its dedicated and not exposed IP address. That process is precisely what we want to implement for our web API. With that in mind, let's start by choosing a CDN service provider. Working with data. This chapter covers understanding the core concepts of a database management system, introducing Entity Framework Core, building a data model and binding it to entity classes, deploying a SQL Server database using on-premise and cloud hosting models, setting up the database context and structure using EF Core. Up to this point, we have been working on our web API using sample data created on demand by a static procedure. Such an approach was certainly useful as it allowed us to focus on the fundamental concepts of our REST architecture while keeping our source code as simple as possible. In this chapter, we're going to get rid of that fake dataset and replace it with a proper data source managed by means of a database. In the first section, we'll briefly review the key elements and distinctive properties of a database management system, as well as the benefits of storing our data there. Right after that, we'll see how we can interact with that system using Entity Framework Core, a lightweight, extensible data access technology that allows us to work with most database services using .NET objects. More precisely, we'll learn how to use the two main development approaches provided by EF Core to generate a data model from an existing database schema, database first, or create a data model manually and generate the database schema from that code first, providing a concrete scenario for both. To achieve these goals, we will also need to provide ourselves with a real DBMS. For this reason, we will spend some valuable time analyzing some of the many alternatives available today, installing a database server on our development machine on-premise, or relying on a cloud-hosted DBMS service using one of the many cloud computing providers available, such as Microsoft Azure. As soon as we have a database up and running, we'll learn how to improve our web API project to retrieve and persist relational data by using the Object Relational Mapping (ORM) capabilities provided by EF Core. Database schema in data model. Before continuing, it might be useful to clarify the meaning of some relevant terms that we'll be using throughout this book, because they're often used in similar, sometimes interchangeable way. We'll use database schema for the database structure, intended to be the sum of all tables, collections, fields, relationships, views, indexes, constraints, and the like, and data model for the abstraction EF Core uses to interact with that structure. This means that the database schema is a logical representation of the database, whereas the data model is made of several C classes working together using a standardized set of conventions and rules. These distinctions will help us better understand the differences of the various operational contexts that we will work with in this chapter and following chapters. Choosing a database management system is a software program specifically designed for creating and managing large sets of structured data. Those datasets are generally called databases. For the sake of simplicity, I'll take for granted that you already know the main advantages of using a DBMS to manage a large quantity of information: improve efficiency, access versatility, data categorization, normalization capabilities, support for atomicity, consistency, isolation, and durability, or ACID transactions, and several undeniable benefits in terms of data security coming from the increased confidentiality, integrity, and availability that these solutions natively provide. Note, confidentiality, integrity, and availability are the three pillars of the CIA triad, a widely used security model that summarizes the key properties that any organization should consider before adopting a new technology, improving the existing IT infrastructure, or developing a project. Since Chapter 1, we've taken for granted the use of a database to store all our board game-related data. The reason for that choice is quite simple. We not only want to benefit from all the advantages described earlier, but also aim to reproduce a suitable situation for developing a web API. Having to deal with the DBMS is likely to be the most common task for any backend web developer for years to come. In our scenario, however, we are playing the role not only of software developers but also of high-level IT infrastructure architects. We need to do something before starting to code. Choose which DBMS to use for storing and delivering our data. The following sections briefly review some alternative approaches we can follow, as well as their pros and cons. For the sake of simplicity, our analysis will be limited to the fundamental aspects of each option, as well as the reason that will determine our decisions.
Local hardware administration. Managing hardware locally used to mean that you will not be connecting to the device over the network. You will be in the server room or data center when you do this. Today's definition of local has expanded somewhat to include over-the-network methods as well. The available options depend on whether the server is a physical device, like a rack server, blade server, or tower server, or if it's a virtual server deployed as a virtual machine on virtualization host. Keyboard, video, mouse. Crash cart. A crash cart is a mobile server room cart equipped with a secure laptop that is used to provide a direct connection to malfunctioning servers and computers for restoration of crashes. Crash carts should be designed for mobility, versatility, and durability. Virtual administration console. To manage servers in a virtual environment, vendors of virtualization software provide administration console that allow one server to manage another for the purpose of maintenance and administration. Server hardware, racking, power cabling, and network cabling. In this chapter, we covered hardware in a server, including the topics in Object 1 of the exam. These include a discussion of form factors such as the tower, rack, and blade server,
We also discuss configuring and maintaining server components such as CPU, memory, NICs, hard drives, riser cards, and RAID controllers. We ended the chapter by exploring methods of satisfying the power and cooling requirements of servers and of the server rooms and data centers in which they live. Exam essentials: differentiate the server form factors. These include tower servers, 1U, 2U, 3U, and 4U rack-mounted servers and blade servers. The U in the rack server notation indicates the number of units in the rack that server use. Describe the components found inside the server. Inside the server case, you will find all of the same components you might find in a workstation, but they will be more robust and there may be more of them. This includes CPU, memory, NICs, hard drives, riser cards, and RAID controllers. Understand the power requirements of servers. Servers can require from 350 watts for a 1U rack mount to 4500 watts for a chassis with 14 blades in it. And identify and mitigate cooling issues. Explain how to use heat sinks, fans, and baffles inside the case to eliminate the heat created by servers. In the server room or data center, understand how to deploy baffles and hot or cold ASIL to remove heat from the room. Installing and configuring servers. Installing server operating systems. Minimum operating system requirements. Hardware compatibility list. Installations. There are many different ways to perform the operating installation. Some are quite simple and others can get complicated but offer granular control of the process. Graphical user interface, attended installation. Core. When you install Windows Server Core, you're installing the part of the operating system shared by all versions. To install Windows Server 2022 Server Core, boot to a virtual or physical device using the Windows Server Media or mounted ISO file. Bare metal, and mounted ISO file. The out-of-box experience will then run, allowing you to select your regional options, enter a product key, choose between standard and data center versions, and select a disk to install the operating system on. Bare metal. A bare metal installation means that the operating system is installed on an empty drive and requires no software to be there first. First, create a bootable ISO image on a DVD that will be used to access the empty hard drive. Second, boot the bootable DVD ISO image. You may need to change the boot order so that the system boots to the DVD before the hard drive. Third, after booting, you will be represented with first page of the Windows Server 2019 installation program. From this point on, the installation process will be the same as if you were booting to an existing OS. You simply create a partition when that page appears, format it, and choose to install it. Virtualized, remote, sleep or stream / as unattended, scripted installations, PXE boot, and TFTP. Chapter 13, Introduction. Even if you do everything right and design the perfect, multi-tiered, scalable, and highly available application environment, it'll be complete waste if it ends up costing too much. The best protection from unpleasant surprises is by understanding how you're built for using AWS services, how you can deploy resources in the most cost-effective way, and how you can automate cost event alerting protocols. Planning, tracking, and controlling costs. The precise function of these tools and even the names. Choosing a CDN service provider. In general terms, there are four main features to look for when choosing a CDN service provider. Capability. A good CDN should have a decent network size, number of servers, and distribution, worldwide coverage. More servers will likely lead to less buffering, greater redundancy, and more scalability. And a good geographic distribution will ensure that the same level of services for all members of our potential audience, regardless of where they are connecting from. Performance. Performance is often related to and most dependent on capability. The most important key metrics to measure include domain name system, response time, connect time, wait time, overall latency, packet loss rate, and bandwidth throughput. Reliability. When it's set up, the CDN becomes the only gateway of our web application. If something bad happens to it or to its configuration settings, our user will be unable to connect. For that reason, we need to ensure that the service guarantees near 100% uptime or availability and good and fast customer support. Pricing. A good CDN should offer an affordable, transparent pricing model. Most CDNs use modular subscription plans based on custom negotiated contracts depending on the customer's bandwidth and feature needs. Another common model relies on use with a per GB pricing that typically goes down as volume rises. Some CDNs even offer free plans for small-scale projects. Any of these approaches can be viable depending on specific needs and, most important, the expected or known traffic volume of the web application. Because we have small-scale project with a limited budget, we should choose a CDN provider with a great cost-benefit ratio. Starting from this premise, our choice will be Cloudflare, an extremely popular CDN service provided by Cloudflare Incorporation since 2010. According to W3Techs.com survey, Cloudflare CDN is used by 19.1% of web sites worldwide, with a CDN market share of 79.7%. This popularity is easily explained by the fact that Cloudflare is one of the few CDN services to offer an unlimited and unrestricted free plan, which makes it perfect for our needs. Another great reason to choose Cloudflare is the fact that it provides 2 free SSL or TL certificates. The Edge certificate will be generated automatically and used by the CDN itself when serving the content to our visitors, ensuring full HTTPS support for our web API. The Origin certificate. We can manually generate and install the Origin certificate on the web server hosting the web API to ensure an encrypted connection between the CDN, Edge, and the host Origin server. In the following sections, we'll learn how to create Cloudflare account and set up this service. Creating a Cloudflare account. The first thing we need to do is create a Cloudflare account. I won't go into details here because the registration process is straightforward. At the end of it, perform the login by using the credentials, email, and password that we set up. Then click the Add Site button, figure 12.2, which takes us to a page where we can add our domain. We can add the subdomain here. However, if you plan to use a subdomain of an existing domain instead of a dedicated domain, we still need to type the parent domain in this text box unless it's already configured with Cloudflare. We'll be given the chance to choose the domain configuration options later. Right after we add the domain and click the Add Site button, we'll be prompted to select a subscription plan. The paid plans, Pro, Business, and Enterprise, are stocked with interesting features, but because we're aiming for a budget-friendly solution, we'll start with the free plan, which guarantees the core features we require, at least for the time being. The free plan requires us to configure Cloudflare Cloudflare as the primary DNS provider for our domain. So we'll use the Cloudflare name service and manage our DNS records on Cloudflare. This configuration option is known as full setup. In case we want to use a subdomain of an existing domain that we don't want to move to Cloudflare, we should consider purchasing the business or enterprise plan instead. These plans include the CNAME setup feature, also known as partial setup. We're going to choose the full setup option, which allows us to select the free plan. Tip: for more information about the full setup and partial CNAME setup configuration options, see this and this link. After we click continue, Cloudflare performs a scan of the existing DNS records of our domain, which will take a few seconds. These records will be used to populate the DNS management panel. Cloudflare will try to copy or clone the current DNS configuration of our domain to get ready to handle it by using its own name servers. And surprisingly, we'll eventually have to update our domain's existing name servers to use Cloudflare's name servers. Updating the name servers. After the DNS scan, we'll access a grid-like view showing the various DNS records currently registered for our domain in Cloudflare. But that configuration won't become active until we update the name servers currently used by our domain with the one provided by Cloudflare. The required steps are summarized on Cloudflare's overview page, accessible through the menu on the left side of the page. The name service update process is straightforward and shouldn't pose significant problems. We need to access the domain management dashboard of the domain service provider that we use to purchase the domain and replace the content of a couple of text boxes with the values provided by Cloudflare. First, it may be wise to do a detailed check to ensure that automatic DNS scan performed by Cloudflare fetch all the existing A, CNAME, text, and MX records, and to add the missing ones, if any, in the Cloudflare DNS management panel. If we fail to do that, the name service update process could compromise some of the existing domain services. They would no longer be resolved. Next, we'll need to wait for DNS propagation, the time frame it takes for DNS changes to be updated across the internet. This process can take up to 72 hours depending on several factors, including the time to leave TTL values of our existing DNS records. When the process completes, Cloudflare will send us an email notification saying that our domain is active on Cloudflare. If we don't want to wait, we can click the Check Name Servers button at the end of the Name Servers Setup Guide, partly visible in figure, to perform a real-time check. Note, for reason of space, we've only scratched the surface of Cloudflare features and capabilities. To learn more about the service, read the official docs at https://developers.cloudflare.com. While we wait for the name servers update to propagate, we can proceed to the next step, deploying our ASP.NET Core Web API by using Visual Studio's publishing capabilities. Fine-tuning our app. In this section, we'll take care of the following tasks. First, get our project ready for production by reviewing the app settings.json file and the program.cs file. Second, improve the web API security posture by adding some specific HTTP response headers, better known as security headers, that will help mitigate or prevent some common attacks. Third, create a static API documentation interface client instead of exposing our Swagger definition file and Swagger UI directly. Reviewing the app settings.json file. Our project's app settings.json file should be okay for production because we adopted the good practice of creating multiple versions of them, one for each environment we need to support. We have the following cascading files. App settings.json contains the default settings. App settings.development.json contains development-specific settings and overrides for all developers. Secrets.json contains development-specific settings and overrides for our own private development environment. Ideally, we need to create a new app settings.production.json file containing the equivalent of the secrets.json files for the production environment. Adding this file in our Visual Studio project and or sharing it among developers would be a bad idea. However, because it could easily end up in some publicly accessible repositories such as GitHub and or unprotected storage devices. For that reason, we'll create the app settings.production.json file directly on the production server during the deployment phase. This approach may not always be practical depending on the overall complexity of that file and the working practices of the IT development team, but it's viable enough in our scenario. We'll see how to do that when we deploy our web API in production. For now, we have nothing to do with these files. Reviewing the program.cs file. As we've known since chapter 2, the program.cs file allows us to set up middleware for each available runtime environment, development, staging, and production by using the app.environment property. Two good examples are the Swagger and Swagger UI middleware, configured to be available only in development. Hiding Swagger in staging production environments is good security practice. Publicly documenting our API might give potential attackers some valuable hints on ways to abuse our endpoints. We can lessen the risk by implementing a restrictive cross-origin resource sharing policy, as well as adding HTTP security headers that could mitigate or prevent other attacks. Using HTTP security headers, as we know all too well, each time a browser navigates to a website, it issues an HTTP request to the web server hosting that site. The server typically responds with an HTTP response, which usually contains a status code, some response headers, and often some content in HTML, JavaScript object notation, or other browser-compatible formats. Another thing we know well is that the response headers contain useful info that the client will use to handle several tasks such as content caching, language and localization, and character encoding. Some of this metadata can affect the website security posture as it controls the browser's behavior with regard to the received content. It can force the client or browser to communicate over HTTPS only, for example, or force the browser to block any iframe, frame, or other source SRC content from third-party servers. The response headers that contain these client policies are called security headers. Adding them to our web applications is widely considered to be one of the most convenient security best practices in terms of cost-benefit ratio for the following reasons. They're easy to implement, it's easy to understand how they work, and what attacks they help mitigate. They require minimum configuration changes. They have a negligible effect on performance. Security headers are required nowadays to pass any penetration test, vulnerability scan, risk assessment, data security checklist, and decent IT audit and or certification process. Here's a list of the most important HTTP security headers that we might consider implementing in our web API project. HTTP Strict Transport Security, HSTS, tells the web browser to access the web servers over HTTPS only, ensuring that each connection will be established only through secure channels. Xframe Options protects against clickjacking by preventing frames and iframes from specific sources such as different web servers from loading on your site. XDAS XSS Protection protects against cross-site scripting by enabling a specific filter built into most modern browsers. Although XSS filtering is active by default in most modern browsers, it's advisable to enable and configure it explicitly to strengthen our website even more. Content Type Options prevents the browser from downloading, viewing, or executing a response that differs from the expected and declared content type, thus reducing the risk
of executing malicious software or downloading harmful files. Content security policy prevents attacks such as XSS and other code injection-based attacks by defining which content the browser should and shouldn't load. Referrer policy determines whether the URL of the web page that linked to the requested resource has to be sent along with the request using the referrer HTTP header. The default behavior, if no value is specified, is to strip that header and hence the referrer info when going from a page using HTTPS to a page using unsecure HTTP and leaving it in all other cases. Now that we know these security headers are and what they do, let's see how to implement them. As we might guess, the best place to handle this task is the program.cs file. Open that file, scroll down to this point, and replace it with the code shown in the following listing. First, strict transport security header. Second, xprim options header. Third, x-xss protection header. Fourth, x content type options header. Fifth, content security policy header. Sixth, referrer policy header. Notice that the HTTP strict transport security HSTS header has its own built-in middleware that others require a manual implementation using a custom middleware. We chose to add the header only in non-development environments, a wise choice because some of headers, especially HSTS, may create some inconvenient problems when we run our app on localhost. Note, I won't cover security headers in detail. We'll add them by using their most common settings, which are good enough to protect our MyVigilist Web API. Plenty of websites offer information about how they work and how to configure them. A good place to start is the OWASP HTTP Secure Response Headers cheat sheet at this link. Although the security headers we implemented can prevent or mitigate some attacks, exposing Swagger in a non-development environment would still be risky. The best thing we can do to comply with the security by design approach is to keep adding Swagger middleware in the development environment only. Unfortunately, this approach will also prevent our audience from accessing the API documentation we work with in Chapter 11, including the Swagger UI. Is there a way to preserve what we did there without exposing Swagger directly? Luckily, several code generator tools can seamlessly create static HTML-based web user interfaces from Swagger JSON definition files. In the next section, we'll learn how to use one of them. Tip: first, be sure to inspect the program.cs file thoroughly for other middleware that shouldn't be used in non-development environments, and use the app.environment property to prevent them from being added to the HTTP pipeline. Our sample project has none of its middleware, but it's a good practice to perform this check before the publishing phase. Creating a static API documentation interface. The first thing we must do to create static API documentation interface is to choose a code generator tool. Plenty of those tools are available, made, developed, and maintained by the Swagger team or third parties. For simplicity, we'll limit our choice to the following: Swagger CodeGen, an open source command line interface tool available on GitHub. Swagger Editor, a web-based open source online editor providing a generate client feature that uses Swagger CodeGen to achieve the same results. These tools is available at Swagger Hub, an integrated API design and documentation platform that includes the preceding tools and a lot of additional configuration and productivity features. It's available at the first two options are free and the third one requires a subscription plan with a 14-day trial available. All things considered, the Swagger editor is the most practical free choice as it doesn't require us to install anything. To use it, navigate to and wait for the web main page to load.
The editor already contains a sample Swagger definition file left panel, which is rendered in real time to a HTML-based user interface right panel. To replace the sample file with ours, perform the following steps. 1. Launch the MyBGList project in debug mode and access the Swagger UI main dashboard. Second, click the https://localhost:4043/swagger/v1/swagger.json link below the title to access our web API Swagger definition file and save that file locally. Third, go back to the Swagger Editions homepage. Fourth, choose File, then Import File option to import the saved swagger.json file. Fifth, when the file is loaded, choose Generate Client, then HTML2 to download the zip archive containing a single HTML file. That HTML file is our auto-generated HTML-based UI. To see what it looks like, unzip and execute it in a browser. Not bad, right? Now that we have this static HTML file, we can choose how to release it to our audience via email, a partner-only website, or any other secure method without having to expose our Swagger definition file and or the Swagger UI directly. Alternative API documentation tools. The static documentation obtained by using the Swagger editor and Swagger CodeGen is one of many options for creating a suitable references for our web API. Several other open source and commercial tools can help us to achieve the same results, offering different UI or UX templates, additional customization features, and so on. I also encourage you to try the additional Generate Client options provided by the Swagger Edition, which include more advanced and visually appealing clients built with C, TypeScript, Angular, PHP, Dart, Go, Scala, and the like. We're ready to move our next topic, choosing a suitable .NET publishing mode. Understanding the .NET publishing modes, the first thing we need to learn is that .NET applications can be published in two modes, framework dependent. This publishing mode requires the presence of the .NET framework, which must be installed and available in the target system. In other words, we'll build a .NET application that can run only on hosting server that has been configured properly to support it. Self-contained, this publishing mode doesn't rely on the presence of the .NET components on the target system. All components, including the .NET libraries and runtime, will be included in the production build. If the hosting server supports .NET, the app will run in isolated mode, separating itself from other .NET applications. Self-contained deployment builds include an executable file and .x file on Windows platforms, as well as dynamic link library file containing the application's runtime. Note, the framework-dependent mode produces a platform-specific executable and a cross-platform binary in the form of a DLL file. The self-contained mode produces a platform-specific executable only. Let's try to understand the pros and cons of each publishing mode.
Working with the VM public IP address. The VM configuration panel is where we can review and change all the VM's main settings. The panel is split into several pages, all accessible from the left menu. If we access it from the Go to Resource button, we should be looking at the Overview page, which is a dashboard showing a summary of the current settings. From there, we should be able to retrieve the VM's public IP address, which is located in the right part of the screen. Adding an Azure DNS name. While we're here, we configure a unique DNS name that will resolve to that IP address by clicking the DNS name option below it. We'll gain access to a new settings page where we'll be able to input an optional DNS name label as shown in figure 12.10. As we can see, we use the lowercase VM name mybglist-win-01 to set the DNS name label. This will create the following Azure Managed Unique Subdomain, which will resolve to our VM's IP address, mybglist-win-01.westeurope.cloudapp.azure.com. But we don't want to use this domain to access our web API directly.
we want to have our API incoming request to be handled by the Cloudflare CDN that we set up earlier. For that reason, in the next section, we're going to configure our VM's public IP address on our CDN by creating a dedicated A record and subdomain for it. Adding a new A record, open another tab in the browser without closing the VM overview page and use it to access Cloudflare. Log in with the account we created earlier, select the relevant domain, mybglist.com in our sample, and click the DNS page on the left menu to access the domain's DNS configuration settings as shown in figure. Click the Add Record button to create a new record specifying the following options as shown in figure. Type A, name, Win01, IPv4 address, Azure VM public IP address 20.123.146.191 in our sample, proxy status, proxied, TTL, auto. These settings create a new win-01.mybglist.com subdomain that will point to the IP address of our Windows VM, like the Azure unique DNS name that we created earlier. Azure DNS name versus custom subdomain. There's an important difference between how the Azure DNS name and our custom win-01.mybglist.com subdomain will work in practice. The Azure managed subdomain will resolve directly to our VM server's IP, and the Cloudflare subdomain will not because we activated Cloudflare proxying and IP masking feature. More precisely, the win-01.mybglist.com subdomain will resolve to the Cloudflare's proprietary IP, which will internally forward all requests to our VM's public IP without exposing it to the public. Such a difference might seem trivial, but it could be relevant in terms of security as long as we use only the Cloudflare subdomain, keeping the Azure one hidden from public eyes. Moreover, notice that we intentionally chose not to use the www.mybglist.com domain name for this deployment tutorial. We prefer to use a subdomain that uniquely identifies the Windows VM that we'll create later, so that we'll be able to create additional VMs or host in future editions of this book. You're free to use www or any other suitable subdomain name instead. Click the Save button to persist the newly created A record to the domain DNS configuration so that we can test it. Testing the A record. The new subdomain will start working immediately because our domain DNS configuration is already handled by Cloudflare and the internal proxying feature doesn't need to propagate. But even if our Windows VM is already up and running, it doesn't have a web server listening to the HTTP 80 and or HTTPS 443 TCP ports. If we try to navigate to http://win-01.mybglist.com/ or https://win-01.mybglist.com/ with our web browser, we hit a 522 connection timeout error. Notice that the error is clearly coming from Cloudflare, meaning that the connection problem occurs between the CDN working and the host error as shown by the informative icons displayed by the error page. There's no need to worry. The error will disappear as soon as we configure a web server to handle the incoming HTTP request. First, let's fulfill another important task in Cloudflare. Create an SSL or TL certificate that we will configure to our origin server. Creating an SSL or TL's origin certificate. One of the main reasons why we choose Cloudflare as our CDN service provider is that it grants 2 free SSL or TL certificates for our domain, one for the Edge server, valid for everyone, and one for the origin server, valid for Cloudflare servers. The Edge certificate is automatically generated, renewed, and served by Cloudflare. The origin certificate must be created manually and then installed on the origin host. Why do we need an origin certificate? Setting up the origin certificate is optional. We need it only if we want Cloudflare to connect to the origin server using HTTPS, thus using the full SSL or TLS encryption mode instead of the default one, which uses HTTP. However, if we want to adhere to our security by design approach, we definitely need to switch to that encryption mode to ensure that all transferred data will always be encrypted from the origin server to the end user's browser and vice versa. Because we're going to configure our newly created Windows VM, now is a good time to generate the origin certificate. From Cloudflare Domains Configuration page, expand the SSL or TLS panel in the left menu and then select the Origin Server option to access the Origin Certificate section. Create an Origin Certificate in Cloudflare. Click the Create Certificate button to start the generation process. We access a dedicated form which we can fill with the following values: generate private key and CSR with Cloudflare. Yes. Private key type, RSA 2048. Host names, leave the default values. Choose how long before your certificate expires, 15 years. Then click the Create button to generate the certificate. After a couple of seconds, we access a page with two text boxes containing, respectively, our origin certificate and its private key. Copy and paste the content of each text box in a text editor of your choice, such as Windows Notepad, and then save both in a safe local folder using the following names: mybjlist.com-origin.pem for the origin certificate, mybjlist.con-origin.key for the private key. We're going to need these files when we configure our Windows VM to be the origin host. Before moving on to that, let's switch the Cloudflare SSL/TLS encryption mode from flexible to full to take advantage of what we did. Setting Cloudflare encryption mode to full. From Cloudflare's domains configuration page, expand the SSL or TLS panel in the left menu and then select the overview option to access the SSL or TLS encryption mode section. Then change the encryption mode from flexible to full. The full encryption mode ensures that Cloudflare will always use and require the origin certificate when connecting to our origin host, thus granting full encryption capabilities to our architecture's HTTP stack. We need to configure that host, which is what we're about to do. Configuring the Windows VM server. Now that we have created our Windows VM server, we need to connect to it. Azure gives us several ways to do that, the most secure of them being Azure Bastion, a fully managed service providing secure and seamless remote desktop protocol, RDP, and secure shell protocol SSH access to VMs without any exposure through public IP addresses. Tip: for additional info about Azure Bastion features and pricing, check out this link. The only bad thing about Azure Bastion is that it's a paid service with an hourly rate that might be too costly for our actual scenario. For the purpose of this chapter, we'll use a standard RDP connection by securely opening the 3389 TCP port on Azure VM. Note: to open the 3389 TCP port for inbound traffic on Azure, follow the instructions detailed in the appendix, using 3389 for the port number and RDP for the service name. It's important to remember that the 3389 TCP port is a common target for network-related attacks performed by malicious third parties, as it's used by a protocol, RDP, that allows attackers to take control of the VM remotely. Keeping that port open for everyone is hardly good practice in terms of security. To mitigate this risk, it's strongly advised to restrict the inbound rule to the IP addresses of our development machine, as explained in appendix. Configuring the Windows VM server. Now that we have created our Windows VM server, we need to connect to it. Azure gives us several ways to do that, the most secure of them being Azure Bastion, a fully managed service providing. Now that we have the 3389 TCP port open, we can connect with our new server using the RDC tool from our local Windows-based development machine. Type the public IP address of the Azure VM that we retrieved earlier and click Connect to initiate an RDP session with our remote host. Once connected, the first thing we must do is install and configure IIS, a flexible, secure, and manageable HTTP server that we'll use to serve our ASP.NET Core Web API over the web. Note, for reasons of space, we're not going to explain how IIS works to explore its functionalities. We'll use the settings strictly required to host our app. For additional information regarding IIS, check out this link. Together with IIS, we will install Web Deploy, an extensible client-server tool that can be used to publish and deploy web apps directly from Visual Studio, thus avoiding the need to implement other data transfer alternatives such as FTP. Last but not least, we're going to install a local instance of SQL Server to host our MyVGList Web API's production database. Installing IIS. To install IIS, follow the instructions detailed in the appendix. Be sure to do that in the Windows VM using the established RDP connection, not on your local development machine. Installing the ASP.NET Core hosting bundle. When IIS has been installed, we can proceed with downloading and installing the ASP.NET Core Windows hosting bundle, a convenient bundle that includes the .NET Runtime, the ASP.NET Core Runtime, and the ASP.NET Core IIS module. That's all we need to run our ASP.NET Core Web API using the framework-dependent publishing mode. The instructions for installing the ASP.NET Core Windows Hosting Bundle are detailed in the appendix. After the installation, be sure to restart the IIS service by following the appendix instructions. Installing the Web Deploy component. Web Deploy, formerly MS Deploy, is an IIS-related component that greatly simplifies the deployment of web applications to IIS servers. For our release and deployment tutorial, we're going to use it to create a one-click publishing profile that will allow us to deploy our MyVGList Web API from Visual Studio to the VM server in a fast and seamless way. It's important to understand that Web Deploy is not the only deployment option offered by Visual Studio. It's the one we have chosen for this book. If you prefer to use a more classic deployment approach based on a different data transfer method or protocol such as FTP, Xcopy, Robocopy, SCP, and the like, feel free to skip the Web Deploy installation. You will also need to create a different Visual Studio publishing profile and deal with the file upload task manually. Web Deploy installation instructions are detailed in the appendix. After installing it, we also need to open the 8172 TCP port for inbound traffic, which is required by the IIS Management Service and Web Deploy. Opening the 8172 TCP port. The 8172 TCP port must be opened at OS level using the Windows Firewall and network level using the Azure VM configuration panel. The Windows Firewall configuration should be okay, assuming we have already installed IIS with the Management Service optional role feature, as it's automatically handled by that component during the installation process. We need to open that port on Azure. Tip: to open the 8172 TCP port for inbound traffic on Azure, follow the instructions detailed in the appendix using 8172 for the port number and Web Deploy for the service name. With that done, we can move to the next step, configuring IIS to host our web API. Let's start by launching the IIS Manager app, a management tool that gets installed with IIS and can be used to configure most IIS settings through an intuitive, easy-to-use GUI. The first thing to do here is install the SSL or TLS origin certificate that we got from Cloudflare a short while ago. However, the PEM/key certificate format that we have saved to our local disk cannot be directly imported to IIS. To do that, we need to convert them to a PFX file. Converting the PEM certificate to PFX. To quickly convert our PEM certificate to a PFX file, we suggest using OpenSSL, an open source command line tool that can be used to perform a wide variety of cryptography tasks, such as creating and handling certificates and related files. Most information about OpenSSL, including the updated GitHub link to the project's source code, can be retrieved from its official website. However, the Windows binaries and installer packages, which is what we need to install it, are available at the following third-party URL, courtesy of Shining Light Productions. More precisely, we need to download the Win64 OpenSSL version 3.0.5 Lite Edition. The Lite Edition is lightweight, 5 MB, and contains only the tool's basic features, which are more than enough for our purposes. The installation process is straightforward. We'll be asked only to copy the required DLLs to the Windows folder or to separate folder, both will work, and to make an optional donation to the authors. After installing it, the tool will be available at the following FAT C/program files/OpenSSL-win64/bin. To use it, open a command prompt, navigate to the folder where we put the .pem and .key files, and execute the following one-line command. Tip: in case you install the tool on a different path and or use different file names, change the command accordingly. The tool will ask us to enter an export password. Choose one and remember it, as we'll need it in a short while. Then confirm it by typing it again and click enter to generate the mybglist_origin.pfx file. Now we can safely delete the .pem and .key files from our local machine, as we don't need them anymore. Now that we have the .pfx file, we can install it in our Windows VM IIS. Installing the SSL or TLS origin certificate. Go back to the Windows VM desktop and then copy the mybglist-origin.pfx file from our local machine to the remote VM using the RDP copy or paste capabilities. Switch to or open the IIS Manager main dashboard, locate the server certificates icon, and click it to access that section. Next, click the Import Link button in the Actions menu on the right to access the Import Certificate modal window. The IIS Manager's Import Certificate window. Fill the form with the following values shown in figure. Certificate file, .pfx, the .pfx file path on the remote VM. Password, the export password we used earlier. Select certificate store, web hosting. Allow the certificate to be exported, yes. Click OK to import the certificate. Tip: again, we can safely delete the .pfx file from our local machine and from the remote server right after importing it. We can always export it from the IIS Manager certificate store if we ever need to. With that done, we can finally configure our ASP.NET Core Web API to IIS, adding the MyBGList website to IIS, keeping the IIS Manager GUI open, locate the Sites folder node in the left tree view, right-click it and choose the Add Website option to access the modal window, which we will use to add a new website entry for our MyBGList Web API. Fill the form with the following values: site name, MyBGList, content directory, application pool, MyBGList, physical path, C://inetpub/MyBGList, binding, type HTTPS, IP address, all unassigned, port 443, hostname win-01.mybglist.com, requires server name indication, yes, SSL certificate, Cloudflare origin certificate, start website immediately, yes. After we click OK, a new MyBGList website entry should appear in the left preview right before the default website. Tip, let's take this chance to disable the default website. Right click, manage website, stop as we don't need it. We're almost done. We need to start the web management service. Starting the web management service. In the IIS Manager GUI, left click the main server's root node. It should be called mybglist-win-01 like the VM name. Locate the management service icon in the central panel and click it to access another configuration window. From here, we need to do the following. First, activate the Enable Remote Connections checkbox. Second, start the service by clicking the Start button to the right. Web Management Service Startup Mode. The Web Management Service is configured with a manual startup mode, meaning that it won't automatically start when the VM boots or reboots. If you plan to consistently use the Web Deploy component to publish and deploy our app, we might think of changing the startup behavior of this service, as it's required to be running for that feature to work. This can be done using the control panel, administrative tools, services app. Now that IIS has been properly configured, we can deal with the database. Creating the production database. In Chapter 4, we hosted our development database on a local instance of SQL Server installed on our development machine. More precisely, we opted for that route instead of using a cloud-based solution such as the SQL database provided by Azure. Now that we are releasing our web API in production, we are faced with that same choice on-premise or cloud-based. For reasons of space, in this deployment tutorial, we're going to pick on the on-premise option again so that we can replicate what we have already learned and got used to. However, readers who want to challenge themselves with a different alternative such as the previously mentioned Azure SQL database service are strongly encouraged to do that. Note, for additional info, documentation, and installation guides about the Azure SQL database service and other Azure SQL related available products, check out this link. Now that we have chosen our path, here's what we need to do. First, install SQL Server. Second, install SQL Server Management Studio. 3. Create a new instance of the MyBGList database. All of these tasks can be easily dealt with by repeating the same steps we took in Chapter 4. Should we install SSMS on the VM server? Technically speaking, we could avoid installing the SQL Server Management Studio tool on the server and connect to the remote database using the SSMS local instance that we installed on our development machine. However, this would require us to open the 1433 TCP port as we did with 3389 and 8172 earlier, which would lead to additional security problems. In case we want to do that, we should definitely restrict the inbound rule to the IP addresses of our development machine as explained in the appendix. When creating the MyBGList database, be sure to also create its login and user structure as we're going to need them for the production connection string. Note, for obvious security reasons, be sure to set a different password for the production login. Using the same passwords for development and production environment is a bad practice that could lead to severe data breaches. Once the MyBGList production database is up and running, we can finally create the app settings.production.json file on the Windows VM. creating the app settings.production.json file. When we added the MyBGList website entry to IIS, we were asked to specify a physical path, which we filled with c:/inetpub/mybglist earlier. That's the file system path where IIS expects our web API artifacts to be deployed, including the app settings.json files. Open that folder using the remote VMs file explorer or command prompt and create a new app settings.production.json file within it using a text editor of your choice, such as Windows Notepad. That's the file that will be used by our ASP.NET Core Web API to override the app settings.json values in the production environment. Ideally, the app settings.production.json file should contain the same keys and values that we currently have in our local secrets.json file, with the sole difference of the connection string's default connection value, which we must replace with the values required to connect to our MyBGList production database. If we follow the same naming conventions that we use when creating the development database, we'll have to change the user ID and/or password values, leaving the rest as it is. Warning, for the sake of simplicity, we're not going to change the Azure application insight, connection string, and the Redis configuration values because they are not that relevant to our sample tutorial scenario. But assuming we want to use those services, we should definitely create different instances for development and production environment as we did with the MyBGList database. We can quickly deal with this task by using the RDP client to copy and paste the content of our local secrets.json file to the app settings.production.json file and then perform the required value change on the new file and then save it to disk. While doing that, ensure that the app settings.production.json file has the correct extension, .json and not .json.text, which is a common problem when using Notepad. With this last step, our Windows VM configuration is complete. Now it's finally time to publish, release, and deploy our web API. However, before doing this, we need to learn more about Visual Studio built-in publishing capabilities and how this feature actually works. While servers and workstations have many of the same hardware and components and in many cases use the similar operating systems, their roles in the network and therefore the requirements placed upon them are quite different. Although many of the skills required to maintain workstations are transferable to maintaining servers, there are certainly enough differences both in the devices themselves and in the environment in which they operate to warrant such certification. So this chapter talks about server hardware. Racking. Racking is the process of installing rack systems and then populating the rack systems with rack-mounted devices such as routers, switches, servers, intrusion detection systems, devices, and many other types of networking gear. Enclosure sizes, unit sizes. Rack systems can accommodate a variety of device sizes. Each device is a unit, and in the section, you'll learn about standard unit sizes. 1U, 2U, 3U, etc. Rack mount servers are those that are designed to be bolted into a framework called a rack and thus are designed to fit one of the server's standard size rack slots or bays. They also require rail kits which when implemented allow you to slide the server out of the rack for maintenance. Dimensions, rack layout. Rack systems have many options to accommodate various power and cooling requirements. Cooling management. When all power considerations have been satisfied, your attention should turn to ensuring that the servers do not overheat. Airflow. Placing intake and exhaust in close proximity on the same side of the chassis, which cause exhausted warm air to flow back into the chassis, lowering overall cooling performance. Installing panels and components such as the graphic cards, motherboard, and hard drives in the way of airflow. Thermal dissipation. Heat sinks are one approach with which you probably are familiar. Baffles or shrouds. Another technique used both inside the case and in the server room is deploying baffles or shrouds to direct and alter the flow of air. Fans. Fans are used in several places inside the server case. There may be one on top of the heat sinks used to assist the heatsink in removing the heat from the CPU. Liquid cooling. Safety. Proper lifting techniques. Rock balancing. Sharp edges and pinch points. Power distribution units. Keyboard video mouse placement. A keyboard, video, and mouse device allows you to plug multiple PCs, usually servers, into the device and to switch easily back and forth from system to system using the same mouse, monitor, and keyboard. The KVM is actually a switch that all of the systems plug into. There is usually no software to install. Just turn off all the systems, plug them all into the switch, and then turn them back on. Then you can switch from one another using the same keyboard, monitor, and mouse device connected to the KVM switch. Serial. The issue that arises is that even if technician's laptop had a serial port, which is unlikely today, there would be at most one. The consoles of the connected device can then be accessed by connecting the console server over a serial link such as modem or over a network with terminal emulator software such as Telnet or SSH, maintaining survivable connectivity that allow remote users to log in the various consoles without being physically nearby. Rail kits. Rail kits are used to provide a mechanism for sliding the server out of the rack. Power cabling. Computing equipment of any kind, including servers, require a certain level of power and an environment that is cool enough to keep the devices from overheating. Periodic testing of batteries. Cable management. Cable ties. Network cabling. In order for all of these devices in all these racks to talk to one another, we have the network cabling. And in the data center, there will be lots of this cabling. Redundant networking. In the same way that you must build in power redundancy, you must also build in network redundancy. This could be achieved on an endpoint such as server by installing and connecting multiple network interface cards. So if one fails, additional connections are available. Publishing and deploying. In this section, we'll learn how to publish our app. More specifically, we'll create the output artifacts, framework libraries, project binaries, static contents, and the like that will then be deployed to the production servers to release our app over the World Wide Web. Here's what we're going to do in detail. First, choose a suitable .NET publishing mode among the 4 available ones, which will be done after learning the pros and cons of each of them. Second, create a Windows publishing profile using Visual Studio's publishing capabilities to publish and deploy our web API project on the production server. Are we ready? Let's start. Introducing Visual Studio Publish Profiles. The Publish feature is one of the greatest advantages of Visual Studio and VS Code over other IDE alternatives. A built-in set of capabilities that allow developers to build, publish, and sometimes even develop a web application directly from the GUI, thus greatly simplifying the whole release and deployment process. The Publish feature is basically a wizard that guides the developer to build a profile, a set of configuration settings about the project, and the deployment target. Once created, the profile is saved to a dedicated .pub XML file on a dedicated /properties/publish profiles/folder, which is created together with the first profile if it doesn't exist already. Such a file or folder structure allows applications to have multiple publishing profiles, meaning that we can pre-configure its release and deployment settings over several different locations. To create a new publish profile, right-click the MyBGList project root node in Solution Explorer and select Publish. Tip: alternatively, we can select the Publish MyBGList option from the Build section of the menu. Once we do that, we'll be greeted by a modal window that will ask us to select one of several available publish targets as shown in figure. Figure Visual Studio Publish feature. Each available target provides a short description explaining how it works. The important thing to notice here is that most targets will create a profile that will perform the publishing and deployment task together, meaning that our app will also automatically go live at the end of the publishing process. However, a few of them, such as the folder target, allow us to only publish the artifacts locally, thus requiring us to manually perform the deploy using different techniques. Publish and deploy requirements. As we can easily expect, the publish and deploy profile targets require the hosting server to support or be compatible with a specific deployment module, package, or component, be it a FTP server, the web deploy component that we have installed a short while ago, or other services supported by Visual Studio. This requirement is quite easy to fulfill when dealing with Windows-based host Microsoft services, such as the Azure App Service. However, it can be difficult for Linux servers, where these techniques are not supported. For that reason, publishing profiles for Linux hosts typically target a local folder or an FTP server pre-installed on the host. Because we installed the web deploy component or Windows VM server, our best options here would be creating a publishing profile based on the Azure target. Let's do this. Creating an Azure VM publish profile. From the Visual Studio Publish modal windows, choose the Azure target, select the Azure Virtual Machine option from the next screen, and click Next to proceed. In the following panel, we'll be asked to select or connect an Azure account and subscription name. After completing that part with the relevant info, we should be able to select our Windows VM as shown in figure. Selecting the Windows VM where we want to publish and deploy our app. Click the Finish button to create the publish profile, which will be saved in the /properties/publish profile/folder. From now on, if we right-click the MyBGList root node in the Solution Folders tree view and select the Publish option again, Visual Studio will open a dedicated MyBGList Publish tab that can be used to visually edit and configure the publishing profile we have created. Let's take the chance to do that because we need to change a couple of default settings that Visual Studio took for granted while creating the profile. Configuring the Publish profile. From the MyBGList Publish tab, click the Show All Settings link button or More Action, then Edit to access a modal containing the Publish profile's configuration settings as shown in figure. From there, change the following settings: connections, site name, MyBGList. It must match the name of the website entry that we created on IIS. Username, insert the VM administrator's username. Password, insert the VM administrator's password. It will make sense only if you activate the Save Password checkbox below. Save password, choose yes if you want to save it and no if you prefer to type it every time. Destination URL, HTTPS, yada yada. Validate connection. Click this button to ensure that the connection can be performed successfully with these parameters. Settings, configuration, release, target framework, net 6.0, deployment mode, framework dependent, target runtime, WinX64. Right after doing that, click save. We can finally hit the publish button near the top right of the My Video list. Publish tab to finally start the publish, deployment, and post-deployment testing tasks.
contain security codes generated by personal authentication apps and biometric scans such as fingerprints, retina, and more codes. I won't cover all those techniques in this chapter, but several online resources can provide more information about these features. For further details on authentication in ASP.NET Core Apps, check out this video.
Cable channels, cable management. Cable channels is part of cable management. It can be time consuming to tie cables up, run them in channels, and sneak them through walls, but it is time well spent when it keeps one person from harm. It is all too easy to get tangled in a cable or trip over one that is run across the floor. Cable channels are used to route cables across floors and other surfaces. They enclose the cables and protect them from damage while also preventing someone from tripping over them. Cable management trays. While cable channels are good for floors, in some cases, cable must be run up and over racks of equipment. In such instances, you can use cable trays, which come in two types, vertical and horizontal. Vertical, for example, you may need to get cable from the back of a rack to the ceiling, where it may intersect with horizontal trays that lead the cabling out of the room or to another rack in the room. Horizontal trays are used to route cable across the room on the floor, the ceiling, or anywhere in between. Server chassis types. When we use the term form factor when discussing any computing device or component, we're talking about its size, appearance, or dimensions. In this section, we'll look at the major server form factors, the rack mount, the tower, and the blade. Tower. A form factor with which you are likely to be familiar with is the tower server. This type bears the most resemblance to the workstations you are used to working with. Rack mount. Rack mount servers are those that are designed to be bolted into a framework called a rack, and thus are designed to fit one of several standard size rack slots or bays. They also require rail kits which, when implemented, allow you to slide the server out of the rack for maintenance. Server. You may also have servers you need to physically secure from tampering that are not located in racks or lockable server cabinets. Blade technology. Finally, servers may also come in blade form. Blade enclosure, blade server, chassis locks, or intrusion detection. Server components. Servers have all the same components that are found in workstations, but due to the high workloads they experience as a result of their roles in the network, the component must be more robust. Hardware compatibility list. Vendors of both software and hardware create compatibility lists that can be used to ensure that a potential piece of software or hardware will work with the server. Operating systems. Major operating system vendors issue several types of compatibility lists: hardware, applications, central processing unit, socket type. Gauge level 1 and level 2, CPU performance, CPU stepping. When a manufacturer invests money to do a stepping, that means they have found bugs in the logic or have made improvements to the design that allow for faster processing. Architecture. Replacing a CPU in a server. Shut down and remove the power from the entire system. Remove the server node from the system. Many systems have multiple servers in base to each server. You must remove the bay. Remove the server node cover. Follow any instructions included with the documentation. Use the proper type and size of screwdriver, usually a number 2 Phillips head, to loosen the screws, usually 4, holding the heatsinks, and then leave it off the CPU. Unclip the first CPU retaining latch and then unclip any remaining latches. Open hinge CPU cover plate, remove the old CPU, insert the new CPU, install the heatsinks. Don't forget to put thermal grease between the CPU and the heatsink. Replace the server node cover, reinstall the server node, replace power cords, and then power on the system. Graphics Processing Unit. The graphics processing unit is a processor dedicated to working on behalf of generating graphic image. Memory, DDR2 and DDR3, static versus dynamic, cache latency, memory playing, replacing RAM. NICs, RAID controllers, summary. Anna got into the carriage in Stillward state that when she had left the house, to the former torment was now added the feeling of being insulted and cast out. Which she clearly felt when she met Kitty. "Where to, ma'am? Home?" asked Piotr. "Yes, home," she said, not even thinking of where she was going. How they look at me as if it has something frightful, incomprehensible and curious. What can he be talking about so ardently with the other one, she thought, looking at two passers-by. Is it really possible to tell someone else what one feels? I wanted to tell Dolly, and it's a good thing I did it. How glad she would be of my unhappiness. She would hide it, but her main feeling would be joy that I have been punished for the pleasure she envied me. Kitty, she would be even more glad. How I see right through her. She knows that I was more than usually friendly to her husband, and she's jealous, and she hates me, and also despises me. In her eyes, I am an immoral woman. If I were an immoral woman, I could get her husband to fall in love with me if I wanted to. And I did want to. This one is Prince Eric himself. She thought of a fat, red-cheeked gentleman who, as he drove by in the opposite direction, took her for an acquaintance and raised a shiny hat over his bald, shiny head and then realized he was mistaken. He thought he knew me, and he knows me as little as anyone else in the world knows me. I don't know myself. I know my appetites. As the French say, those two want that dirty ice cream that they know for certain, she thought, looking at two boys who had stopped an ice cream man who was talking the barrel down from his head and wiping his sweaty face with the end of a towel. We all want something sweet, tasty. If not candy, then dirty ice cream. And Kitty's the same. If not Vronsky, then Levin. And she envies me. And hates me. We all hate each other. Kitty me, that's the truth. Twitkin, Coiffure, GMS Fur Copper Part Twitkin. I tell him when he comes, she thought and smiled. But at the same moment, she remembered that she now had no one to tell anything funny to. And there isn't anything gay or funny. Everything is vile. The bells ring for vespers, and this merchant crosses himself so neatly, as if he's afraid of dropping something. Why these churches, this ringing and this light, only to hide the fact that we all hate each other? Like these cubbies who quarrel so spitefully. Yashvin says, he wants to leave me without a shirt, and I hate. That's the truth. In these thoughts, which carried her away so much that she even stopped thinking about her situation, she pulled up at the entrance of her house. Only on seeing the hall porter come out to meet her did she remember that she had sent the note and the telegram. "Is there an answer?" she asked. "I'll look at once," said the porter, and glancing at the desk, he picked up the thin, square envelope of a telegram and handed it to her. "I cannot come before 10, Vronsky," she read. "And the messenger hasn't come back yet?" "No, ma'am," replied the porter. "Ah, in that case I know what to do," she said, and feeling a big rat surge up in her, and a need for revenge, she ran upstairs. I'll go to him myself, before going away forever. I tell him everything. I've never hated anyone as I do this man, she thought. Seeing his hat on the coat rack, she shuddered with revulsion. She did not realize that his telegram was a reply to her telegram, and that he had not received her note. She imagined him now, calmly talking with his mother and Princess Sorokin and rejoicing at her suffering. Yes, I must go quickly, she said to herself, still not knowing where to go. She wanted to get away quickly from the feeling she experienced in that terrible house. The servants, the walls, the things in the house, it all gave her a feeling of revulsion and anger and pressed her down with its weight. Yes, I must go to the railway station, and if I don't find him, I'll go there myself and expose him. Anna looked up the train schedule in the newspaper. The evening train left at 8:02. Yes, I can make it. She ordered other horses to be that harnessed and began packing her traveling bag with the things necessary for several days. She knew she would not come back there anymore. Among other plans that entered her head, she also vaguely decided that after whatever happened there at the station or at the Countess' estate, she would take the Nizhny Novgorod Railroad to first town and stay there. Dinner was on the table. She went up to it, smelled the bread and cheese, and convinced that the smell of all food disgusted her, ordered the carriage to be brought, and went out. The house already cast its shadows across the wood street, and the clear evening was still warm in the sun. Anushka, who accompanied her with her things, and Pyotr, who put them into the carriage, and the obviously disgruntled driver, they all disgusted her and irritated her with their words and movements. I don't need you, Pyotr. And what about your ticket? Well, as you like, it makes no difference to me, she said with vexation. Pyotr jumped up on the backs and arms akimbo, told the driver to go to the railway station. Here it is again. Again, I understand everything, Anna said to herself as things at the railway went off, rocking and clattering over the small cobbles. And again, the impressions began changing one after another. Yes, what was that last thing I thought about so nicely? She tried to remember. Tweeting? Colfer? No, not that. Yes, it was what Yashvin said. The struggle for existence and hatred, the only thing that connects people. No, you're going in vain. She mentally addressed a company coach and four who were evidently going out of town for some merriment. And that dog you're taking with you won't help you. You won't get away from yourselves. Glancing in the direction in which Pyotr had just turned, she saw a half-dead rank factory worker with a lolling head being taken somewhere by a policeman. Sooner than one, she thought. Count Bronsky and I didn't find that pleasure either, though we expected so much from it. And now for the first time, Anna turned the bright light in which she saw everything upon her relations with him, which she had avoided thinking about before. What was he looking for in me? Not so love as the satisfaction of his vanity. She remembered his words, the expression on his face like an obedient pointer in the early days of their liaison. And now everything confirmed it. Yes, there was the triumph of successful vanity in him. Of course, there was love too. But for the most part, it was the pride of success. He boasted of me. Now it's past. Nothing to be proud of. Not proud but ashamed. He took all he could from me and I'm of no use to him anymore. I'm a burden to him and he tries not to be dishonorable towards me. He let it slip yesterday. He wants the divorce and marriage in order to burn his boats. He loves me, but how? The sense is gone, she said to herself in English. This one wants to astonish everybody and is very pleased with himself, she thought. Looking at a red-cheeked sales clerk riding a red horse, Yes, I no longer have the same savor for him. If I leave him at the bottom of his heart, he'll be glad. This was not a supposition. She saw it clearly in that piercing light which now revealed to her meaning of life and of people's relations. My love grows ever more passionate and self-centered, and he keeps fading and fading, and that's why we move apart. She went on thinking. And there's no help for it. For me, everything is in him alone, and I demand that he give his entire self to me more and more. While he wants more and more to get away from me, we precisely went towards each other before our liaison, and after it, we resisted in different directions. And it's impossible to change that. He tells me I'm senselessly jealous, and I've told myself that I'm senselessly jealous. The bell rang. Some young men went by, ugly, insolent, and hurried, and at the same time conscious of the impression they produced. Pyotr also crossed the room in his livery and gaiters with a dull, animal face, and came up to her in order to escort her to the train. The noisy men quieted down when she passed them on the platform, and one whispered something about her to another. Something nasty, to be sure. She mounted the high step and sat by herself in a compartment on a soiled, once white spring seat. Her bag bounced on the springs and lay still. Outside the window, Pyotr, with a foolish smile, raised his gold-braided cup in a sign of farewell. An insolent conductor slammed the door and latched it. An angry lady with a bustle, Anna, mentally undressed the woman and was horrified at her hideousness, and a little girl, laughing unnaturally, ran by under the window. Katerina Andreevna has it. She has everything. Matante, cried the girl. The little girl, even she is ugly and affected, Anna thought. So as not to see anyone, she quickly got up and sat at the opposite window in the empty carriage. A dirty, ugly music in a peacock, his matted hair sticking out from under it, passed by the window, bending down to the wheels of the carriage. There's something familiar about the hideous music, thought Anna, and recalling her dream, she stepped away to the opposite door, trembling with fear. The conductor was opening the door, letting in a husband and wife. Would you like to get out? Anna did not reply. Neither the conductor nor the people who entered noticed the expression of terror